Preparing to live stream the meeting on YouTube.
Successful, I hope.
About 1 minute. Okay. Preparing to live stream the meeting on YouTube. Okay.
Successful, I hope.
About 1 minute.
I hope success for all participants.
Okay.
And my team.
Preparing to
I hope success for all participants.
Süleyman Hocam, YouTube'un sesini kısabilir misiniz? Birinizde YouTube açık. Yaşar Hocam, şimdi co-hostluk verdim. Ali Hocamız da burada. Wang da burada. İkisine de co-hostluk tanımladım.
Günaydın Ali Hocam. Wang Jiang, welcome.
Hello.
Hello. Yeah.
Can you hear me? Yes.
Yes, yes, I see you.
Hello, John Kwan. Mr. Ali Hojam, good morning.
Good morning. I am Jiang.
Bye.
Wait a minute. We have intro video firstly. Only 2 minutes. After that, your screen. We see your screen. Thank you. Thank you, Wang.
Yes.
Professor Ali Teke, please open your voice. Your voice is closed just now.
Is it open? Is
Yes,
it okay now?
It is okay. Okay.
Okay.
We have 3 minutes.
Okay then.
Yeah.
Well, we have come to the last day of such a scientifically fruitful and excellent organization conducted by especially Süleyman Özçelik, Professor Süleyman Özçelik and his colleagues.
Ali Hocam, özür dilerim. Biz bir önce video göstereceğiz. Çok kısa, 2 dakika.
Öyle mi? Tamam.
Aha, waiting room'da henüz bekleyenler var. Onları da içeri alacağız. Tam 9'da başlayacağız hocam.
Tamam.
Tamam. Çok sağ olun hocam. Teşekkür ediyorum.
Rica ederim.
Wang Jiang, if possible, close the background curtain completely. There are some light from your back.
What's
Okay,
yeah.
okay, it is good, yeah. We will start with a video.
Katılımcılarımızı bekliyoruz Yaşar Hocam. Şu an artıyor çünkü hızlı bir şekilde.
Yes.
1-2 dakika bekleyelim. Onları içeri aldıktan sonra videoyu başlatacağım. Ondan sonra sözü Ali Hocam'a bırakacağız.
Okay. We have 2 minutes. Then we will invite all the participants, and after that we will share a 2-minute video and then introduction about you, and we will start it.
Please, Professor Ali. Okay.
Okay, thank you very much. I would like to say hello and good morning to everybody. We have come to the last day of such a scientific, fruitful, and excellent organization conducted by Professor Özçelik and his colleagues. I would like to congratulate and thank all you who contributed to this conference once again. Today, we have three distinguished speakers in this session, in the first session of the last day of the conference. The plenary speaker is from China, and two invited speakers are from Australia. So we're going to start with the plenary speaker, Professor Jian Wang, who will join us from China. He is the professor at the Wuhan National Laboratory for Optoelectronics, Huashan University of Science and Technology. Give a brief information about him as follows. Professor Wang received his PhD degree in physical electronics from Wuhan National Laboratory for Optoelectronics, Huashan University of Science and Technology in 2008. He worked as a postdoctoral research associate in the Optical Communication Laboratory, University of Southern California, from 2009 to 2011. He is currently a professor at the Wuhan National Laboratory for Optoelectronics, Huashan University of Science and Technology. He is a director of the development of optoelectronic devices and integration at the same institute. He leads the multidimensional photonics laboratory. His research interests include optical communication, optical signal processing, silicon photonics, photonic integration, orbital angular momentum, and the structured light. He has published over 200 papers in peer-reviewed international journals, including Science, Science Advances, Nature Photonics, Physical Review Letters, Optics Express, and Optics Letters. He has authored and co-authored over 150 international conference papers. He has also given 100 tutorial, keynote, invited talks in international conference. He is currently the topical editor of the Optical Letters, Chinese Optic Letters, and area editor of the Microwave and Optical Technology Letters. He's also frequently reviewer of Nature Photonics and the Nature Communications. So his talk is going to be about today, multidimensional entanglements transport in conventional single mode fiber. Professor Wang, if you are ready, please in advance. We are pleased to advance that you will share your valuable works with the audience and participants attending this conference. If you are ready, it is welcome to take the microphone and start your presentation, please.
Yes. So can you see the shared screen?
Yes, we can see it.
Does it work when I switch it? Does it work?
Yes, it's working now.
Okay. Good morning, everyone. Maybe good afternoon, good evening, and to all of the world. And thank the chair for the kind introduction. It's my great honor to be here. I mean, through the online to give my talk here. The title of the talk is Multidimensional Entanglement Transport in Conventional Single Mode Fiber. This is a joint work with Professor Andrew Forbes in South Africa. And since it's a plenary talk, so I'd like to slightly change my title of the talk a little bit. I will kind of like extend the talk to be classic and quantum communications using structured light. So here shows the outlines. First, I will give a brief introduction of structured light. Then I will talk about some recent works of the classic communications using structured light, including the free space, fiber-based, underwater, and even chip-based structured light communications. And after that, I will also talk about the quantum communications using structured light, especially the multi-dimensional entanglement transport in single mode fiber, and also the high-dimensional quantum cryptography in ring-core fiber. And finally, is a brief summary and perspective. So structured light. So what is a structured light? So structured light, also known as the tailored light, or shift light, scalped light, or even custom light, which is typically characterized by spatially variant amplitude phase pollution distribution. So in this screen, actually, you can see some typical examples of the structured light. For example, this one with which is a Hermite Gaussian beam with a spatially variant amplitude distribution, and this one with a with a spiral phase structure carries orbital angular momentum. We also call it like a twistor light just because of this spiral phase structure. We also have this spatially variant polarization. For example, for this one, which is a radially polarized beam, we call it like a vector beam. So all of this actually can be called the structured light, which is actually access the spatial structure domain of the photons. We know the photons actually have multiple domains. For this structured light, actually it tailors the spatial structure of the photons. For example, for this object angular momentum, actually of the twistor light in the middle, actually you can see here, this is a Gaussian beam, and the beam width actually is a planar phase front. But for when it carries this spiral phase structure, because of the phase singularity at the beam center, there is a low intensity at the beam center. So you can see this donut shape.
Do we lose the connection?
Weak connection from your side, I think.
Professor Ali Teker, there is a small technical problem with the connection of Professor Jian Wang. We are waiting for connection. Just now, it's no okay. Jiang Bian, can you hear me? Wang Jiang, we have your slides. Just we don't have your voice. Dear participants, please wait. It is very small technical problem. We will come back to the meeting and session. So just I'm asking Professor Zhang Bian, can you hear me? Yes, Professor Wang Jiang is entered just now to the room, and but we don't have your voice just now. Can you hear me, Wang?
He is absent now. No. We are
Yes.
waiting again.
So, Wang, can you
Now it's
hear
okay.
me? Yes. Jian Wang,
His microphone is okay now.
but I can't hear him. Wang, if you hearing me, you can write in chat box, and you can open your video if possible. Yes, yes. But I cannot hear you, Wang. Just know you opened your video, but we don't have any. Okay. I think there are some weak connection maybe in your side, Jian Wang. So it's no problem. Maybe you can restart your computer. We will be waiting for you. If we don't have any solution for this, please check and restart. We have 2 minutes for this, and if possible, our organizers, if the chair of the session let us, we can play the video again, and we'll be waiting for the Jiang Wang after 2 minutes. Okay.
Yaptım.
Wang Jian, can you hear me just now?
I can hear you. Can you hear me?
Okay, I can hear you. Professor Ali Teke, you can continue. Go on, please.
Sorry.
Okay.
We are sorry for the delay from the technical problem. So we can go ahead from the, if you want, if we can go ahead from the beginning since, or you can
See the screen?
very left. Okay, yeah, we can see this screen.
Sorry, but I don't know what happens. I'm actually my microphone works well, but anyway, sorry for taking your time. So actually, those structured actually can find lots of interesting applications, including for this one in this slide. You can see it can be used for the sensing, for this kind of Doppler metrology, and also it can be also used to do some like optical twist spanner. Actually, you can see this one. You actually have this like we have this like twister light emitting from this fiber. So actually, then it can actually trap these like particles and rotate them like the optical spanner. And for optical communications, actually, generally we need lots of devices. For example, the generator and the detector. Typically, we may need some. Actually, we have some. We have different ways to generate and detect this structured light. For example, the spiral phase plate, the cylindrical mode converters, special light modulator, integrated silicon photonic device, angular grating, and even materials and metal surfaces. And here shows one example, which is kind of on silicon platform. Actually, we can design and fabricate this kind of elliptic silicon resonator array. And for each of these like resonator, actually by probably controlling its like size and its orientation, we can control its localized amplitude and phase response by probably arranging this array. Actually, we can actually, for example, we have Gaussian beaming. We can flexibly shift its like spiral phase front, so we can have this like twisted beam out. So if we generate multiple these OEM beams and carry different data information, we can use them for OEM multiplexing communications. And also at the receiver end, we can also do this, do it in the opposite way. We can do the OEM demultiplexing. And here shows another example of the OEM generator based on the holographic method. So we have this holographic grating. We transfer this grating on top of the silicon waveguide. So when an in-plane guided mode, we have an in-plane guided mode here. So when it propagates through this region, it will have like localized phase mismatching. Then it can emit light out. So we can generate this OEM beam. When we have different inputs, actually we can generate either OEM -1 or either OEM like a positive one. If we simultaneously have the two inputs from two sides and probably control their relative phase, so at the output, actually we can even do this kind of OEM synthesizer. We can control its rotation and its shape. And this kind of sub-wavelength structure actually shows really broadband like property. You can see here even larger than 100 nanometers response. We can further extend it to a complicated version. So in this design, actually, you can see here we have a superposed holographic design. So we have X orientation and Y orientation. We super them together. So we transfer this complicated hologram on top of this silicon waveguide. So for this one, we have 4 ports. So if we have the input light from these 2 ports, we will generate the X polarized OEM, either positive one or -1. If we have 2 input ports from the other input ports, actually we can generate the Y polarized OEM beams. Actually, these two holograms actually can carry different topological charges. That means this kind of design, which is first ultra compact, second is broadband, larger than 100 nanometers bandwidth, and the third is pollution diversity. It can support both X pollution and Y pollution, and also it can support multiple OEM beams. So it is kind of like an ultra compact solution for this broadband pollution diversity OEM generator. And if we also add a matter mirror at the bottom here, actually, because when the light, you have the light propagating through this waveguide, part of the light actually also are leaked into the substrate. So if we add a matter mirror here, actually, it can fully use the light. In this case, we can improve the efficiency by about 5 dB. So you can see here that by using this structure, we can also successfully generate X polarized or Y polarized these beams. And we can also do this like OEM generator and as a fiber facet. If we transfer this like microstructures and the fiber facet, we can also do this kind of OEM generation. Which is kind of like a fiber compatible. It also shows like a broadband response. Here shows another example of the all fiber twist light generator. As you can see here, so at the input we have single motor fiber. So at the output we have a few motor fiber. So we splice them together. So then we add a long period fiber grating. We add pressure here, so it can do the like mode conversion from the Gaussian mode to this like high order mode. Then we rotate it by 45 degrees. When we add another like pressure here, so it will introduce a biorefringence. So for the X and Y component, they have different like refractive index. After propagation for a suitable distance, then it will introduce a pi/2 relative phase shift between the X and Y polarized components. Then at the output, you can generate this OEM beam. So at the bottom, actually, the other experiment results, you can clearly see this donut shape. When it is interfered with a reference Gaussian beam, you can also see this kind of spiral intensity distribution, which can be used to confirm the OEM generation. And we can even use a very simple approach. We can directly do this kind of like slightly offset splicing here. Then we add an inline pollution controller. As the output, we can also generate these optical vortices, and you can see here within a large bandwidth, we can even observe this high quality OEM generator. So all of this are about the generation. There are lots of works. Actually, if you have interest, you can go through the previously mentioned review article. And in addition to the OEM generator, actually you also need the multiplexer and demultiplexer for optical communications. Here shows some examples. For example, you can use 3D photonic integrated circuit, and this OEM bond sorter based on the transform optics, and also this OEM diamond grating, and even complex multi-OEM phase mask. So here shows one example of the all fiber OEM multiplexing and demultiplexing approach. Actually, it's based on the directional coupling of the optic fiber coupler. But instead of using the traditional single motor fiber, here we use a large core fiber which can support the OEM mode, as you can see here. So when we have a fundamental Gaussian mode in, actually it can excite, for example, the HE21 like old mode. Then if we have another pollution, for example, Y pollution, then we can excite the HE21 even mode. When you have a circularly polarized Gaussian mode in, because it can be decomposed into both the X and Y pollution inputs. So as the output, we will generate this OEM mode. So this is the all fiber approach of the OEM generation based on the directional coupling. But if you cascade this kind of devices together, then you can realize this all fiber OEM multiplexing and demultiplexing. So here shows some experimental results you can see here. So we can do the 3 OEM modes, multiplexer and demultiplexer. And here shows fabricated devices. All of them are all fiber devices. For example, the fiber OEM coupler, OEM generator, multiplexer, and demultiplexer. And actually, for this structured light, in addition to the OEM modes, actually we have different kinds of special modes, such as linearly polarized modes in the weakly guiding fiber, and also the vector modes with especially variant polarization distribution, and also this kind of circularly polarized OEM modes and linearly polarized OEM modes. So in future, like heterogeneous optical networks, actually people may employ different kinds of like special modes at the network, at different sub-networks. So at the network nodes, it is highly desired to intelligently recognize different kinds of modes used, so that you can choose the proper like demultiplexer. So in this like work, actually we develop a deep learning based like model recognition. So we can intelligently recognize different kinds of special modes using the optical neural network. And with all of these like basic concepts and the devices and technologies to generate, detect, and multiplex and demultiplex the different like structured light, then it is possible to develop the optical communications applications. The first one is the free space scenario. So for the optical communications, actually similar to the wavelength division multiplexing technology, as you can see here. So this is a milestone in the optical communications. For the wavelength domain, actually we have multiple wavelengths, and each two of the wavelengths are orthogonal to each other. That's why we can develop this wavelength division multiplexing. So then it is a similar story for this like OEM degree of freedom. So in principle, we have infinite number of OEM modes, and any two OEM modes actually are orthogonal to each other. So very similar to this wavelength degree of freedom. That's why we can also use this OEM degree of freedom for communications. Actually, there are two approaches you can apply to realize the communications. The first one is the modulation. We can use the different OEM modes to represent different data signal, which is kind of like orbit OEM shift key, like the advanced modulation formats. And the other way is the multiplexing. We can use different OEM modes as independent data channels, so we can multiplex different data channels to increase the transmission capacity. So here shows the first example of the modulation communications. Instead of using OEM beam here we use like BCL beam. It's also kind of like special mode basis, and also it is kind of like abstraction free. So we can employ different BCL beams, and we transmit, we switch it when we switch the BCL beams when in the link. So this kind of time varying BCL beams actually can be used to encode and the information. So at the end, we can actually detect these BCL beams to realize the BCL beam modulation communications. We can also use this kind of like vector modes here. So actually you can see here. So we can use different like vector modes to decode the information. So we can decode this lunar image, and we transmit in free space as the receiver. We can do the decoding, so then we can recover the information. And for the multiplexing, actually, here shows one example. So we have multiple OEM beams. Each OEM beam can carry a different data information, so we can multiply them together to increase the transmission capacity. And in particular, the OEM degree of freedom actually is fully compatible with all existing like degrees of freedom, such as the wavelengths, the polarization, and also the complex amplitude. So that means we can probably incorporate the OEM multiplexing technique together with all the existing mutual like techniques, such as, for example, so this is kind of a multi-dimensional multiplexing communications. So we have multiple OEM modes here. For each OEM mode, we have two polarization. For each polarization, actually, we have multiple wavelength channels, and for each wavelength channel, we have advanced modulation formats. So in this way, so when we transmit like OFDM 8-QAM signals over more than 300 WDM channels covering the whole C plus L band, and with like per max 26 OEM modes, that means in total we are able to transmit more than one transmission capacity together simultaneously with more than 100 bits per second per hertz spectral efficiency. So here shows the experimental results you can see here. So here shows the memory of the channels, the spectrum, the B curves, and also the entire spectrum. And the previous experiment actually was done in the lab condition. So the transmission distance is kind of like short, is less than 10 meters. And if you want to further extend the transmission distance, we actually also did the outdoor free space communications. So you can see here, more than 100 meters free space OEM communications. Here shows that they are immense. And in addition to this, like OEM communications, for this structure light, actually, you can also flexibly shape, tailor the phase front as a transmitter, so that actually you can probably control the trajectory of the beam. So you can use also to realize this kind of bendable like communications, which is kind of line like communications. So it kind of like an abstraction array. You can do some setting, even the trajectory can be broken, and can be actually multiple receivers. So all of this actually based on the flexible like phase front tailing as the transmitter, which is also kind of structured communications. The fiber actually, as we all know, the traditional single mode fiber actually does not support the OEM mode. So in 2013, Professor Rapchandra designed this kind of fiber, which also has a indexed contrast. So this kind of fiber actually can lift off the degeneracy of the modes. So we can see here in traditional weakly mode, actually all these actually they are overlapped together, but for this kind of new fiber, actually they are separated. So because of this separation, actually they are able to transmit OEM modes with low crosstalk. Probably you can realize OEM multiplexing without the multiple input, multiple output digital signal processing technique. So this is kind of memory-free OEM multiplexing transmission. And we also design some kind of like recall fiber in this experiment. So we realized the memory-free OEM in 18 kilometers range. And for the fiber communications, if you would like to transmit for ultra long distance, actually you probably need amplification. We also develop some amplification techniques. For example, as you can see here, this is kind of Raman amplification. So this is amplification. So we are able to realize more than 110 kilometers transmission. So you can see here shows the very intensity profile of the 110 kilometers transmission. You can still see a high quality, which shows good like transmission performance. Yeah, just an example of the in the previous experiment, actually we only have a single actually it's around 0.5 dB, as you can see here. And in previous experiments, the fiber loss is around 0.3 dB. So that we with FC company, a Chinese like fiber fabrication company. So we are able to further reduce the loss of this fiber. We can reduce the loss to be around like 0.2 dB per second per kilometer, very close to the conventional single fiber. So in this case, like low using any amplifiers. But we also this kind of like fiber loop need to be compatible with
Jian, can you hear me? We don't have your voice just now. And before that, your voice was blurry. And just no, yeah. Can you hear me?
Yes, I can hear you.
Yeah.
Can you hear me?
Yeah, it is okay just now. You can go on. Okay.
Okay. So in addition to this ring core fiber, actually, we can even use the commercially available multimodal fiber, for example, OM3 or OM4 or OM5. Actually, you can see here, this more than 100 like the OM modes. So if you all these modes as you cannot see anything. So how can we so in this we are to realize the OM model transmission. So in this case, we are still able to realize the OM transmissions. And here shows another example. So all of these fiber-based transmissions is also important to compatible with the existing single fiber. So we also make so that we can easily connect with the single fiber. It's like this is kind of like compatible with the existing single model fiber network. So you can see the kind of results here. And in addition to the OEM modes, so how about some other special modes? Actually, you can even use fiber eigen modes, which is kind of vector modes. So by doing this kind of special design, so this kind of fiber actually can support tons of like vector modes, and all of these modes are also separated from each other. So we can use these vector modes to do the vector modes multiplexing transmission. And here shows another design which is easy to be fabricated, which is kind of like photonic crystal fiber. So it is kind of like silica, but with lots of like circular like holes. So it can this kind of design. And all these modes actually are fully with each other. So you can use this sample to potentially realize this kind of like item or multiplexing transmission without using any kind of like digital signal processing. Underwater conditions. So here shows one example. Like advanced like in these underwater conditions. And can also use different OEM modes because of different users. Then you can do and also you can realize this kind of underwater OEM communication across the water-air interface. To use the OEM to realize this. And also here shows an example about because the water surface actually is and it changes very fast, so you cannot receive the signal. But with this we also develop this kind of like employing the OEM marketing. We put everything inside this box, including we not use the specialized modulator. We actually use the Q-plate. So all of these things are put inside the box to for the transmitter and the receiver. So here shows the BR curves of the transmission link. So how about the chip? So here we show another example about this chip-enabled communications and interconnects using the twistor light. So actually in our lab, actually we use this kind of like 5 femtosecond directly writing like technique to fabricate this kind of 3D waveguide. So as you can see here, so here shows the waveguide structure. Actually, we have this Mach-Zehnder-like interferometer structure, but as the output waveguide is kind of wider, which can support a high order mode. So the input mode actually can be converted to this high order mode with 2 slopes. And at the same time, at the output mode, actually, at the output waveguide, we also fabricated this kind of trench structure. This trench structure actually is eigen mode you can see here. So actually, which is also like 2 slopes, but with one like 45-degree orientation and the other minus 45-degree orientation. And they also show different like refractive index. And after propagation for a suitable like length, as they will introduce pi/2 phase shift. Then at the output you can get this like OEM modes. So here shows the illustration. Here shows the facet image of the fabricated 3D waveguide. Here shows the measure experimental results. So if for the single one, actually you can realize the generation, which kind of like 3D waveguide generation, OEM generation. But if you have this kind of even much more complicated structure here, so we can even do the chip scale OEM multiplexer here, as you can see here. So at the input, so we have 2 single mode fibers in.
Wang Jian, we don't have your voice just now, and the signal is very bad. Professor Ali Teke, I'm sorry for interrupting the session. Can you hear me, Wang? No, if you are hearing me, write please in the chat box. Then I'm sorry for this bad signal connection. I know many people here is waiting for Professor Wang Jian's interesting talk. I promise you we will upload the video of this talk on YouTube. I will ask from Professor Jiang Wang to recording this video again for us. Don't be worried for this issue. And Professor Aliteke, if I don't know, Jiang cannot hear us also.
Yes.
You can ask people if people can have any questions. We can continue with chat box with Jiang Wang.
I think he can't hear us, so we can write a question from the chat platform. But we should wait for him to finish the presentation, I think.
Okay. So people, anybody, do you have any question you can write on the chat box?
Sorry about the connection.
Okay. Yes, we are hearing you.
Professor Wang, are you there?
Yes, sorry about the connection. I don't know why. Yesterday when we tested it works very well, but I don't know what happened today.
Now we are hearing you.
So should I stop now? Because it seems.
Well, actually, we have run out of time. But if you have 5 time to finish the presentation, you can go ahead.
Okay, maybe I can directly shift to the this part. Okay. Let me shift to this page. Okay. So here in this work, actually, we propose and demonstrate the multidimensional entanglement transport through single model fiber. So this is actually a collaboration work with Professor Andrew Ferber's group. So you can see here, to be specific, we demonstrate the transport of multidimensional entangled states down conventional single model fiber by exporting hybrid entangled states. The main process actually can be split into 2 parts. First, and 1 photon of a high dimensional OEM entangled photon pair is converted to a photon with spin angular momentum by spin optical coupling, and so that a hybrid entangled state is generated. Since all subspaces of OEM states of the other photon remain unchanged, so they are accessible by switching the spin optical coupling component. So in this perspective, rather than just 1 2D subspaces of the spin angular momentum or 1 high dimensional space of orbital angular momentum, we realize an infinite number of 2D spaces that can span the high dimensional space, which is so-called multidimensional entangled state. Then the photon with spin angular momentum transport through the single model fiber, while the photon with orbital angular momentum transport in free space. So this let us use the conventional fiber with negligible crosstalk and losses and few and even simple detectors, and opening the potential for multiplexing, thus making the solution practical. And here shows the experiment setup. A continuous wave pump laser here is specially filtered by a pinhole to deliver a Gaussian beam at 10 millimeters long, like a PBKTB crystal, and generating 2 lower frequency photons by means of degenerate type 1 SPDC process. And by this, the signal and either photons actually have the same wavelength of 8-10 nanometer, and also the high horizontal polarization. The residue pump beam is filtered out by a bandpass filter with a center wavelength of 8-10 nanometer and a bandwidth of 10 nanometer. And the 2 correlated photons, signal and either, are specially separated by a 50-50 beam splitter, with the signal photon A interacting with the spin optical coupling optics, for example, a couplet, and for orbital to spin conversion. And subsequently, photon A was coupled into the signal fiber by objective lens to transmit through the filter and coupled out by another objective lens. And the either photon here was emitted to the special light modulator with lenses. And after that, the photon B was emitted again and by a lens and by accumulated and also coupled into the signal fiber, and hence special filtered as well for the detection. And the projective measurements were done by the quarter wave plate along with polarizer for photon A and SM and for photon B. And the photon A encoded with the polarization eigenstates was transmitted through the signal fiber, while photon B encoded with multidimensional OM eigenstates was transported through free space. And last, both photons actually were detected by the single photon detector, and with the output passes synchronized with a coincidence counter. And the mode spectrum of the ATPC state is shown on the top of this figure. And the matrix is also measured by the mode spectrum, spanning on both signal and either photons. And here, this figure actually to characterize the entanglement of the SPDC mode right after the crystal. We perform the state tomography on the SPDC photons, which is a group of projection measurement to get the projection value on different bases. And the constructed density matrix match well the entangled state of L equals to 1 with a fidelity of around 98%. And here shows another result for another topological charge, which is L equals to 2. And after going through the spin orbital conversion and transmitting through 250 kilometers of signal fiber, the hybrid entangled modes actually are verified by the same test we execute to the SPDC mode. What's different is that the right circular polarization photon is actually entangled with a photon carrying positive L value, and a left circular polarized photon is entangled with a photon carrying negative L value. And that explains why the biggest amplitude emerges and at L and B equals to 1 and 2 when photon A is right circular polarized and vice versa. And after going through the spin orbital conversion and transmitting through the signal fiber, the hybrid entangled modes actually are verified by the same test. And what's different here is that the right circular polarization is as you can see here. So the normalized fidelity for L equal to 1 is around 95%, and for the L equal to 2, the normalized fidelity is about 92%. And as for the hybrid entangled mode tomography, the projection measurement of photon A is carried out on a group of polarization basis, and the rest remains the same. And the reconstructed density, as you can see here, and to further characterize the non-local correlations in each hybrid subspace, a violation of the CH-SH Bayer inequality with the two photon system is used. So first, we project photon B onto the states and corresponding to A, V, D, and H polarization states, while we measure the photon coincidence rate as a function of theta B, so which is the relative phase between the two L values in arm B. So as you can see the results here.
Sorry for interruption. We have just run out of time. If you summarize your talk, we will be appreciated.
Okay. So I have only 2 slides left. So as you can see here, so another interesting work I would like to mention here, actually, which also explores the spin orbital coupling. We transmitted the high dimensional hybrid OM states through the ring core fiber. So as you can see here, and here shows the results. And here shows the summary. Actually, the structure light actually in addition to the light wave, actually all electromagnetic waves could be complex and structured, ranging from radio wave and even to the middle infrared wave and infrared wave, visible, even the X-ray and the electron. Now, actually, for the classical optical communications, actually, the future vision is probably the heterogeneous structured communication networks in phase. It's a combination of the free space, underwater, and fiber, and also different frequency light, including the radio and light. So it's the challenge would be the compatibility among different kinds of networks. And for the quantum story, actually the entanglement can also be distributed in both free space, fiber, and even the underwater. And the challenge is how to distribute in the legacy network, the single model, for example, the single model fiber. So our work also gives a potential approach, try to use the spin optical coupling methods to generate the multidimensional entanglement so that the single model fiber transport might be possible. And we can also still transport multidimensional information. I think that's all of my talk. Thank you very much. And sorry for the interconnection issues. So if we have questions, so we can communicate with each other. I'd like to share my talk with you. So if you have further questions, thank you. Thanks, the chair.
Shishiniv, Professor Wang, thank you very much for your nice presentation once again. So we are sorry for the internet connection problem. So we have run out of time, and we can just take one question, and then we can go for the other speaker. Do we have any questions? I think we don't have. So thank you, Professor Wang, again.
Thank you all. Thank you all. Thank you all of them.
Okay, dear audience, we can go to the second speaker of this session. Professor Alexander Furber from the Department of Physics and Astronomy, Macquarie University, Australia. So I'm going to give a brief information about him. Professor Furber received his master's degree in engineering in 1999 and PhD degree in photonics in 2001 from Vienna University of Technology. He then joined the company Femto Laser Production GmbH, where he was responsible for the development of advanced ultra short pulse TISF laser system. In 2004, he returned to academia and moved to Australia to take a position as a research fellow at the University of Sydney to study ultra-fast pulse propagation effects in novel optical fibers. In May 2005, he was awarded an Australian postdoctoral fellowship, which allowed him to establish his own research group at Macquarie University in Sydney. He's currently Associate Professor and Higher Degree Research Director within the Department of Physics and Astronomy in Macquarie University. His main research interests are focused on interaction of femtosecond laser pulse with solid matter for photonic device fabrication and the development of waveguide and fiber laser system, particularly in the mid-infrared spectral region. So his talk is going to be about ultra-compact, actively Q-switched waveguide lasers based on liquid crystal modulators. Professor Furber, if you are ready, we can start your talk.
I'm ready. Thanks for the introduction.
Okay.
And good morning or good evening for everyone. It's evening my time. I hope everyone can hear me well, and I hope you can see my slides.
We can hear you clearly, and we can see the presentation right now.
Okay, perfect, great. So thanks for the invitation to present at your conference. And thanks for the introduction. As I said, my name is Alex Furber from Macquarie University in Sydney, and I'm going to talk about Q-switched waveguide lasers based on liquid crystal modulators. So to set the scene for this talk, I have to go back quite some time, like 10 years ago, where we started to work on waveguide lasers, femtosecond laser written waveguide lasers, in collaboration with the group of Professor Lancaster and Professor Monroe at the University of Adelaide, also here in Australia. And we demonstrated a whole family of waveguide lasers based on a fluoride glass called Z-blend, zirconium fluoride glass, and doped with various rare earth ions, and with femtosecond laser waveguides inscribed. So waveguide laser is a very elegant concept, because what you basically need is a small piece of doped glass. You inscribe an optical waveguide into a block of doped glass. In the most simple case, you butt couple an output coupler and a high reflecting mirror. You pump your laser, and you get something which is extremely compact, waveguide-based, chip-based, and high-efficient laser. So just two examples that we published a long time ago. That was on the left here, you can see this was work in holmium thulium. Here work in thulium around 1.8 micron, and in holmium thulium at 2.1 micron. We demonstrated CW waveguide lasers with high efficiency. So I said those waveguides in chip are inscribed with the femtosecond laser direct write inscription. And the basic idea is that you take a femtosecond laser and you focus your femtosecond laser inside a transparent material, which can be a doped piece of glass, can be an undoped piece of glass for passive devices. So in this case, it's a doped glass for the active waveguide laser. And if you focus your femtosecond laser inside a piece of glass, what you achieve is you can change the refractive index of your glass, and this change of refractive index happens locally. It's highly localized to the focal volume of your femtosecond laser beam. That means when you now move your glass block relative to your laser beam, you put your glass block on a translation stage, you move it around, you can inscribe structures into your glass. So this method is extremely versatile. The concept is almost as easy as taking a paper and drawing on pen. Your paper is a femtosecond laser, your pen is a piece of glass. It means your paper is three-dimensional. You can inscribe three-dimensional structures. And because you can focus your laser down to a spot size of sub-micron, your features are also extremely fine, and you have very high resolution with this technique. So I wanted to start first briefly introduce the techniques, but also not familiar with the femtosecond laser inscription technique. Because what we do is we take a femtosecond laser, which is typically a titanium sapphire laser, which emits laser beams with wavelengths of about 800 nanometers, so in the near infrared, red near infrared spectral region, and we focus it into a block of glass. And the glass is a transparent dielectric. It's a transparent dielectric means it transmits visible light, and transmits visible light because it has a very large band gap. And a photon at 800 nanometers has a relatively low photon energy. So you think, how can a femtosecond laser with such photon energy interact at all with the glass? Because there is no absorption of the laser energy in the glass. So there's an interaction comes from the nonlinear absorption. And nonlinear absorption that's schematically shown here, for example, multiphoton absorption, also tunnel ionization, that relies on the very high intensity of the short femtosecond laser pulse and also the high intensity in the focal volume. Therefore, we can avoid linear absorption at the surface, and we can really deposit the energy inside the material. Okay, so briefly, how does it work? Well, you focus your beam into your transparent dielectric. Transparent dielectric has a filled valence band. There's no electrons in the conduction band. But through the strong electric field ionization processes, which is multiphoton ionization, tunnel ionization, you create now electrons in the conduction band, and those electrons can be amplified with impact or avalanche ionization. So there's a large number of electrons is generated by the laser then in the conduction band, and in the second step, those electrons transfer their energy to the lattice via electron-phonon collision. So where the energy deposition into the electronic subsistence happens on the time scale of the femtosecond laser pulse, so 50 to 100 femtoseconds, depending on what inscription laser you use. The transfer of energy to the lattice happens on a picosecond time scale typically. So the next step is then now once the laser energy has been transferred to the lattice, what does the refractive index change? Right? And there are many unknowns, and this really depends on the material. Whereas the first two steps were quite universal for all transparent materials, the actual change in refractive index highly depends on the material used, as I will show you for the case of Zeblen, and it highly also depends on the process parameters. If you use, for example, lasers with megahertz repetition rates versus similar laser with kilohertz repetition rates, you get very different modifications in the same glass. Structural changes in the glass matrix are most of the times involved, as I will also show you. It means we change bonds in our glass matrix, but very often we also induce atomic species migration through the laser. Ion migration plays also an important role in the formation of those waveguides. So I get the glass that we use is Zeblen, which is zirconium fluoride glass. I'm mainly interested in this glass because it has a very high transparency. So in my group, we are very interested in developing sources for the mid-infrared, mainly fiber-based sources. So we're also working a lot on mid-infrared fiber lasers, which are also based on Zeblen fibers. The typical silica glass becomes opaque at wavelengths of about 2 micron. Zeblen glass is transparent out to about 4 micron. And the also advantage of Zeblen, the fluoride glass, is that it can be doped to fairly high concentration with rare earth ions. For example, terbium for emission of about 1 micron, thulium for emission of about 1.8 micron, or holmium for emission of about 2 micron, also 3 micron. So this glass inscribes waveguides with our femtosecond laser. That's kind of a textbook example of how we can inscribe waveguides in a glass, as is shown here. With this technique, you can inscribe perfectly symmetric round structures. So in the top row, you see waveguides viewed from the top, and the bottom row is waveguides viewed end on. And you can see you can write waveguides which are perfectly round, and you can tailor the diameter of your waveguide with your inscription speed and energy of your inscription beam. So that's really great. Only problem is that the refractive index, when you look at the bottom picture, so this is illuminated from the back. It's a microscope image of the waveguide illuminated from the back. And those waveguides, you see them not bright, but it's in dark. And this is because the refractive index change is actually negative. So what the laser does is it uses a permanent refractive index change, which is in the order of about -2 × 10⁻⁻3. So it's a negative index change. So why is it a negative index change? As I said, so it comes to the glass. Zeblen is a very complex glass. It contains different glass forming atoms, ions, zirconium, fluorine, barium, for example. And we wanted to analyze what happens in the glass matrix after irradiation with the femtosecond laser beam. And what we've done is, so here we see a bright field image of the waveguide, again, dark in the center, indicating the negative index change. And here is shown a refractive index profile image that we took with a refractive index profilometer that also shows that we have here this central core with negative refractive index surrounded by the bulk material. And we've looked at the Raman spectrum of the glass. The Raman spectrum is unmodified glass compared to the Raman spectrum across the waveguide. And the Raman spectrum is of a glass like Zeblen is a sum of peaks that come from all those various bonds within the glass matrix. But what we have seen is that when we deconvolute the Raman spectrum, so that's the total Raman spectrum here, we can deconvolute it and we can look for very small changes in the Raman spectrum. And we found that several peaks changing, mainly peak 6 shown here, which corresponds to so-called single bridging fluorine bonds, and peak 2, which would be this peak here, which is a signature of double bridging fluorine bonds decreases. So from this, you can deduce that actually what happens after femtosecond laser irradiation is that some of those double bridging bonds get cut, and you have an increase in single bridging bonds compared to the double bridging bonds. The single bridging bonds are physically longer than double bridging bonds. This leads to a decrease of the local intensity of the material, and a decrease in the density of the material corresponds then also to the decrease in the refractive index of the material. So we have a negative refractive index change. It's not a waveguide as such. How can we use this now to inscribe a waveguide? Well, what we can do is we can write an array of those waveguides, and we arrange them around an unmodified core, and we get this so-called depressed cladding waveguide. It's shown here for 6 cylinders, where we have, this would be our core. So we guide light in an unmodified core. The dark rings, this is where the glass is modified. This is our actual negative refractive index waveguide. We can write more cylinders to get the core more symmetric. We can write several rings of those cylinders to get thicker claddings. Right? So you have really high flexibility in how you shape your waveguide. But the big advantage of this technique is that we can shape the waveguide more or less arbitrarily, and we guide light in an unmodified region of the glass, which means that there's also no danger that we can actually photo anneal the inscribed waveguide. So this will be refractive index profile here. You see in the core, we have the bulk refractive index, and what we inscribe with the femtosecond laser is the depressed cladding around the core. And depending on how thick the cladding is, you can get very low losses for this waveguide. And the big advantage now is that it's shown here. So we can have the waveguide with several rings, we can have a very large core. Those waveguides support multiple modes, and those waveguides, depressed cladding waveguides, are inherently lossy. It supports lossy modes, so that all those modes that are supported by the core are inherently lossy. But the thicker the cladding is, the smaller the losses. So that's shown here, example for a specific wavelength. This is for 1.8 micron. It's shown that when we have a diffractive index change of about 1.5 times 10 to the power of -3, the fundamental mode has losses that decrease if you make our cladding thicker. So if you make your cladding thick enough, you can get the losses down. But what's the beauty of this waveguide structure is that the higher order modes that are also supported by this structure. So the higher order modes, because they physically extend wider and they are more leaky into the actual bulk material, all those higher order modes have even higher losses. And so we can discriminate the fundamental modes from the higher order modes. And if you use this as a laser, although the structure supports higher order modes, it actually will always laser in a fundamental mode. So this supports very large fundamental modes in a waveguide laser geometry. It means that we can have a laser with a waveguide laser, which has a relatively large mode field area, which would be ideally suited for pulsed operation of the laser. In pulsed operations, we want to achieve very high peak power in order to reduce the damage threshold, to not go over the damage threshold of the material. We want to keep the area, the mode field diameter, large enough so that we keep the intensity below the damage intensity. So that brings me to the actual main topic of my talk, that we transform this laser into Q-switch laser. Why do we want pulsed lasers? Or just a few examples here. Well, if you get enough pulse energy, you can actually start to use your small chip laser to induce ablation. In medical applications, for example, you remove skin cancers. By manufacturing, you can make markings in transparent material such as glass if you have high enough peak power. Again, laser-induced breakdown spectroscopy, or also particle velocimetry be another application for pulsed lasers. So how do you pulse a laser? The Q-switch lasers either have passively Q-switch lasers, or we have actively Q-switch lasers. Passively Q-switch lasers typically have federal absorbers incorporated inside the laser cavity. With a passive Q-switched laser, the repetition rate depends on the dynamic interplay between the gain and the saturation properties of the saturable absorber. So repetition rate is typically quite high, and therefore the maximum pulse energy is limited, and moreover, we cannot control the pulse energy. If you want to control your repetition rate and achieve a low repetition rate but high pulse energy, you typically employ active Q-switches for a Q-switch laser, and mainly electro-optic modulators or acousto-optic modulators. Both of these are fairly bulky optical elements. Electro-optic modulators typically need high voltage power supplies. Acousto-optic modulators typically need very large radio frequency power. So those Q switches are therefore not really compatible with a small waveguide chip. We want to keep a small compact platform. We don't want to integrate a really large active Q switch into our cavity. And that's why we started then to work with a company called ZLF, which is an Australian startup company that has patented technology to produce liquid crystal-based transducers in the context of distributed sensing networks, actually. So what they've done is they've come up with this device here, a very small device, which contains a liquid crystal, which I will show on the next slide. And the application here is that you apply an electric signal. The electric signal changes the polarization of light that comes in here, coupled with an optical fiber. And in combination with polarizer, the electric signal changes the reflected light reflected off this transducer, and therefore we can translate the electric signal that's applied here, typically comes from a sensor, for example, in a mine, into an optical signal. So therefore, talking about mines, in mines, you want to avoid electric cabling, so all the distributed sensors that typically give you an electric signal. The signal can be translated in an optical signal, and the optical signal then can be transmitted throughout your sensor system. Now, our idea was to take this transducer and so see if this can be also used as a Q switch in a waveguide laser. So we wanted to build a monolithic and miniaturized laser cavity. Our goal was to have a cavity length still chip-sized, so a few centimeters long, very low weight. You want to tune the rep rate from below 1 kilohertz, ideally to several hundred kilohertz. And we tried, our goal was to have pulse durations in only a few nanoseconds and very high peak power. So the goal was definitely to have peak powers more than about 1 kilowatts in a small and compact platform. So how does this liquid crystal look like? On the liquid crystal is within substrates of the glass substrate, and we have two ITO layers, which are the electrodes, the transparent electrodes. And we have very small so-called alignment layers, ST1 alignment layers, and we have a very thin liquid crystal layer in between. So for example, several micrometers thick, typically 5 to 9 micrometers thick. And this is a so-called deformed ferroelectric liquid crystal mixture. By the presence of electric fields, the molecular arrangement of this ferroelectric liquid crystals is deformed, and you change the helical shape of those molecules, and this leads to change in polarization of the incoming light. So if you have light coming in, then if you change the voltage between the ITO layers, you can change the polarization of the light coming in, and in combination with the beam splitter, you can control how much light is reflected back to the direction of where the incoming laser beam is, and the reflected back in the orthogonal polarization state. This was used in a transducer setup where the feather left was focused on having high linearity to translate an electric signal into an optical signal. We investigated this in the context of a Q switch laser, where we're not interested at all in linearity, but we want to achieve a high modulation depth. But in a Q switch laser, you want to achieve very high loss modulations. Basically, you want to adjust the liquid crystal such that you have 90-degree polarization rotation, so that your laser is completely blocked, that your internal cavity losses are 100% ideally. So you can build up very high gain. And once the gain has built up to maximum value, you want to switch your losses down to 0 to release all the gain that was stored in the active medium as giant Q switch laser pulse. So we've investigated this here, and we saw that with this liquid crystal, with the optimized liquid crystal structure, we can get a modulation depth of about 95% with applied voltage of only plus minus 8 volts, so 18 volts. And so this was at low frequencies, and if we increase the frequency of the modulation signal, we can see that these liquid crystals can be controlled with voltage of up to almost megahertz, and at a megahertz we still get about 6% modulation. So it's extremely fast liquid crystals. Those liquid crystals typically not thought of fast switches in a laser because they're typically slow, but those ferroelectric helical liquid crystals can be switched with very high switching frequencies. If you apply higher voltage, it's shown here with 60 volts peak, so plus minus 30 volts, we can achieve modulation depth of 100%. So you can really switch from 0 losses to 100% losses up to very high frequencies. So we can up to about 200 kilohertz, we still almost have 100% rapid modulation depth. And at 1 megahertz, we still get fairly decent modulation depth. So that's the laser that we've built. So we have here a waveguide. In this case, it's terbium doped for operation 1 micron. We coat one facet with a dichroic mirror layer. which has a cutoff at 1 micron. It's high reflective at 1 micron at the wavelength of the laser. We pump it externally from a pump diode at 976 nanometer. And then we collimate the light on the other end, chip, so that we have an anti-reflex coating on our other side of the chip, collect the light with a small lens, have a polarizer here, and then here our liquid crystal modulator. So that's a schematic here, and this is the setup shown here. So the whole device is quite compact. We'll later show that it can be even more compact, but this device is about 10 centimeters wide. And we've shown that it looks beautiful. It's Q-switch laser, as you would expect. You can lower the repetition rate. As you lower the repetition rate, your pulse peak power goes up and your pulse duration goes down, as Q-switching, active Q-switching theory predicts. You can get short pulses, get very high peak power. Average output power goes slightly down as we reduce the repetition rate, but the pulse energy goes up. So with this prototype, we had pulse energies, peak powers in excess of 100, 120 watts, using a liquid crystal device, which was straight from the company as a transducer, which was not modified at all in the context of a laser. We've optimized then the liquid crystal transducer and have incorporated the liquid crystal layer directly onto our chip without needing to collimate the light coming out of our chip. So have a real small laser, which is not just basically the chip. We have here the light coming in from a pump fiber. This is our waveguide chip with the waveguide inscribed. And on the other side here, we have the liquid crystal layer directly onto our chip. And with this optimized setup, we can now, we achieved pulse peak powers with almost 3 kilowatts at 1 kilohertz. So it's shown here, applied voltage peak to peak about 100 volts. So the highest voltage to achieve with a high modulation depth. Pumped with about 400 milliwatts of pump, 300 milliwatts is absorbed. Our pulse width is between 5 and 6 nanoseconds, fairly low average output powers, but high peak powers and high pulse energy in this laser. I want to show now finally that, so this was all in ytterbium, but the same idea can be used in different active waveguides. So the ytterbium emission at 1 micron. We said, let's test the same setup in an ytterbium in the thulium context. Thulium emits at about 2 microns, so 1.9. So again, back from the fully monolithic setup to a setup where we have the liquid crystal cell, the output coupler, and the polarizer as discrete elements, and we collect the light that's coming out of the waveguide and pumping here from the pump diodes into our waveguide. This waveguide is either, let's say, terbium or thulium waveguide. It means the laser diode is either laser diode at 790 nanometers or at 980 nanometers, depending on the medium. And that's shown here. So comparably with ytterbium, you get typically higher power. So it's similar pump powers. We get average powers which are double in ytterbium than in thulium. We get higher slope efficiencies, mainly due to the higher losses in the liquid crystal layer at the 2 micron, and being operated at lower frequency in the thulium. So it's 2 micron. The advantage of 2 micron is that we can then use nonlinear Jacobian fibers, which transmit at 2 micron, does not transmit at 1 micron for frequency broadening. So we have a setup where we have then launched a 2 micron light into a nonlinear fiber, optical frequency broadening. And we have seen that with the peak power that we have at the moment, 2 micron, 160 watts, we can broaden the spectrum of the initially very narrow band light, 1.88 microns, out to about 60 nanometers. And simulations show that if we increase the pulse width again to kilowatts, we can achieve almost a super continuum wide spectrum out of this really small chip laser. Work to be continued. Okay, so it brings me to the end of my talk. I acknowledge funding agencies. So a lot of our funding comes from the US Air Force of Scientific Research and from the Office of Naval Research, and also from the Australian National Fabrication Facility. So ZLF and LabTech are 2 of our industrial partners in this project, and that university support come from Macquarie University. It's my university, and strong collaborations with the University of New South Wales, which is also in Sydney, in Australia. And thanks for your attention, and if we have time, I'm happy to take questions.
Thank you very much, Professor Furber. And also, I would like to thank for your attention for the time. Okay, we can take the question right now. If you have a question, please raise it. We are having the question from the YouTube as well, I think. Is there any question? Okay, I think we don't have any question, Professor Furbe. Thank you very much for your presentation and a nice talk again.
Thank you.
Thank you, Alex. Thank you.
That's my video. Thank you. Thank you, everyone.
Professor Bowen, just a second. We would like to introduce firstly, and then you can start your presentation, please. Do you hear me?
Yeah, I hear you.
Okay then. Thank you. Okay, we come to the last speaker of this session. He's Professor Warwick Bowen from Australian Institute for Bioengineering and Nanotechnology, the University of Queensland in Australia. So I'm going to give a brief information about him. He's recognized both nationally and internationally for research at the interface of nanotechnology and quantum science, including nanophotonics, nanomechanics, quantum optomechanics, and photonics quantum sensing. He's an Australian featured fellow. He leads the quantum optics laboratory at the University of Queensland. He's director of the University of Queensland Precision Sensing Initiative and is both program and node manager of Australian Centre for Engineering Quantum Systems. The research in Professor Bowen's lab spans from the very fundamental, for example, how does quantum physics transition into our everyday world at large scales, to the applied, for example, developing next generation sensors for medical diagnostics and navigation. To pursue this research, his lab works in close partnership with industry and use state-of-the-art facilities for nanofabrication, nanoanalysis, precision optical measurements, and deep cryogenic refrigeration available in-house or on campus at University of Queensland. Professor Bowen has supervised more than 30 postgraduate students who have been recognized with prizes such as Fulbright Scholarship, an Australian Youth Science Ambassadorship, a Springer PhD Thesis Prize, the Queensland nomination for the Australian Institute of Physics Bragg Medal, the Australian Optical Society Postgraduate Student Prize, and the University of Queensland Graduate of the Year. He regularly has projects available both for postgraduate students and for also postdoctoral researchers. So his talk will be about today, absolute quantum advantage in biological imaging. Professor Bowen, if you are ready, we welcome to start your speech, please.
Thank you very much, Ali, for that very flattering introduction. Very much appreciated, and very much appreciated the opportunity to talk today to you and tell you a bit about the work we do in my lab. I would really love to actually be there with you rather than being stuck here, but this is the world we live in right now. I did feel like I would make you all a little bit jealous and show you a picture of a turtle. So I'm currently I'm giving you this talk from an island, Heron Island, which is a University of Queensland research station. And I literally just got back from snorkeling and seeing turtles, which was wonderful. But that's not the topic of this talk. The topic of this talk is applying quantum light in microscopy. I should acknowledge the people who really do the work. So this was the main goal of Kachira Casasio's PhD project. And then there were a whole bunch of other people involved, particularly Alex Terrison, who's another PhD student, and Lars Madsen, who's a postdoc who's working on the project. The work was conducted in the Australian Centre for Engineered Quantum Systems, and was funded primarily by the US Air Force Office of Scientific Research. So deeply appreciative to them for that support. So basically, let me see if I can change the slides. So basically the idea of this area of research in my lab has been to take concepts and techniques from gravitational wave physics, where you're wanting to use lasers to measure exquisitely precise, exquisitely small signals from masses in space, and apply them into microscopy. So take the same techniques and see if we can measure exquisitely small signals that come out of biological systems. My lab does a bunch of other work, and I wanted to just briefly mention that. So we have a whole lot of research in superfluid physics, where we use light and combine that with silicon chips and nanotechnology to control superfluid helium. So we've demonstrated things like laser cooling of a liquid using superfluid helium and tracking of quantized vortices. And the ultimate idea is that if we can learn how to control quantum fluids on a chip, we can build quantum technologies out of them, such as very precise inertial sensors. The second area that we work in my lab is phononics. So this is about learning how to control the flow of acoustic waves on a chip. And there we're working with industry partners, including Lockheed Martin, to build computer circuits out of mechanical acoustic waves that we could put in a satellite and have intrinsically robust to radiation, to ionizing radiation. And then we have a whole stream of research on quantum optomechanics, which is about understanding the fundamentals of quantum physics. How large can you make a quantum superposition of a massive system? And also about technologies. How do you build technologies for quantum communication and computation applications and sensing? I don't have time to talk about any of that work today, but very happy to answer questions about it or tell you about it some other time. So the main topic for today is a new result that we have that is analogous in some way to Google's result from 2019 showing quantum supremacy or absolute quantum advantage in computing. So the idea here is to show absolute quantum advantage in quantum sensing. So show that quantum sensing can give you absolute performance better than could ever be possible with classical sensing. And here I'm showing you a page out of the UK Quantum Technologies Roadmap, where they identify microscopes. So we're particularly interested in biological microscopes that can see things that would not be possible to see using conventional technologies. And they've identified these sorts of microscopes as one of their 2 decadal plan milestones for quantum enhanced imaging for their UK roadmap. Okay, so why is it that quantum may offer advantages in microscopy? Well, the reason for that is it really comes down to the laser. When the laser was introduced in the 60s, it was very rapidly turned to microscopy. And what has happened since then is this rapid increase in the capabilities of microscopes, which is driven by the increase of intensity you can get from lasers. And that allows you to see smaller systems, to break the diffraction limit, and to get exquisitely selective images of specific properties within biological systems. So you can understand this sort of push to higher intensity, at least if you're a quantum optics person, from just the simple idea that there is shot noise on light. So that means that any measurement you make with light, because it's made of photons, is going to have some noise, and in order to boost your signal above that noise, you need to use a lot of photons. And so what I'm showing you here is a plot of the intensity of some light field and the signal to noise of some measurement. And the idea here is that the signal to noise is growing linearly, is growing as square root of the number of photons or square root of the intensity. If you don't have anything fancy about the light, if it's just a nice low noise laser beam. And And so you'd think, okay, I just keep turning the intensity up and I get more signal to noise, and that's great, end of story. But of course, that's not something you can keep doing indefinitely. At some point, the sample you're looking at starts to become damaged. And that turns out to occur for intensities on the order of a watt per micron squared. You start, in those sorts of intensity ranges, you start to see these things like changes in bioactivity. So you can generate free radicals, so chemical reactions introduced by light that alter the environment of a biological system. And eventually at very high intensities, you can boil the very water that makes up the medium in the cell, and you could ablate a cell. So you just can't keep pushing the intensity up indefinitely. And that sets an upper bound on signal to noise, which of course will depend very much on the sample you're wanting to look at and the kind of damage you're willing to accept. But there is some fundamental limit beyond which you're not going to be able to go. And the idea is that if you use quantum correlations, you can control the shot noise on light, you can push it down, and that allows you to increase the signal to noise at a given intensity, and then push into signal to noises beyond the fundamental capabilities of a regular microscope, and therefore see objects or structures that you just couldn't see with a regular microscope. Okay, so that's the idea. You may, if you have familiarity with quantum optics, then you might be familiar with parametric down conversion. The idea here is you have a nonlinear crystal, you pump it with some light, and then it creates pairs of photons at half the wavelength, which are correlated and you can use for quantum sensing. So most quantum sensing experiments have been done with these sorts of systems. These sorts of, with light, have been done with correlated pairs of photons. Here are a couple of examples where you can reduce the noise below the shot noise level using these sorts of systems. And here's another example where the same sort of source is used for imaging. The catch with these sorts of experiments is they lie at very, very, very low light intensities. So similar intensities to the intensity of the moon at the Earth. So these are intensities for which only some very, very specialized systems would be affected by. Most biological systems would be very happy to operate in that sort of level of intensity. So one needs to push up to higher intensities to reach regimes which are A, relevant to biological microscopes, intensities, the kind of intensity that are used in microscopes, and B, where you couldn't just turn up intensity to get better signal to noise. So to do that, what's traditionally been done is that you put one of those nonlinear crystals in an optical cavity. So this is the nonlinear crystal here, and there's two mirrors that form a cavity. And then if you pump that crystal both with the pump light and with a seed at half the wavelength, at twice the wavelength, at half the frequency, then you can use that to generate bright quantum states of light rather than these photon pairs. And the way that works is if you think about an optical field, then you can plot it on a phasor diagram. It has some amplitude, which I'm just calling A here. And it turns out the Heisenberg uncertainty principle says it has to have some fundamental uncertainty on the end of that phasor. And the idea is that you can use one of these, it's called an optical parametric amplifier. Oh, I should say, and that means that any measurement you make with that light is going to have intensity noise that has to be greater than or equal to square root of the number of photons that are detected. So the idea for getting beyond that limit for bright light, so the stick means the light is bright, you can put a lot of photons into it. And now if I use the same nonlinear crystal, I can de-amplify the stick, and that also de-amplifies the noise on the amplitude of the light and allows me to get a noise floor beneath what would otherwise be a fundamental limit, beneath the shot noise floor. And means you can operate at much higher intensities. So these are the sort of intensities people operate at. So around the intensity of a laser pointer, and up to, with gravitational waves, intensities of about a milliwatt per micron squared. And so that, as I said, these sorts of light are used routinely now in gravitational wave detectors, and they've been applied into biology. And in my lab in the last 5 or 6 years, so we showed that you could make biological measurements with relative performance better than classical techniques using this quantum squeezing, these squeeze states of light. But again, if you're serious about really pushing the absolute performance limits, you have to go up in intensity until you get to the point where you start to affect the system you're looking at. And if you look at the best microscopes, they use nonlinear processes within biology. So they're 2-photon or 3-photon microscopes typically, to get this beautiful selectivity and sensitivity to particular signals within components of a cell. And in this case, because they're using a 2-photon or a 3-photon effect, they need really very high intensities to make sure there are enough photons there to get the effect going. The cross section for the processes is very short, is very small. So they're working really right at this limit. They're always balancing their photon budget. How much signal can I get without destroying the sample I'm looking at? There are many of these sorts of microscopes. So here are some examples. And the key thing is that they, instead of using continuous wave light, such as the light used in the gravitational wave detector, they use pulsed sources of light. And so in our lab, we've spent a few years, those pulse light sources of light sit up here at these sorts of intensities where you start having to worry about ablation, about free radical generation, about all sorts of issues cropping up in biological systems. So in my lab, we've spent the last few years developing a source of quantum correlated pulsed light. It's based on the same sort of idea as other squeeze light sources, but because it's pulsed light, it's very high intensity, you don't need a cavity. That simplifies the problem. So what I'm showing you here is we have a laser. We've got a 532 nanometer laser, which is a pump. This is the nonlinear crystal here. And we have a 1 micron laser. That's the seed, which ends up being de-amplified in this crystal and comes out squeezed. So in principle, this is quite simple. And in practice, it's a little tricky because one of the big advantages of using a cavity is that it defines only one spatial mode of light that interacts, and therefore you only get this quantum correlation on one very well-known spatial mode of light. Removing that cavity, you don't get that benefit anymore. And that adds some complications, but without going through the details, we were able to deal with those complications and produce squeezed light of very, very high intensity. Okay, so we've got the squeezed light. We can start to apply it into microscopy. There are many different types of microscopy we could demonstrate. The one we chose to look at is called stimulated Raman scattering. So Raman scattering microscopy is a very powerful technique. It tells you about the concentration of molecules with particular vibrational bonds in a biological sample. So you can use it to probe the chemistry of a biological system. And most Raman microscopes use spontaneous Raman scattering. They have a pump, and that pump then scatters light of a Stokes frequency that's lower, Stokes light, by the Raman, the frequency of the vibrational bond that you're probing. And then by looking at the amount of scattered light, you can learn how much of that particular vibrational bond is in your sample. But recently, people have been developing stimulated Raman microscopes, and they've been doing this because it gives them better signal to noise than a spontaneous Raman microscope. And the way that works is you have both a pump and you insert a field at the Stokes frequency. And then what the pump does is it amplifies that Stokes field. So it provides gain for it, and you measure that gain. And the way you measure the gain is a really nice trick to do this, and that is that if you modulate the pump, then you modulate the gain, and you can see sidebands appearing on the Stokes field that would otherwise not exist, only if there is that particular chemical bond you're trying to probe present in the biological sample. So that's what we do. This is the full setup for our experiments. This is the squeezed light source I showed you before. Then we tap off some of the pump for that squeezed light source, and we use it as the input to an optical parametric oscillator that generates our pump field. So this squeezed red field at 1 micron is our Stokes field, and then we generate a pump at 800 nanometers. We modulate that so that we can modulate the gain of the stimulated Raman process, and then put both into a microscope, dump the pump, and detect the Stokes. And we look for a modulation at the frequency of this modulation of the pump. And this is what we see. No, this is not what we see. In order to validate the microscope, we image a particular bond in polystyrene. So this is a polystyrene bead, and we're interested in the aromatic stretch bond, which is this stretching you can see with the green arrows here. And when we tune our lasers to that bond, we see a peak, which tells us the concentration of that particular bond in our sample. But the key point I'd like you to get out of this is the peak tells you the signal size. Because we're using quantum correlations, we can push the noise floor down beneath the usual shot noise on the measurement. So we can get a relative signal to noise, so a signal to noise at a fixed intensity that is better than the signal to noise you could get with the best system with no quantum correlated light. But what's interesting is what happens as we turn the laser power up. As we turn the laser power up, so I'm turning the laser power up on the horizontal axis, and I'm measuring the signal to noise, both the classical signal to noise, the signal to noise with shot noise limited light, and the quantum signal to noise. And you can see at any particular power, the quantum signal to noise is higher because the noise floor is lower. And both of the signal to noises increase quadratically as I increase the pump power. That's what I expect for this particular nonlinear process. But they only do that up to a particular point. They do that up to about 26 milliwatts of pump power. Above that, we start to see a divergence away from this expected signal to noise, and eventually a severe collapse in the signal to noise. This is because our polystyrene bead is being damaged by the pump. And if you could set any line here you like as being the amount of damage you want to avoid, but if we set that line at where the signal starts to diverge from expectations, and you say I don't want any change in the signal to noise due to the intensity there due to damage, then you can see that at that we're showing an absolute advantage, an absolute improvement in signal to noise here compared to what you could possibly do using shot noise limited light. So this is, as far as I'm aware, the first demonstration of the use of entanglement to absolutely improve signal to noise in any optical measurement. Okay, so just to convince you that there is indeed damage going on, this is some images of beads. This is an image of a bead before we've made any measurement, and this is images of beads after they've been damaged. And you can see some of them are completely destroyed. This one's been basically evaporated. This one's been mainly evaporated. Some of them are melted, like this one and this one and this one. And some of them are ablated. This one, you can see a slight ablation. Here it's much more obvious, where you've ablated you've just drilled out some part of the bead, and down here as well. And this fact that the damage is sort of balanced, there's many different types of damage going on at the same time, that tells you that our microscope is actually very well optimized to minimize damage, because all the different types of damage depend differently on the repetition rate of the the light source and the pulse width. And so you want to balance them so that all the damage sort of hits at the same time. And we've done that here so that you can get the maximum intensity before any damage occurs. Okay, so we've applied this microscope into biological samples. This is an example of 2 yeast cells. With a particular intensity, what we find is that over time, those yeast cells are damaged by the light. So you can see this damage appearing due to the laser field. So this tells us that there is a really strict limit on how much light in this microscope you can put on the sample and be able to look at it and have it not damaged. If we turn the laser power down, then we can evade that noise, that damage, and we can start to take images. So here's an example of an image of a cell that we've taken with shot noise limited light. And you can see some features in here, and this is clearly an image. If we use quantum correlations, this is the equivalent image we get. I'll flick back and forth between them a couple of times. So what you should observe is the contrast is really very much better. It's 35% better on the quantum enhanced image. So it's a crisper image. You can clearly see these blobs. They're lipid particles. So they are fatty particles that exist inside yeast cells, and the particular Raman shift we're looking at here is chosen to target those particles. So we see these bright patches which indicate that in those regions there's a lot of lipid. Then this sort of broad background is the cytosol. It's just the fluid inside the cell. And then you can see here what might be part of the cell wall. The other thing you can see in this image is that it has pretty good resolution. So it has resolution of about 200 nanometers. That's sub-diffraction limited, which is what you expect because this is a nonlinear microscope. I hope that this sort of convinces you that really you can get much crisper images if you use quantum correlations. I wanted to briefly acknowledge 2 other works that came out that were submitted about the same time as ours, which show the same sort of quantum enhancement, but only for spectroscopy, not for imaging. And they use much lower intensities than we do, so they don't see the damage that we see. So they don't see this absolute advantage in microscopy, which I think is I think personally, a really nice result. Okay, so that's the main result I wanted to talk to you about today. I'm not sure how much time I've got left. You
have just a few minutes left, Professor Bowen.
Okay, so I'll briefly just tell you about one other result that we've got this year, which I think is quite nice, and that's not using quantum correlations, using instead just shot noise limited light, and using it to track particles very precisely, and from that learn about the medium that the particle's in. So basically what we're doing is we're tracking the Brownian motion of a particle using an optical tweezer. So we've got a laser field, we've got a particle trapped in it, and the scattering of light off the particle tells us the position of the particle. But what's different about our experiment than almost all previous optical tweezers is our optical tweezer is so precise that we're able to track the velocity, the instantaneous velocity of particles. So instead of getting a random hopping that you normally get with Brownian motion, we see a smooth curve, a smooth trajectory of the particle moving around. And that's something that Einstein thought was impossible. It was first demonstrated by Mark Raisin and his team at University of Texas a few years ago. But we've used this now because we realized that instantaneous velocity immediately tells you kinetic energy, and kinetic energy is directly connected to viscosity. So the viscosity of a medium is how fast energy is dissipated. And it's something that's quite hard to measure by other techniques. But if you get into this ballistic regime where you can track the velocity of particles, you can essentially immediately determine viscosity. We use this to make measurements of viscosity at timescales of about 20 microseconds, which is around 4 orders of magnitude better than had previously been done. So basically taking viscosity measurements from second timescales to microsecond timescales. And we think this is going to be broadly useful for understanding the fast dynamics of out of equilibrium biological systems and out of equilibrium systems in general. I won't say much about that, but I'll probably finish and just thank you for your time and your attention and take any questions.
Okay, thank you so much, Professor Bowen. If you have any question, please write on the chat. Okay, I don't see any question, Professor Bowen. Thank you very much again.
Pleasure.
You're welcome and have a nice day.
You too. Enjoy the rest of the conference.
Thank you very much.
Thank you, Professor Bowen.
Thank you very much, Dr. Bowen. And thank you, Mr. Ali Hocam. Thank you for your valuable contribution to our conference. Thank you.
Pleasure.
Thank you. Goodbye.
The meeting point of the roads between Europe, Asia and Africa, and a perfect interweave of cultures, Ankara, a culture paradise of 5,000 years. These lands, which hosted many Western and Eastern civilizations, became the center of the Turkish War of Liberation, launched with the downfall of the Ottoman Empire, and became the capital of the Republic of Turkey. You can find the opportunity of treading the path of history by visiting the year-round open museums and open-air museums in Ankara, which serve as a bridge between past and present, remaining intact, defying thousands of years. There are many historical and modern mosques in Ankara. The roof of Hacı Bayram Mosque was built in such a way as to embrace the wall of the Temple of Augustus, as if to prove the centuries-old coexistence of religions in fraternity. You should never depart from Ankara without seeing the traditional Ankara houses. Ankara is also one of the most important stops on the historical Silk Road. The inns, caravansarais, and traditional bazaars of that period provide a safe transport, easy access, and a wealth of purchasing opportunities. Historically important Turkish baths and spas are the health and tourism sources of Ankara. Ankara is also a university city boasting 5 big state and 10 private universities. Ankara is also a city of art, life, and entertainment. The state opera and ballet performances, the plays staged by the state and private theaters, the concerts by the Presidential Symphony Orchestra, as well as national and international festivals keep its people occupied for a whole year. Seymens, the swashbuckling heroes and traditional dancers from central Anatolia, may show up in all corners of Ankara. All institutions and organizations complying with Atatürk's motto, sound mind, sound body, have spearheaded the construction of many sport halls in Ankara. Ankara also draws attention with its parks and recreation areas. It is located at the heart of many of Turkey's tourism riches. Ankara is the easiest city in terms of transport. Ankara is also easily accessible by air, land, and rail from any country in the world. The Turkish cuisine is one of the world's most famous cuisines. The Ankara specialties constitute the select examples of Turkey's culinary marvels. Ankara is the homeland of the Ankara goat, the source of clothes vying with silk for quality, the Ankara rabbit, whose wool is as light as Angora wool, the world-renowned Ankara cat, and the flower of love, also dubbed the flower of the prophet. Its shopkeepers, the carriers of a tradition of 1,000 years ago known as Ahilik, the Guild of Turkish Craftsmen, are sincere and hospitable. They are generous, alms givers, and like guests, with their tables open for everyone. They are, in short, humanists. Ankara, of which Atatürk voluntarily became a fellow townsman, is a monument of peace, with its cultural foundation and a center of tolerance. With its history and natural riches, eating culture and tourism, agriculture and animal husbandry, its politics, sports people, art, and its residents is a leader capital breathing life into Turkey. A culture of paradise of 5,000 years. Ankara, the heart of Turkey.
Hello, everybody, again. Professor Ramazan Koch, can you hear me? Yeah. The chair of the second session is Professor Ramazan Koch from Optics and Acoustical Engineering, Gaziantep University, Gaziantep, Turkey. Can you hear me, Professor Ramazan Koch? Yes, we have your screen, but please open it. Yeah, okay, okay. I would like to give the stage to Professor Ramazan Koch. Sure. Thank you. Hi. So, hi, Sai, Professor Chormay.
Hello.
Okay, go on.
Okay. Hi, everybody, and thank you for your joining. I am Ramazan Koch from Gaziantep University, Department of Optical and Acoustical Engineering. I will be sharing this meeting today. Now, I would like to welcome all participants and attendants. Thursday's second season about the light and light-based technology. Now, we have 5 speakers there, and we have limited time. Therefore, it is better to begin our task. First speaker is Professor Chormay from Okinawa Institute of Science and Technology, Graduate University from Japan. And I would like to inform, I would like to give information about her before she begins to his talk. She recited her basic science in experimental and mathematical physics from the St. Patrick's College, National University of Ireland, and a master degree search about the electron-hydrogen collision, again from the same university, same college from the Ireland, and her PhD in physics, Stern-Gerlach atomic informality of hydrogen from the University of Paris, North France, and she had a lot of papers about the optics, physics, especially quantum optics, and she has several awards and designations. I would like to give some of them. President Award for top undergraduate student in science, and the Europe Science Bursary, Lisa Mentor Fellowship, Science Foundation, Ireland Principal Investigator Award. You can find details from his, from her webpage, and I advise to join her webpage and to check her papers. And as I said before, we have limited time. For the sake of effective use of time, if Professor, if you are ready, then we can start.
Yeah. Can you hear me?
Yes.
And you see my screen?
Okay.
Yeah. Okay. So thank you very much for the kind introduction, and thank you for giving me the opportunity to talk about some of my work today. So I'm Sheila Nick Kermick. I'm from Ireland and I'm living in Japan, in Okinawa. So just to give some of you an idea of where Okinawa is, if we consider this is Europe and here's Turkey, and this is what most of you consider to be Japan. Okinawa is an island chain between the mainland of Japan and Taiwan. So we're located here. on a very small island. So it's about five kilometers wide. I can walk from one coast to the other quite easily. And the university was established 10 years ago, so we'll be celebrating our 10th anniversary in November. And we're a university, a very small university. We only offer a PhD program to international and Japanese students. Everything is through English and it's funded through the Japanese government. And we're currently accepting for the 2022 entry. And also for anybody older than a student, every year we typically recruit somewhere around 10 new faculty. So we're an expanding university, quite quickly expanding. And we also, for younger people, so undergraduate students and master's students, we have research internship program. And for PhD students, we have a visiting research student program. So details of these are through the graduate school or through any university of interest, in any research group of interest. And here's a picture of our university. So this is our laboratory building. This is the national flower, the hibiscus. And this is the East China Sea, which is a coral reef just down from the university. So as you can see, it's a very nice, calm environment in which to do research. So my group is quite large and we cover quite a number of topics. So one of the primary things we work with are cold atoms, because my own background originally is atomic physics. And with cold atoms, we look at very small numbers of atoms, so maybe about 10 to 100 atoms typically within any system. And we look at them through these systems called optical nanofibers. So I'll introduce the optical nanofiber during this talk. We also look at light to manipulate matter. So this links into some of what Warwick Bowen was speaking about just earlier. And we look at optical tweezers and trapping light in confined geometries. So some of these geometries are also what I'll talk about today. So these are called whispering gallery mode geometries. And finally, we look at light as a sensing platform. And these can be quite varied depending on the application. So the university is quite unique in that we don't have departments. So if a student has an idea of research and effectively they need to use light to that research, it's quite possible they'll end up being supervised by me. So for example, we have looked at plastic distribution within the ocean. We have done some neuronal imaging on brains deep within the brain of mice. And then we do some more standard type of environmental monitoring, such as pressure and temperature, using either these whispering gallery resonators or some other types of cavities. So I said I'm going to focus today on manipulating matter, and I'm going to focus on, first of all, simply using an optical nanofiber and the light fields that we get from the optical nanofiber. And then I'll talk about what we can do if we start working with a microbubble. So it'll be largely particle trapping in different size regimes using one or other of these devices. So I'll start to introduce the ultra-thin optical fiber. This, also known as a nanofiber, has many, many names, or sometimes people even use the term optical wire. I'll give the two applications. One is particle trapping and manipulation, so as an alternative to optical tweezers and various things that we can do with regards to the optical fiber confined light. And then the second application I look at is using these ultra-thin optical fibers as couplers for whispering gallery resonators. And then I'll give some examples as well of experiments that we do with particle manipulation inside these whispering gallery resonators. So the first thing, the crucial thing to understand is the ultra-thin optical fiber. So I think there are about maybe 20 researchers in my group, and most of them in some way have to work with ultra-thin optical fibers. So what are they? If we think of a normal optical fiber, very, very simple system, we have a core and a cladding material, and there's a small refractive index difference between the core and the cladding. And if we're thinking of a ray optics picture, we say that light propagates through the core due to total internal reflection at the boundary between the core and the cladding. And in reality, we end up with some very minor leakage of light in the forms of an evanescent field from the core to the cladding. But because of the refractive index profile between these two materials, the leakage is very small. So they're optimized to make sure that almost all the light is confined within the core. And depending on the size of the fiber, so the sort of the ratio between this core and the cladding, we can propagate different modes through the fiber. And typically we talk in terms of single mode fiber, where we have the fundamental mode propagating, and this has a Gaussian type profile. So most of the light energy is confined really in the center of the core region. But we can also have few mode fiber or multi-mode fiber, where we can start playing with the linearly polarized modes or the true modes of the fiber. So these are effectively can be viewed as the different profile patterns that are able to propagate within the fiber. Which modes will propagate? I mentioned it was a function of the size of the fiber, but it also will depend on the wavelength and the actual refractive indices of the materials we use. So if we look at a normal single mode fiber, typically they're 125 micron in diameter, and the core will be about 5 to 9 micron in diameter. And the refractive indices between the cladding and the core for a silica fiber, typically the core is slightly larger than the cladding, very small difference. And this leads to what we call the weakly guiding regime. So almost all the light is confined very well within the core. And we can use certain approximations with regards to describing the light propagation. And these are these linearly polarized, or the LP modes. So if I want to think of how the light is, and I imagine just here, this MATLAB is indicating the core. So the grid here indicates the core, and most of my energy is confined within the core if I have single mode guiding. So for the nanofiber, or the ultra thin optical fiber, what we have is a region of the fiber which gets down to less than a micron in diameter. So if we start off here with normal part of fiber in the pigtails, and then we reduce that diameter using an exponential profile down to several hundreds of nanometers, maybe up as far as 1 micron, this is what we call the ultra-thin optical fiber. So then if we consider a single mode scenario where we have the fundamental mode propagating, when it reaches this tapered region, the modes start coupling from the core into the cladding material. And then as we taper down further and further to the nanofiber waist, we end up with light extending into the surrounding environment. So this is not a loss, and that's what's really crucial. This is an evanescent field which has an exponential decay from the surface, but the light is still confined within the fiber. So if we look at having an interaction with our light, we can bring a particle close to this ultra-thin region. There will be some form of interaction, but the light will still be guided by the fiber, and we can still detect it at the other side of the waveguide. So at this the uptaper for the pigtail, if we can assume that they're symmetric, we aim to start typically with a transmission of somewhere around 99%. So these are very, very lossless. Of course, they degrade over time, but 99% is a good starting point for these fibers. So what's actually happening to the fiber as we're making this region thinner and thinner? So here we have a normal fiber, here we're getting a fiber that's thinner and thinner, and here we have a region where the core has become so thin we can ignore it, and now the cladding material starts acting as the core, and the environment, whether that's air or water, starts acting like the cladding. So if we think of the refractive indices in this region, we now have a much bigger difference. So the core is now that of silica, 1.444, and depending on whether it's air or water around it, we have a large difference between these values. And what that means for light propagating is we end up with a very large evanescent field. So in the original scenario, if I consider my wavelength of light to be sort of similar to the size of my fiber, most of my light will be confined within the fiber itself. As I make the fiber diameter smaller and smaller, I'm getting more and more light leaking out into the environment. And then when I have a situation where the waveguide is less than half the wavelength of light propagating through it, I can have massive evanescent field lobes, and most of the energy is outside. So in the work that I'm going to talk today, sometimes we use very high power and we just use a very small evanescent field. Sometimes we go to very small fibers and we use a very low power, but we still get a very high evanescent field because we've entered this scenario. So one of the advantages is the one I've talked about. I can bring something close to the fiber and it can interact with my light field. The other advantage is that I'm effectively focusing light down to a very tight confinement here. So this evanescent field is exponentially decaying. So we typically say that a few hundred nanometers from the fiber surface that the field becomes negligible. But this region here itself is a few millimeters long. So if I compare a very tightly focused free space beam, I will end up with a limitation over where it's very tightly focused due to the Rayleigh range. Whereas for my ultra-thin fiber, it can be viewed as very, very tightly focused, and this will extend over a few millimeters. So if I'm looking at having some type of interaction, again, I now have a very long region for that interaction. And the other thing is, because it can be viewed as very tightly focused light, we've entered the non-paraxial regime for light propagation. So the normal scenario where we consider paraxial light, this is no longer valid for light in these optical fibers. And this leads to some very interesting effects on the light itself. So how are they made? We use a heat rig. So we have a hydrogen-oxygen flame. We scan that hydrogen-oxygen flame along the optical fiber. You can just see the optical fiber in the video here. And at the same time, we pull the fiber using translation stages. So this process for a single mode fiber takes maybe a minute, maybe less. And as I said, in the ideal case, we'll end up with a transmission of greater than 99%. So when we've done this process and we have a very thin waste of the fiber due to this hot flame melting or causing a molten state of the glass, we end up with something like this. So this is an optical nanofiber. The bright spots are indicating a very dirty optical nanofiber, so it's going to be a very lossy one. So this one we wouldn't work with, okay? But it's just good for imaging because you can see how much loss you can have as soon as a single dust particle lands on it. So we try to keep them as clean as possible and as dust-free as possible in order to do our experiments. Now, if we think of the size of these, this would be single mode fiber. This would be a typical red blood cell, about 5 micron, human hair, maybe about 50 micron, and then a 2 micron tapered fiber. And this is from the Bath group. So they're relatively easy to make. They're cheap to make. They're quick to make. So that's great. Essentially, any laboratory can make these fibers. Because of the way the light is confined in them, you can look at nonlinear effects in the fiber itself. So some groups focus on that, just working with the fiber and looking at very 2-photon, 3-photon phenomena and so on. Their light is tightly confined, but the fiber is still very flexible. So it's surprisingly flexible despite its tiny size. And we can also just connect it to other fibers. So at either end of the nanofiber, we just have a normal pigtail. So we can just connect that onto a laser or a detector. And this means that overall our system is very low loss. So let's think about the light propagating through the fiber. So these are the fiber modes that we can have. So LP01, as I said, is similar to a Gaussian. LP11 is the next order of modes that we can have. It's a group of modes consisting of several. It's actually containing 4 real modes. And these are the 2 that we focus on. So if we wanted to go higher, more exciting patterns, we'd have to have bigger fibers and our evanescent field would decrease. So in order to have a balance between good evanescent field and control over our mode, we focus on, first of all, the LP01. That's what we use for most of our work. So fundamental mode fiber. And occasionally we work with this higher order mode fiber. So this can be interesting if we want to look at anything concerning orbital angular momentum, for example. The way we choose the mode is depending on the size of the fiber that we make. So if we go very small, it's going to be the LP01. Slightly larger, these modes will propagate as well as the LP01. And what are these fibers used for? Well, the number of areas is huge. Okay, so they can be used for optomechanics. They're so tiny that the photon momentum, as light is passing through, you can almost observe the photon momentum and you can try to do photon momentum studies. They're used for nonlinear optics, as I said, because you reach these really high field intensities within this tiny volume of material. They're used as optical sensors. You can cover them with materials such as graphene and you can increase the range of sensitivity that you can have. They're used as resonators, so you can tie them in knots and create ring cavities. You can do some additional processing on them and using, for example, a focused ion beam or a femtosecond laser, and you can create fiber Bragg gratings or Fabry-Perot type cavities. They're also used for cold atom experiments. You can do a lot of chiral activities. You can trap atoms using them. So many different topics. So what I'll talk about is this particle manipulation using them, and also as couplers into other cavity devices. So evanescent field coupling here. So first of all, let's look at the particle trapping and manipulation. So we're all familiar with the optical tweezers. I think these are 1 micron polystyrene beads. And this was a video done by one of my postdocs. The optical tweezers won Nobel Prize in 2018. So you use very tightly focused light. And in this case, it's just being scanned around in this pattern so quickly before the particles can escape. So it's just the focus is moving, tracing out this pattern, and the particles don't have enough time to get untrapped before it returns to its same place. So we're all very familiar with this concept of optical tweezers. But with the nanofiber, it's slightly different. So this is an example of a nanofiber, or it'll be about 1 micron probably in size. In this case, we're again using 1 micron polystyrene particles. They're in a solution of heavy water, and we're shining 1064 nanometer light through the fiber in a single direction. The light passes through, and we just have a momentum transfer from the light that pushes particles along the fiber. But similar to the optical tweezers, we have a gradient force from the evanescent field that pulls the particles in towards the fiber. So effectively, we trap the particles along, or just maybe 20 nanometers from the surface of the fiber, and then they get pushed along by the light momentum. So these are the two things that we exploit in our particle manipulation. So if we just have use the optical gradient force to bring those particles through, you can see that we have a lot of light scattering. So we don't really have a control on the number of particles. So what we typically will do is first we'll take an optical tweezers, capture a single particle, bring it into the fiber, let the light then move the particle. And that way we have a control over the number of particles, and we can control this sort of scattering effect on the particles. So the advantages, we can play with this light intensity very rapidly. We need very low powers. So an optical tweezer, you need a reasonable power to do your experiments. Here we can work with very low powers. I mentioned that we work with a single particle. We can actually work with many particles. So we can do chains of particles. We can look at the dynamics of these particles and the different scattering effects and different absorption, depending on the particle's position relative to the light source. We can do 3D trapping. So when we play with the polarization of our light beam, we can see some of these polarization effects. And this actually allows us to study some of the light features in this non-paraxial regime. So the one I'm going to show you today is related to spin angular momentum, or the polarization of the light, but we also have some transverse components of light that we can work with, and we're also studying them. So the very first experiment that I'll introduce to you is optical binding, and the theory for this was done with Helmut Ritsch in Innsbruck. So in this case, here's our optical fiber, and here are our polystyrene beads. In this case, they're 3 microns, so bigger than in the previous videos. What we do is we take an optical tweezers, trap the particles, and then bring them towards the fiber, turn off the optical tweezers, release the particles, and then turn on the propagation light through the fiber. Okay, so when we have the optical tweezers, the particles are evenly distributed. This again is the time sharing of our optical tweezers beam. We turn off the optical tweezers, the particles create their own pattern, and this is due to the light scattering and the effects of optical binding along the fiber. So if we look at the video, this is a video of about 7 particles, 6 particles, and we can see that the particles will form this chain, and relative to the light source, the separation between neighboring particles increases. So near the light source, we have a large separation. Further from the light source, we have a small separation. The movement of the fiber is just essentially the student moving the camera in an unsteady way. So what we looked at was this formation. If we pulled one particle out, they would reassemble themselves and create another chain that we can predict the forces with theory. And we see that, in fact, this is actually a stable configuration. So we can predict what sort of configuration we will have depending on the number of particles. And we also saw that the speed of these chains can be increased compared to the speed of a single particle. And the speed increase is happening due to the scattering of the light, essentially. So if the first particle near the light source is scattering light, that's then also influencing the subsequent particles. So we have sort of some form of enhancement effect. The maximum number of particles we're able to do this with was 7, and that's purely because of the optical tweezers here. The student found it very difficult to capture more than 7 particles in a linear chain and be able to keep them just when they released them next to the nanofiber. So 7 was the limit we hit here. So the next experiment we looked at then, that was just a fundamental mode. So a certain type of mode propagating the fiber, just the Gaussian or the fundamental. We then looked at what happens if we use a higher order mode. So the higher order mode generally means that we're going to have more extension of the evanescent field into the environment. So we would expect more of the light energy to be going into the environment. So if I play the videos, these were done at the same rate. You can see that with the higher order mode, the particle is moving extremely quickly compared to the fundamental mode. In fact, we've seen an 8 times increase in the propulsion speed of the particle. So this is purely, again, related to the nature of the higher order mode. More of the energy is confined outside the fiber, whereas for the fundamental mode, more of the light energy is confined within the fiber. We then decided, okay, let's start, instead of just working on the linear momentum of light, let's start working on the polarization of light. So the first thing we started looking at is the spin angular momentum. And this is work that's still ongoing. So our theoretical collaborators with this are Mish Petrov and Ivan Toftel in ITMO, and also Van der Kien here in OIST. So if we think of light, we generally think of it in terms of either its orbital angular momentum or its spin angular momentum. And the orbital angular momentum, we had a very nice talk on it earlier, just unfortunately the sound was a bit not really working for listening to it, but we were able to see a lot of the nice transfer of orbital angular momentum that they were doing. So in the orbital angular momentum case, you have this inclination of wavefronts, and you have this spiraling or Fuseli effect of the wavefronts. And spin is linked to the rotation of the electric field. So it's effectively the polarization of the light. And when we think of orbital angular momentum or spin angular momentum as 2 different concepts of light, we're thinking in terms of the paraxial light. When we go down to the non-paraxial scheme, we cannot separate out the orbital and spin. So they're completely coupled together. And this means that the traditional sort of pointing picture of light, we have to change the way of thinking. So this happens in either a dispersive isotropic medium and for non-paraxial light, but also for us, it happens within the optical nanofiber. So the spin angular momentum and orbital angular momentum are no longer independent components. This also will happen for structured light in free space. And again, this was referred to earlier in the first talk that we had today. And we're not worried about structured light. So we're only focusing at the moment on the spin angular momentum and the coupling of the spin angular momentum to orbital behavior. So eventually we would like to also look at the orbital angular momentum behavior and see the reverse coupling. But for now, we just focus on the spin angular momentum. So in order to be able to control the spin angular momentum of light, what we need to be able to do is to control the polarization of light within these optical nanofibers. And this proved extremely challenging until our group in 2019, and at the same time published, I think in the same journal, another group in Paris came up with methods of controlling the polarization of light. So not just estimating the polarization, but really having some form of control of the polarization. And once you have control of the polarization, you know exactly what you're working with, and then you can see how this polarization information can transfer into the orbital motion of some particles. So this is the experimental setup. So it's very similar to the last experiment, but here I'm just going to show a schematic. So we have our optical fiber, and it's immersed in some water in which we have a very non-concentrated solution of particles. Again, these are 3-micron polystyrene particles. We have beams going from both directions. So this is to stop the linear momentum of the particles. We only want to observe now the polarization, the circular polarization behavior on the particles. So by having beams going in both directions, we're effectively going to stop the particle and only the rotational behavior will become evident. This is one example. You can see the particle slightly moves along on the fiber. This just to some imbalance in the two beams. We don't have a perfect standing wave. We have some imbalance and there's some ellipticity within our polarization. And you can start to see that the particle is clearly rotating around the fiber. And this is from playing with the polarization here on one of the beams. We can change the amount of power in the beams. This one, we have a better balance between our left and right. And as we change the power, we can see that the frequency of rotation is increasing. So we can monitor this and determine what the frequency is. And you can see that when the particle goes behind, we will not see as much light. When the particle comes to the front, we start seeing a lot of scattered light. And just looking at this scattered light, we can determine the orbit frequency. So here are the sort of signals we get. This is for a 3 micron particle and a 700 nanometer fiber. So we really have a small fiber compared to the wavelength of light at 1064. And we see in front of the fiber, we have very high signal for scattering. Behind the fiber, we have a low signal of scattering. And we can also see that the orbital frequency is proportional to the polarization of the couplet light. So in other words, we can change the polarization, right or left circularly polarized. We can change the direction in which the light is, or the particle is rotating around the fiber. The other thing that we can see is this sort of behavior. So you can imagine that two particles get pulled in towards the fiber due to the gradient force. And then they come together and they literally start dancing together around the fiber. So this is a really nice example of optical binding. We can see the particles coming in from opposite directions. And as soon as they start to interact, they go completely in sync and start rotating around the fiber in sync. And again, this is a combination of the light in the fiber and the polarization of the light in the fiber, plus the influence of the scattered light from one particle on the other. Now, what we're currently looking at is these are simply polystyrene spheres. What we're now looking at is anisotropic particles. So in other words, we're using liquid crystals, and then we can really see an enhancement of some other features that become apparent in here. The anisotropy contributes to some of these rotational behaviors, and we can start to distinguish different directions, whether it's a transverse spin effect and so on. So this is the current work, and hopefully the paper will be coming out quite soon. The second application I'll talk to you about these nanofibers is as a coupler into a much larger system. So these are whispering gallery resonators. So whispering gallery resonator is a spherical geometry or a circular geometry cavity where light propagates in what's called a whispering gallery. And the name for these resonators comes from St. Paul's Cathedral, where you have this whispering gallery dome. Also, there are examples of this all around the world. So for example, I've been to this one in China, the Temple of Heaven, where the wall here around it is a whispering gallery. So the types of whispering galleries that we work with are typically microspheres or microbubbles. Microbubbles are hollow. The example shown here is it's closed at one end. So if you put something in there, it's not going to flow, it's just going to stay in there. However, these can also have an opening at both ends, and we can flow particles or fluids through them. And this is the sort of work that I'm going to talk about. So where does the nanofiber play a role? If you look at this picture of the microbubble, you can see the nanofiber here coupling light in to the whispering gallery mode. So the light, as you can imagine, coming along here, then gets coupled into the cavity and does this whispering gallery orbit around the cavity. The size of these microspheres, typically somewhere between about 50 to 120 micron. What are these used for? Well, they're used a lot in sensing. They're used a lot in nonlinear optics. These microspheres can be made from silica. They can be made from an active glass materials such as Zeblan. We just had a talk on Zeblan materials also earlier today. So they can be made from literally any glass or even from various polymers. For us, if we're working with these micro bubbles, they're just made from silica. So we take a silica capillary and we make these bubbles. Examples of where they're used is in biosensing. So here we have a laser coupled into one of these very thin optical fibers. This is a solid cavity here, so similar to these microspheres on the tip of a normal fiber. So light is going in here, gets coupled in, orbits around, and then gets coupled out, and you can detect any shift in the frequency of the light. So the light, typically you need to have a tunable laser so that you can tune to the cavity resonance here. And in these examples, you functionalize the outside of the cavity with these blue things in order to functionalize. And then this, once they're functionalized, and certain analyte or certain material can be attracted towards it. When it gets attracted towards it, the size of the cavity effectively increases. So therefore, the resonance will shift. So the sort of thing you expect is without any analyte present, you have a certain resonance. When an analyte is present, that resonance will shift. And from this resonance shift, you can determine things such as the concentration of the analyte or maybe the size of a particle that deposits on the sphere. So these are the typical signals that people look for, a frequency shift of the resonance for the cavity. So how do we make these cavities? So I said we're working with hollow ones, and we start off with a microcapillary. And in this microcapillary, we flow air through it while heating it using a CO2 laser from both sides. So the CO2 laser causes the glass to become soft. The air causes the glass to blow up like a bubble, and we end up with these little cavities, micro bubbles, micro bottles, depending on the shape that we choose. And as I said, we can either have it closed off at one end, or we can have it so that we can keep flowing fluids through here. So I just have a video, I think it's playing nicely. This is just some optics, don't worry about it, but here you can see the cavity being created. This is a closed cavity where we only have the bubble with no exit. So why are these bubbles interesting? Well, these bubbles also contain optical modes. So when we couple the light in, I said we have these whispering galleries, but these galleries themselves, these modes, have certain structure. And if we create a wall that is extremely thin, we can have a higher order mode, which is largely carrying the energy inside the cavity, so that any fluid inside the cavity is going to interact with my optical mode. So when we make these, we aim at having a very, very thin wall. So this is just an example here of a broken bubble. And it's just done like this for SEM imaging. And when we break it, we then just grind it very gently to try to get some form of smooth surface. And then we put it in the SEM and measure the thickness of the walls. And we have submicron thicknesses. And this means that the mode can't be contained in the material of the wall. It actually relies on the fluid inside. There are alternatives to our design, so we tend to stick with one single cavity, but it's possible to make multiple cavities along the capillaries. So Misha Semetsky has made several cavities along, and you can have different size cavities which would interact with different wavelength lasers, for example, and these could be used for sensing different materials. You imagine you have 3 different materials flowing through here, and each cavity could be tuned to detect a single material. And in sensing work, for example, these have a quality factor or indicate how lossy they are. So very high quality factor. We've got ones as high as 10 to the 8 at 780 nanometer. So extremely low loss in the cavities. And we've measured pressure sensitivity of about 38 gigahertz per bar. The distribution of the mode, this indicates the inside of, this is indicating the outside. So if the wall is very thick, most of the mode is contained within the wall. I make the wall very thin, most of the mode goes into the liquid core. And this is the regime I'm interested in, where I can have what's called a quasi-droplet regime. So essentially, I will play with making a wall that is very thin, generating this mode in the whispering gallery when I couple light in, and then using it in order to detect whatever material is flowing through the cavity. So these are the first experiments on trapping. So we have one of our cavities, we flow particles through here, and we have the fiber as a coupler. as we can have excitation of the whispering gallery mode. This then acts as a trapping potential for the particles. The particles are fluorescing, so we pump them at 532 nanometers and look at the 630 nanometer emission. And the Q factors in this experiment, so again, empty bubble, 5 by 10 to the 7, so pretty good cavity. We lose about 1 order of magnitude when we fill the bubble with the water solution containing the particles. These are the sort of systems we get. So these are more bottles. We can have, you can see here the particles coming in from the top, and then they enter into the modes. So they get trapped in the whispering gallery modes, and you can start seeing the nature of these whispering gallery modes. So they actually spiral through the bottle, okay? Then they turn around at a caustic, and then they spiral back upwards again. We get very high particle propulsion. So the fastest we've detected is about 40 millimeters per second. It's much faster than what we can really see easily on our camera. So you can just see here where the scattering is, that the particles are trapped there. And we can get particles, multiple particles trapped. So here we can see the particles trapped at a caustic, so one of these turning points of the spiraling mode. And we can see at many other modes within the bubble. So those particles are being propelled along. So obviously, if we don't want the particles to propel, but we want them to be trapped, we need to do counter-propagating modes. So modes going circular direction and counter-clockwise direction within the cavity. So here you can see a particle that's trapped, so it's no longer really moving quickly. Then I turn off one of my beams. So it's actually this one gets turned off, and the particle starts to go through very quickly. So I'll just play that again. The particle here is trapped because I have both beams on. Then I turn off one beam. It's no longer trapped in what space, it's more being pushed around by the whispering gallery mode. So once we have this, we need to think, okay, now we have a way of trapping particles or identifying particles possibly in it. So what are we going to do? So at that point, we started to work with a group of chemists in the US to look at chemical reactions on gold nanorods. So this is the group of Randy Goldsmith in the University of Wisconsin, and this is the principle of the experiment. So we start off with one of our whispering gallery. We flow material through there so that we can have gold nanorods, and you see an example here, deposited on the surface of the cavity inside. We pump using our whispering gallery modes using an optical fiber, and we pump the nanorods using external light. So there are certain things that we can look at. The first is spatial and morphological information of single nanoparticles during photoactivated chemical reactions. So effectively, the dimensions of this nanorod can change depending on the wavelength of light that we use. And the other thing is the control of the nanorod orientation. So this light will exert a torque on the nanorod, and this will create the nanorod to rotate and at some point free itself again from the surface of the cavity. A more detailed schematic of the experiment is here. So the whispering gallery mode is through fiber at 765 and 781 nanometers. We can pump at 3 different wavelengths and we monitor them. So that's just an external pump of the gold nanorods. So what the first thing to do is to identify, can we locate when we have a single nanorod? So here you see an example. This is just after the nanorods have gone through, and this is the thermal imaging of single nanorods on the system. So once we have this level of thermal imaging, we identify a single nanorod, and then we work with that nanorod. And if we think of these nanorods, they can be polarized and they can have plasmon bands. So depending on the orientation of the polarization of the light with respect to the aspect ratio of the nanorod, we can either excite a transverse plasmon band, which I'm going to indicate by green, or a longitudinal plasmon band, which I'm going to indicate by red. So what we do is we identify a single nanorod, and then I locate where these bands are. We have many different pump wavelengths, so they're indicated here, and the blue dashed line is the probe wavelength to see what we actually have. So these are the external pumps, and then the blue is through the nanofiber. Okay, so with these plasmon bands, if our light is oriented along the nanorod, the maximum axis, we'd expect minimum absorbance on the transverse band and maximum absorbance on the linear band. And we determine we get this at a certain angle of 40 degrees. We can then start plotting this polarization as a function of the different wavelengths. So the green is the minimum absorbance, and the red and the dark purple sort of will give us maximum absorbance. When we rotate, we can get the opposite. So we can identify at which polarization we get maximum and minimum absorbance, and we start to identify this type of plot. So for the different colors of probe, we can determine the frequency shift that we get through the nanofiber, and then we can determine the polarization of our system. And of course, we can fill in all other possible orientations of the nanorod as well.
Professor, I'm sorry, you have 5 minutes.
Yeah, I'm nearly finished here. So what we're now looking at is how do we change the aspect ratio of the nanorod using a photo-induced reaction. So using FeCl3, that's the solution in which the nanorods are placed, and using 635 nanometer light, we can change the aspect ratio of the nanorod. So when we do this, and over time, here we're plotting the polarization angle again, so similar to in the previous one, and the amount of signal that we get. So this is from the thermal photo images. So over time, we can see that each of these is a different polarization trace relevant to the aspect ratio changing. And you can see that the maximum polarization angle is slightly shifting. So then if we just plot that, so we're plotting the exposure time and the maximum region of signal and where we get the maximum polarization, we see this decrease. These vertical lines just show we're no longer having the chemical reaction. So at that point, you just need to increase the amount of signal. So you just need to pump it harder. And same here, if we're looking at the maximum angle at which we get our signal, so what is the maximum polarization angle for our signal, we start to see this increase. So these are both signatures that we are indeed driving this chemical reaction in order to change the aspect ratio. So what's actually happening here? So this is a chemical process. So I'm not too familiar with chemistry, but I have had to learn a little bit. In the fabrication of these nanorods, there's a surfactant used in order to prevent the nanorod sticking and to control the shape of the nanorods. And this is called CTAB. And it turns out that when you clean the nanorods and you start to work with them, there's always still some surfactant remaining. When we put this in the FeCl3 solution, the iron congregates on the nanorod and starts to create an interaction. When we shine green light on it, this is a very fast interaction. It starts decreasing, so it starts more or less eating away at the gold material. When we have 635 nanometer light, this is a very slow interaction, but it also will decrease the gold material. So up until now, people have always looked at bulk samples. They have never been able to work on this chemical reaction using a single particle. But for us, we were able to do a single particle analysis. And what it turned out is that this difference between the fast and the slow process on a single particle level is not so great compared to in the bulk particle. So now what the chemists are trying to understand is why a single particle behaves almost identically for the two wavelengths compared to the bulk system. And then the final thing that we looked at was the torque. So this rotation that you can have due to the light. So here's the nanorod. Here's the rotation depending on the plasmon that we're exciting. Here's our pump. And as we vary the polarization of that pump, the nanorod starts to rotate. And with this rotation, we can change our signal. So this is the signal as the nanorod is rotating. When it rotates so that it's aligned perpendicular to the linear polarization, we get our maximum signal. At that point, the torque is so large on the particle, so it's really been forced to align with the polarization or perpendicular to it, that it then releases itself from the material, so it's no longer stuck on the surface, and it stays aligned with the light. So this is really allowed to look at single particle torque from light and how the forces interact here. So the next step then is looking at single molecule behavior. So the single nanorod is quite large, and we now go to single nanorod. Okay, so to summarize and what we work on these ultra-thin optical fibers for particle manipulation. We also have some other designs of fibers that we work with, such as slots within these ultra-thin fibers. I talked a little bit about whispering gallery mode resonators. We have many experiments on nonlinear optics, but I talked about the one tying in with particle manipulation. And now we're looking at functionalization with the colleagues in the US for single particle identification. We have a lot of other projects in the group based on plasmonic structures where we manipulate particles down towards the single protein levels down to around 5 nanometers. And of course, all this work was done by many people. So this is my team. You will see that Turkey is also represented here by Metin. And these are the social media platforms for the group. And of course, we need money, and the money comes from the university and a number of Japanese funding agencies. And one of the students is now funded through an SPIE scholarship. So thank you for your attention.
Thank you so much for this nice talk, Professor Sahil. We can take questions. There are one question from the Cenk Ceylan. Here, his message is, Dear Professor Shormak, hi, very nice presentation. I think so. Some and OAM from light modulation actually natural of source because transmission by nature of coding for transportation best created to output.
So I actually don't understand this question.
I
honestly do not understand. I honestly think this question might be for somebody else. I mean, what is natural source transmission by nature of, I honestly don't understand this. So I saw this question coming up, and this is why I hesitated at one moment in my talk, because I was like, I don't understand this question. I'm sorry. If
we can take questions. Another question?
Professor Koç, if possible, I have a question. Thank you very much, Professor Kormaik, for your very nice presentation.
Thank you.
So the question is that how you can measure the spring constant in the bubble?
Oh, so for if particles are trapped there, yeah, we haven't done any of that type of analysis so far. So the only thing we've done at the moment with regards to the particle trapping in the bubble is with regards to demonstration of particle trapping. We've done it for 500 nanometers and we've done it for 200 nanometers. For the 500 nanometers, we worked with theoreticians in China. Some of them are experimentalists, but the postdoc who worked with us was a theoretician. And the theory was just related to essentially the optical forces and what speed we might get. But it totally failed for the 200 nanometers. The speeds we get for 200 nanometers did not match at all. So I only showed the 500 nanometer experiments because the 200 nanometer were so fast and the theory doesn't match. But for how to measure things like, you know, the normal way of looking at what is the strength of this trap, we haven't figured this out yet. But it's important. But for now, we can't measure any of this sort of behavior. We'd have to have some other type of analysis. At the moment, we're really looking at the scattering from the particle to see how quickly it's rotating. To do anything like spring constant or any of this normal trapping parameters to get how good the trap is, we'd have to think of something else.
Thank you very much, Professor Şile. Which order of magnitude of forces we need for trapping? I know it depends on the nanoparticle size and the type of the nanoparticles, but I would like the order of magnitude of force.
Yeah, so I think the typical order of magnitude is piconewtons. Yeah, it's really tiny forces when we're working with nanoparticles. Yeah, it's very small. But of course, as you said, this depends on, you know, the other parameters too, even what the fluid is, if there's a surfactant present, it'll all depend, but somewhere around piconewtons is typical.
Thank you very much.
Okay, no problem. Thank you.
Thank you very much for this nice talk.
Thank you.
Okay, we can now proceed our second talk. Our second speaker is Dr. Matteo Bassi.
Professor Ramazan Koch, just there is a problem. I am in connection with Professor Matteo Bussi. Matteo, the charge of the laptop of Matteo is shutting down just now. If possible, you introduce what just Matteo in waiting room. You know, if possible, you shortly introduce himself, and then yeah, okay. After the finishing, we can give the extended introduction if possible.
Okay.
But he's in waiting room just now. Please. Okay, join. You can go on, please.
Hi. Okay, Matt, connected now?
Not connect. He's not connect now.
Then he has video.
When he's connected now, Matteo, can you hear us?
There is a problem. There is no voice. There is no his voice. His microphone is not connected. And also video. There is a problem.
Then
oh yes.
Okay, now is okay.
Okay.
Yes, Professor Matteo is here now.
Yeah. Hello, can you hear me?
Professor Matteo, welcome. Hi.
No, thanks. I had a lot of problems, sorry, but probably I can manage.
Are you ready now?
Yeah, it should work. I have to share my screen. Just a moment. Okay, can you hear? Can you see the screen?
Okay.
Okay.
Let me give a brief information about you before your talk.
Yeah, thank you.
Dr. Matteo Bassi joined from Italy. He is an invited speaker. He is a researcher in the Institute of Materials for Electronics and Magnetics, part of the National Research Council in Parma, Italy. His research is now focused on germanium nanowires for sensors, transition metals, the halogenized and gallium oxide for deep UV solar wind detectors. Dr. Matteo Bassi has attended about 20 international conferences with several invited speakers, and he is author of about 100 papers in national peer review. Now, if he is ready, then you can start your talk.
Okay, thank you. As I said, I have some, so I hope everything will be fine. I will talk about our activity about solar blind photoresistors based on gallium oxide polymorph. And this is actually a work done in collaboration with my institute, IMM-CNR, and the University of the Department of Physics and Chemistry. So a brief introduction. I will speak about gallium oxide, its applications. I will give a brief talk about the epitaxial growth methods, and then I speak about the electrical context and how you can use this material to realize photoconductors for solar blind detections. So gallium oxide is a very interesting material that began to be studied as a wideband semiconductor at the beginning of the last decades. It has a high breakdown field and an excellent figure of merit that makes it an excellent candidate for power electronic devices with performance superior to silicon carbide and gallium nitride, with the difference that it can be also realized in a large area substrate with potentially low cost, differently from gallium nitride and silicon carbide. Regarding the application, high power devices are not the only application that you can do with this material. You can also realize solar blind UV detectors thanks to its wide band gap. So these are just a few examples that show that the research of gallium oxide is being pursued with a lot of investment, in particular in Japan for high power devices, and also in the US. And in the last years, also it began to appear the first prototype devices for high power electronics, MOSFET, and so on. But okay, we are in a light-based conference, so I thought to speak about the other potential application of this material, that is the solar blind photodetectors. What are these kind of detectors? Okay, you know that the sun emits a black body solar spectrum with a certain shape. But when the radiation comes to Earth, we have some gases in the atmospheres that absorbs some regions of the solar spectrum. In particular, the ozone layer completely blocks the UVC radiation, so that at the Earth's surface, you don't have any background of UVC light. And in this range of frequency, you don't have background radiation. So if you have a source that emits UVC, like, for example, some chemical reaction of flames, jet engines, or missing plumes, or even the corona discharge made by high voltage appliance, you have a source of an artificial source of UVC light. And if you have a detector that is sensitive only to this to this region, you can easily detect the source of this light. And this has important application, for example, in security, for flame monitoring, or in other application that use UV UV light. And I will come to another application at the end of the talk. A few words about gallium oxide. It is a wideband gas semiconductor that crystallizes in different phases. The most stable, the only stable, is the beta one that has a monoclinic structures. Some drawbacks, such as it's very prone to cleavage. So as far as you have to technologically use it for processing, it is easily broken. And also it has anisotropical properties. Then we have the alpha phase that is metastable and has an even higher band gap than the beta one. And finally, we have the epsilon one that is also metastable, but crystallizes in an orthorhombic lattice and can be easily grown on sapphire, and is more manageable because it has higher crystallographic symmetry. You also can alloy gallium oxide with aluminum or indium oxide to tune the band gap, and so increase or decrease the band gap of your device. And also you can you have different polytypes of aluminum, and you have an additional degree of freedom because you can match different alloys with different polytypes. A brief talk about how you can grow this, this material. There are vapor phase techniques, mainly MOVP, HVP, or mist CVD, or physical techniques like MB or PLD. I will do a brief talk about the vapor phase techniques. In particular, the MOVP, metal organic vapor phase epitaxy, is what we use in our laboratory to realize our films. And you have a carrier gas that can be usually an inert gas, or you can use oxygen or water as precursor, and trimethyl gallium as a gallium source. With HVP, you can usually achieve a very high growth rate. And as for gallium precursor, you usually use a mixture of hydrogen chloride through a liquid gallium boat. Finally, you have a quite different technique, which is called mist CVD, that is very effective in growing this polytype. In this case, you realize, you make a mixture, a liquid gallium precursor, you use gallium acetylacetonate, HCl, and water. And thanks to an ultrasonic generator, that is the one that you use for making moisture, you deliver the mist to your growth chamber. So you have different polytypes, you have different techniques to grow this material. And there are critical parameters, like, for example, the type of precursor, the presence or absence of chlorine, the temperature deposition, that also depends on the deposition techniques. And you can also deposit this material on different substrate. By tuning the growth techniques and the parameter, you can obtain a particular polytypes, that is beta, epsilon, or gallium. And you can have, you have different growth recipes and different growth process for each of these techniques to realize a particular polytype. What we do is we do epitaxy and processing of epsilon gallium polytype, and our growth parameters, our growth techniques is MOVP using water and trimethyl gallium. Epsilon gallium oxide is interesting as a material because it has also a wide band gap, can be deposited on sapphire, and it has also a ferroelectric and piezoelectric properties that you can explore for making two-dimensional electron gases. And you can also apply it in solar blind detectors. So a brief summary about our films. These are our standard growth conditions. We use hydrogen or helium as carrier gas, and we dope our films with silane. The films that we obtain are relatively good quality. We can achieve a wide range of thickness. The films are transparent and with a good surface morphology. The gallium oxide grows by the nucleation of hexagonal island that later expand and coalesce in order to form a continuous film. We characterize our films by X-ray diffraction. The only problem that we had is that the peaks of epsilon gallium oxide and the bulk beta gallium oxide are very near one to the other. So it is difficult to analyze the film using low angle diffraction. But if you go to higher diffraction angles, the difference between epsilon and beta is very evident. So about the electrical context that we do for electrical characterization and realization of devices. Okay, we start from a substrate, we deposit a film, and by sputtering, we deposit a bilayer of tin oxide and ITO. So at the end, we have stripes of our metal contacts that we use for actually a TLM geometry. We did our IV characterization in the dark, and we found out that our best sample, let's say, are up to 10 to 9, 10 to 10 ohm centimeter for the nominally undoped layer. If we illuminate with light, we see an increase of about 100-fold of the current that we measure. So our system is sensitive to light. Let's go a step back to the UVC solar detection, because we are interested in sensing this part, this range of the spectrum, the UVC light. So what we did is to apply a voltage, measure a current, and illuminate with specific light. And okay, in this graph, the difference between the dark current and the current when the sample is illuminated at 265 nanometers is quite evident. We do a step further and we measure the spectral responsivity, that is the electrical output you have at with a given optical input, so for a definitive wavelength at a given frequency. And if you see the responsivity towards the energy, you see that there is a huge difference between the responsivity at the band gap, let's say at 265 nanometers, and the responsivity in the visible range, which is 2.4 electron volt or 500. We have a ratio about four order of magnitude between the UVC responsivity and the visible responsivity. This is a picture of our actual test device. And we also made time-dependent measures. So we illuminate and turn off the light in order to see how reliable and consistent the system is over time. And we found out that we have a good stability, so the signal is very stable, and you can repeat this measurement as many times as you wish. We have a good noise signal-to-noise ratio, and we measure the response time that is in the order of some seconds. And the difference between the sunlight light and UVC light is very evident. So this is a fitting of one of those signals. So we fitted the curve with a double exponential in order to obtain a rise time that is in the order of some seconds, and a decay time that is in the order of less than a second. If we compare these values to a standard, or let's say state-of-the-art beta gallium oxide solar blind detector, we find out that the rise time of our system is quite higher than the state-of-the-art reported in literature, while the decay time is quite similar. We attribute this difference to the fact that our geometry of the contacts is still not optimized. We have a very large metal stripes in the order of the millimeter. And we think that by using photolithography, we can improve this rise time and decay time. We also measure the responsivity at different light intensity, and find out that we have a good correlation between photocurrent and irradiance if you use a log scale. So our device is quite good, and we can start to think to use it for application. And which kind of application are we thinking about? we are thinking about detecting the corona discharge in high voltage appliance or equipments. So first of all, what is the corona effect or corona discharge? If you have a conductor with a potential difference between the plates, it can be that after a certain voltage, you have a discharge because the dielectric is broken, and the conductors become surrounded by a glow that is called corona, and it is actually produced by the ionization of the gas around these conductors. So the corona effect, when you are thinking about high power systems, has detrimental consequences because it produces a voltage drop. It means that you can have interference in communication, and with time, it can also lead to failure. Also, because in this process, it is formed ozone gas because of the ionization of oxygen, and the ozones can damage the system, the conductor, and corrode the equipment. So eventually you will have a failure. So if you remember here in at the earth level, on the ground, we don't have any background UVC light, and high power appliance, when they are close to failure on the week, when they begin to have problems, they emit. They are subjected to the corona discharge, and they emit UVC light. So if you build a detector that can sense this light, you can actually think about a device that will help you to prevent the failure of high voltage applications. So we conclude the talk with this slide. Just a moment. Okay. No. Okay. And in my talk, sorry, I was quite fast because I had some trouble. And so I gave a brief introduction. I talk about the growth of single crystalline layer. And I described how we fabricate and characterize our device that we intend to use for solar blind detections. So if you have or willing to collaborate, you can drop a mail to me or to our group leader, which is Roberto Fornari of the Parma University. And with this, I end my talk. And okay, thank you for your attention. And I hope I have enough battery to reply to your comments or questions. Thanks a lot.
Thank you very much, Dr. Vasi. We can take questions.
Thank you very much,
Thank you, thank you, Suleiman, for inviting me. Nice to see you.
Nice to see you again.
Yeah. Hope to see you again in real life.
Yeah. Thank you very much for contribution.
Thank you.
To our conference, our event. I am happy to see you again.
Yeah.
See you again. Thank you very much.
Thank you.
Meanwhile, I would like to thank Professor Süleyman Özçelik for this nice meeting organization. Now,
thanks, Ramazan Hoca.
If Professor Paransata is ready, is he joined here? Professor Paransata? No, he is not here.
He's here,
Well,
Professor Koch. First, Professor Panigrahi, can you hear
Panigrahi?
me?
Yeah, I can hear you.
Okay.
I can hear you.
Okay, hello.
Hi.
Professor Koch.
Hi,
come
welcome,
on, please.
Professor.
Hi, thank you. Yeah.
Now, we can proceed now, our third talk, third invited talk. First, let me give some information about the Professor Panigrahi. He is from Department of Physical Science, Indian Institute of Science, Education and Research, Calcutta, India. Professor Panigrahi, I am sorry, current research interests lie in the areas of nonlinear dynamics, quantum optics, and the quantum computation, and the large-scale data analysis involving wavelets, transform, and tools of artificial intelligence. He has applied many other tools to physical problems, and in that process, he has shown that an exact equivalence of the interacting algorithm and the model with free oscillation. He is a member of National Academy of Science, Al-Habad, and the Juragat Academy of Science. And his talk is about photon-edit cat state, phase space structure and statistics. Now, if you are ready, you can begin your talk. You have 30 minutes.
Thank you, Professor Koch, for kind words. And I am thankful to the organizers for giving me this chance. So I'll be talking about photon-added cascade. And this work was done with two of my students here, Orman and Gargi. I'll give the reference at the end of the talk. So, cascade has been with us since this famous example given by Schrödinger to illustrate the ambiguity in quantum mechanics, namely collapse of the wave function. So eventually people have produced cascades. For example, starting from 2004 onwards, there are many experimental realizations of cascades. Mathematically, these are very simple structures. In fact, some up to Gaussians, the so-called coherent state, from which cascade is produced, is just a Gaussian, shifted Gaussian function. So mathematically, they're easy to handle. In terms of quadratures and applications, of course, they're very deep. Now, why am I interested in cascade? Because recently, these cascades have come into play in quantum communication and quantum computation. Particularly, you will see the so-called CAD code is an experimentally realized object now. So people can produce cascades. Now you will see cascade is very robust against noise. And particularly if you add, to the cascade, add 2 photons or subtract 2 photons, it will get back to itself. So then the question arises, subtract 2 photons because it's an eigenstate of A square. So if you subtract 2 photons, it will get back to itself. So it is very robust against error. Therefore, then we ask this question that if you add a photon to a cascade, what happens? Very simple question which started our search, and it turns out to be quite non-trivial, because particularly to see experimentally what really happens, we have to go to linear function in the end. That will throw a lot of light on what happens when you added a photon. So very briefly, I'll start with coherent state. And as you know, this photon added coherent state has found experimental realization some years back. And it was, photon added coherent state was studied initially by my former colleague, Professor G.S. Agarwal in University of Hyderabad. So that was one of the motivations which we started to study cascade and what happens if you add to it. So that is how I will go. First, I will show if you add a photon to coherent state, what happens. Now, then this, the phase space and the structure, all those things comes out very nicely through the linear function. You will see there is something called the interference in the phase space, which was originally brought into physics by, around 87, 86 to understand fractional revival and many other things by Wheeler and Sly. That just like in real space, there is interference. It shows ups and downs. Phase space also there can be interference. And there lies the key to understand the cat state and what happens if you add a photon to it. Now they will see very beautiful structures. Those things will be useful, and it was first pointed out by Jurek that for metrology, very small displacement in coordinate rather and momentum, or to be more precise in terms of light, the quadrature can be measured using those shapes. That is one of the practical reasons why people are studying this kind of case. Now you will see that how the statistics and intensity correlation manifests when you change the cat state by adding a photon, so that the phase measurement can be carried out accurately. When cat is around, the pittance cannot be far away. So I'll show you that this pittance state is actually a very interesting thing, because it can simultaneously sense very small difference in coordinate and momentum. This was a very beautiful paper by Jurek around 2002. So then I'll talk a little bit about how to produce photonated cat states and then summarize our results. So as I mentioned to you that the coherent state mathematically is fairly simple. It's an eigenstate of A. And if you look at the eigenstate of A, and you will find out it has a shifted Gaussian. In principle, this alpha can be complex. So the real part shifts X, and the momentum and the imaginary part acts like momentum. And if you do a Fourier transform of that, you'll find out the momentum shifts by alpha 2. So if it's a purely imaginary shift, that amounts to a shift in the momentum. If it's a real shift, it amounts to a shift in the coordinate. Now, okay, they have been there for quite some time, studied quite extensively, and Sudarshan, Lauber started this thing. Laser is a physical realization of that. Now, so if you see in terms of Fock space, in the harmonic oscillator eigenspace, so here is the normalization factor. So and here is the statistics distribution. If you take alpha bar square as t, you can find out from here that it will be coordinate state will show the statistics which is Poissonian, because e minus t to the n by n factorial will come when you take alpha overlap. So the number of states, the Fock space, will be distributed according to a Poissonian distribution. And people say, more rigorously, that it is actually classical light. So now they have, of course, realized through laser. So this statistics is the main thing here. And there are many other ways to show its classical nature. If you do the time evolution, you will find out the time evolution. Under time evolution, this alpha will behave like a harmonic oscillator. If you satisfy the center of the Gaussian will move like a harmonic oscillator. Okay, so now this cat state, I write down the general one with the phase in it. This is this famous Yerkes-Dollar state. If you study this state, then of course its special limit, theta is equal to 0, it will be even cat state. Theta is equal to pi with the odd cat state. Both of them are eigenstate of A square. Because A on alpha is equal to alpha. A on minus alpha is minus alpha. So if you take A square, it will be eigenstate of alpha plus minus alpha. So these states have been experimentally realized around 18 or 19. And people have actually shown that if you start with the, let us say, even state, if you go to odd state, the parity changes. And you can actually detect the parity change and do an operation to bring it back. Similarly, if there are lots of photons, it is an eigenstate, if theta is equal to 0, it's an eigenstate of A square. If 2 photons are lost, it will come back to itself. So that is the reason this thing has been used in the so-called CAT code. It's a computational code. Just like qubit 0 and 1, cat state can be used as qubits. So now, although it looks sort of very innocent, this phase has a very significant role. You will see it manifests as expected in statistics in a very big way. Now, physically, if you ask me, where do you see these kind of things? A classic example would be double well potential. For example, in Feynman's book, you will see the ground state of the double well potential can be very well approximated by a Gaussian in 2 locations, x is equal to plus alpha and x is equal to minus alpha. Now, so as I mentioned, this A square eigenstate, the fact that cat are eigenstate of A square leads to the so-called CAT code, particularly very useful quantum error correction. Now, as I mentioned, these properties, particularly the interference, phase, all those things, really comes out through Wigner function. And Wigner function was introduced quite some time back, and it is it's not exactly a probability distribution because it can be negative. So if mathematically, it is actually basically take your original wave function, displace it by psi star is displaced by some amount u, y, psi is displaced by minus y, and you do a Fourier transform kind of thing. You get the function. So it's a function. You can actually deal x and p as regular variables, no commutation, nothing. But it has very beautiful properties. More formally, since you are displacing the psi star by y and psi y minus y, the displacement operator comes into play. Now, because one is plus, one is minus, so this parity operator comes in. So it's a composition of the parity, which is pi, and displacement operator formally gives you the Wigner function. That is a nice way, physical reason why people write it like that. This parity operation in particular is used in bringing back, this event state to from the odd state or vice versa. So now, if it is positive, then it is classical. It shows classical nature. So negativity of the Wigner function is a mark of quantum effect. So now similarly, so that is what we look out for. Now, if you go to the P function, you can clearly see that the negativity of P function, for example, it is very beautifully, you can put it like that. Now, if it delta n square, if it is Poissonian, it is delta n. Now, if this measure P, if it is negative, this fellow is going to reduce n. So therefore, it is a signature of non-classicality. Okay. So now, same thing for Wigner function also. Now, for example, coherent state is a shifted Gaussian, perfectly classical. You can see that it's a Gaussian both in the coordinate and momentum direction. Now, if you look at event cascade, sum of two Gaussians, so it doesn't vanish at the origin. So there's a big peak here. Then there are these two other peaks which arise because of the localization. One is at plus alpha, one is at minus alpha in the x direction. But if you put a phase, you can see that there will be minor peaks in the momentum direction. So that comes from the phase that alpha 2, and that leads to interference effect and negativity. So that is the reason why all these things that I'm going to show is going to appear. This interference in the phase space. Now this is see, for example, you will see that squeeze. It's not that Wigner function negativity is the only measure of non-classicality. For example, squeeze coherent state. It's a shifted Gaussian with squeezing such that delta and delta p are not equal, but it is not negative yet. One of the quadratures, it is more squeezed, but still it is quantum. So this part one should keep in mind. It's not that the Wigner function negativity is the only marker of quantumness. Now this was 1991 was the year when Agarwal and Tara studied this multi-photon added coherent state and pointed out that there is through this Q parameter, n square average minus n average square by average n, that there is squeezing. So they use both Wigner function, Q function to find out that what happens as you kept on adding more photons, it became closer and closer to Fock state. So non-classical nature came out. Then it was experimentally realized in a very beautiful experiment in 2004 in Nature paper. So now, basically, you take a cavity and coherent state is present. So a single atom passes and it emits a photon in the cavity and comes out. Then no, it's a photon added coherent state, very sensitive experiment. Okay, so now this is a single photon added coherent state. So the alpha parameter I have taken one, you can see the squeezing. And so one quadrature is getting squeezed. It becomes more pronounced if you go to x-space. Alpha is equal to 1 and then alpha is equal to 3, you will see that it shifts and gets small alpha is more quantum, large alpha is classical. Now you can look at this Q parameter which I mentioned n square average minus n average square, and m is equal to 0 is flat 1. Now, as you keep on adding more and more photons, it becomes less than 1 in a pronounced way. This is the result of Tara and overall. Now, let us go to our cascade. Now, in cascade, so you see the original cascade, alpha is equal to 2.3. So there is some kind of particle and wave nature kind of thing which comes out for small alpha and large alpha. You can see here it is localized. So localized means delta x is small, so highly localized. So you can see the dominant takes high, significantly high value in your origin. Okay, now as you increase alpha, so the fellows, these two Gaussians are splitting apart, and there is the interference. So this is the interference which is like a wave behavior. And this interference will not come out in the real space, only when you go to momentum space. So if it is localized in the x coordinate, interference pattern will come out in a momentum direction. If it is momentum localized, interference will show up in the x direction. It's a very beautiful. And now this difference, this positive to negative, this red is positive. This difference is like, in case of diffraction pattern, is a quantity which is measurable. Now, if you change alpha, this quantity changes. So this, as I mentioned to you, the cascade has been used in experiment. I think that the experiment was first done in 2007 to carry out soft Fourier sensitivity. Namely, you can measure frequencies less than what is allowed by the Fourier. Soft Fourier, the precise name is soft Fourier sensitivity. Slight change in frequency, they of course dealt with time and using laser, time and frequency domain. So that's the reason delta nu was the thing that they could measure. And this experiment is a physically related experiment titled soft Fourier sensitivity. This comes from here. So this kind of measurement is very sensitive, and people have already done experiments. Now, if you add, so to be more precise, if you add now 2 photons if you add, you see negativity. Now, just 1 second. This is no, actually I'm making it. I think this is the original cascade. This is the original cascade, and this is the photon added cascade. You see the negativity which appears here. That actually makes it measurable. If you add a photon, you can actually see that in phase space a single photon produces a difference, and that difference is measurable. So rate is high value, so that it produces a D. And for larger value of alpha, you can see interference pattern also differs. For without photon, simple cascade, and with photon. So this obviously, because it's like number difference, 1 photon and no photon, the origin, the particle nature is more prominent. You can see very clearly the negative domain here that tells you a single photon has been added. Now, phase space, of course, also gives information, because without photon, this is the structure, with photon, this is the structure, but this is much more prominent because of single photon number state. Now you go to 2 photons. If you add 2 photons, expectedly, you can see here that the origin becomes now positive. You see there are now these 2 domains. So separated by a clear negative thing. So you can actually measure these high values, and you can count that 2 photons have been added. This of course shows up here also. You can see comparison to here, but is much more prominent with small value of alpha. Now, Hidden state is actually a state which is localized both in coordinate and momentum. It was studied earlier, in the context of in a formal way, but a beautiful paper by Jurek, a paper in Nature in 2002, highlighted the use of these states for sensing of quadrature deviations. Like for example, delta x, delta p, very small changes, you will be able to measure them. And it shows that if these states reach the so-called Heisenberg limit, coherent state is 1 by root n, short noise. Hidden state precisely goes to 1 over n. So the maximum sensitivity can arise from hidden state. And there have been experiments, like I remember correctly, 2017 and 19 and later on more experiments showing the hidden state's ability to sense this quadrature deviations. So what happens is here, why Keaton state is so nice? Because you see there are now phase space, in the phase space, there are two different kind of interference. There is interference, there are 4 Gaussians localized in 2 in the coordinate space, 2 in the momentum space. Now there is interference across this, interference across this, and again interference across this. Because of which at the origin there are tiles. You can see here zeros, 4 zeros. So there are tiles which are marked by zeros. Black is 0. Each tile has an area which is less than the Planck constant. And that was Jurek's question. Does it make physical sense? So zeros are measurable. You can actually measure them. So what does it mean that this resolution is less than Planck's constant? Because we thought that in the phase space the basic unit is Planck's constant. Jurek actually pointed out with a very beautiful paper that this area is actually measurable, and if you change slightly delta x and delta p, these things are going to be shifted, and that shift can be clearly measurable. And so as you make bigger and bigger Gaussians, they become more and more accurate, because this Planck's area, short Planck area, is h bar square by capital A. Capital A is the effective area of the Gaussians. Very counterintuitive results, and some experiments have been also done. So you can see here beautiful carpet-like thing where the zeros mark one tile. The basic 1 unit of the tile is 4 of them. If you combine 4 of them, because lambda by 2, another lambda by 2, this way also. So this was what Jurek's result is. And now these things, if you add a photon, what will happen? Why is it sensitive? You can see here clear change, in the both in the localization effect and also shift. In fact, if you look at it very clearly, you will see the zeros are shifted very clearly. So these are measurable. Very, very accurately, you can add photons and measure them. Now, for example, if you take with the phase, you can actually do n square minus n average square. This is a typo, n average square, this Q parameter. If it is less than 1, in fact, anti-bunching. Q greater than 1 is bunching. For example, anti-bunching was the first one which led to this origin of quantum optics, because the Hanbury-Brown twist effect, if one photon comes, it's unlikely the other photon will come. Bunching is the other way around. So this kind of studies, number fluctuation, is the one which led to the birth of quantum optics through this famous Hanbury-Brown twist effect experiment. Now, if you compute, if they come out as functions of alpha, a bit lengthy, but you can compute n square in average, and you can nicely plot them. So n bar square, actually, you can see that they're all lie below 1. So they show anti-bunching, and there is certain difference of theta in the presence of theta. You can see there are certain differences, and differences are small, differences are big for small value of alpha. So quantum nature truly comes out for small values of alpha. Now, how do you produce them? For example, how do you take a coherent state, a squeeze state, and add a photon? So you basically take a James-Cummings model where the photons interact with this two-level system, and atoms are there. Now this atom field, you start with a cascade. First, you have to produce a cascade. Now, so originally you start with a cascade and atom in the excited state. Now you evolve time. In time evolution, the Hamiltonians of this kind. A photon is annihilated, and sigma plus state goes from 0 to 1. A photon is created, the state comes down. So if you take this kind of Hamiltonian, which is apparently routine in quantum optics, and in the James-Cummings system, you start with a state where you have to create a cascade path, and then an atom in the excited state. After a short time, it actually evolves into this, that there is a cascade with a single photon, there's a cascade with no photon. So now if you observe it, half of the time, of course, you'll find out that it is cascade with one photon. So this, in fact, makes it quite plausible that quantum optics people tell me that it should be possible to see this. Okay, so now let me summarize. So addition of one photon to a cascade leads to the changing parity. Namely, the even state becomes odd state becomes even state. So this parity change has been measured experimentally and helps in correcting, bringing the original state back, because apparently measuring the parity is easy and giving a kick to the state to come back after that is also easy. This is very nicely illustrated through the Wigner function. Very clear manifestation for small alpha as negativity increases near the origin. Now, this also leads to squeezing. So, in principle, what does the squeeze test can be achieved through this process? The presence of a theta gives you control parameter. You can actually make it Poissonian or Poissonian as you will. This could be useful in cryptography. Now, furthermore, for sensing purpose, for the soft Planck structures, PLA and CK, soft Planck structures are quite useful. In fact, sophisticated type of states have been created. There was a PRL paper in 2019 which created a very robust composite state which has a very fine soft Planck structure which is very robust against noise. They can be useful for sensing purpose. Now, if you add photons, then of course squeezing also is achieved. Now, people are now beginning to use these kind of things for producing cat code, and of course many other fundamental experiments. One can also carry out dealing with statistics. So this is the paper I was referring to. Orman and Gargi, they are my students, and this just came out in optics letters. It followed the first paper of Aurora, who was my colleague in Hyderabad. This was 1991, and this is the first experimental paper which showed the title it as quantum to classical transition with single photon. Coherent state was classical, and one photon it becomes quantum. So I will stop here, and so thank you for support. Any questions?
Thank you very much, Professor Pangai.
Thank you.
I also thank you very much for your effective use of your time.
Thank you so much.
We can take a question. On my chat board, there is no question now.
People can send emails to me later on.
Maybe. Okay, thank you very much. We can take our next speaker, Rasim Jabbarov. Is Professor Jabbarov here?
Do you listen me?
Welcome, Professor. How are you?
Yeah, can I share my presentation?
Okay. We have limited time.
Yes, I know.
If you share your document here, your video, and we can begin here.
Yes, I cannot share my presentation. I don't know why. My presentation is OK.
What?
My presentation is OK.
Yes, is off. We cannot see your presentation on our screen.
I can start?
Yes, you can start.
Yes, thank you very much.
And you can introduce yourself if you want.
Yes, I am Rasim Jabbarov from Azerbaijan National Academy of Science, and same time I am head of the scientific department, Research and Development Center for High Technology at the Ministry of Information and Communication.
Sorry, will you share your screen?
What?
Will you share your screen?
Yes,
your document.
Mr. Rasim.
Merhaba hocam.
Hoş geldiniz.
Çok sağ olasın hocam.
Welcome.
Thank you very much. But I cannot share my...
You can share your screen.
Yes, I've lost my screen there.
Bottom side of your screen, you can find share screen option.
Yes. Where is,
Okay. Yaxshi.
Have a nice talk.
it's
You have 15 minutes.
yes.
Rasim hocam.
My presentation is ok.
No, it is online now.
I cannot.
Okay, you can continue.
Of course. Of course. Our era is that 21st century is an era of knowledge-based society. If we look the history of lighting, we can view it as a development of increasing the efficient technologies for creating visible light. Of course, we will focus on solid-state lighting technology based on inorganic light emitting diodes. As solid-state lighting LED technology is more advanced and more likely to be first to enter general illumination application. This new white light source will change the way we live and the way we consume energy. It is an important economic and social problem. Rapid development of high brightness efficient LED is affected by many factors, from the selection of the substrate material for growing of the LED chips and to the packaging of LED, such as lattice mismatch between gallium nitride, less structure, and choosing substrate, green gap problem, size of phosphor, and package. Therefore, in this work, to improve the light quality, we have mainly analyzed two factors. One of them is the impact of carbon nanotubes due to the hexagonal structure to improve the crystal quality of gallium nitride substructure by applying multiple carbon nanotubes as an intermediate level layer between sapphire.
Sorry, Rasim, can you see your PowerPoint in your screen?
I don't know why I cannot.
If you have Rasim desktop'ta masa üzerinde varınız mı PowerPoint? Onu açın. Biz Zoom sadece görüyoruz burada.
Ben açabilmiyorum onu. Bilmiyorum neden.
Siz bunu minimize edin. PowerPoint'unuz orada mı?
PowerPoint'um desktop'ta.
Desktop'ta. Ama biz sizin desktop'unuzu şimdi görmüyoruz.
Ben de anlamıyorum neden.
Bunu Zoom'u kapatmayın. Bu sayfayı kapatın. PowerPoint'i açın.
Bunu kapatın.
Evet. Kapatmayın. Minimize edin o şeyi.
Minimize edin.
Sorry. Okay. Şimdi onu aç. Full screen, aşağıdan full screen yapsanız. Ama burada 5 slide var. Aşağıdan Rasim bu aşağıda sağ tarafta. Ha. Evet, aşağıda üçüncüsü sağ taraf. Yok, o yok. Yine gittiniz oraya. PowerPoint aşağıdadır hocam. Tamam.
Animation'dan
Presentation modu seçeceksiniz. Evet. Aynen. Tamam. Sağ olun.
Şimdi tamam oldu mu?
Oldu. Sağ ol.
Şükür
Thank
Allah.
you.
Şükür Allah. If we look the picture, energy conversion of phosphor converted white LED from electrical input to light output. We will see what problem we have and what technical challenge for theoretical limit of white LED are still continued, and key improvement parameters as follows. Of course, chip efficiency, phosphor efficiency, and package efficiency. All this level, we have the improver parameters, and we have the problem. Today, my task is, one is problem is to decrease the lattice mismatch between gallium nitride and sapphire substrate. Therefore, we used carbon nanotubes, multiple carbon nanotubes, and because large difference in fundamental properties of such as lattice constant and thermal expansion coefficient between gallium layer and sapphire substrate generated structural defects and high density of trading dislocation. And that leads the deterioration of optical and structural properties. Therefore, applying hexagonal structure carbon nanotubes thin layer with high thermal stability on sapphire as primary layers plays a role to decrease lattice mismatch between sapphire on gallium nitrides. And you look at this picture, scan electron microscopes analyze which gallium nitride carbon nanotube sapphire and gallium nitride sapphire, and you will see full white half maximum at low temperature, which kind carbon nanotubes. The full white is very narrow. It is indicates that we can decrease the trading dislocation and increase the structural quality of the sample. Of course, more details needs to be studied in order to give more explanation of this behavior. And future we will enter this subject more seriously. Due to the pandemic period, we cannot visit any laboratory, and we cannot more detailed about that. Second one is the application of multiple pyramidal shaped phosphor structure to negate the reflection and the reabsorption of photon in the LED package. Of course, we have SMD LED devices, and today is modern implementation of the light emitting diode technology is chip on board technology. COB represents an array of light emitting chips placed on a common substrate, which are electrically connected to the metal plating and covered by encapsulated materials. The encapsulant protects the chips and the wire bonding from the effect of the ambient. The encapsulant may also contain phosphor particles, which convert the primary wavelength emitted by the chip into the more other wavelength as a down conversion. COB, that means chip on board, demonstrate a number of advantages over an array of individual LED assembled into a light module. The advantage include a reduction of manufacturing cost due to the use of shared electrical connection and optics, bigger optical power, and more compact size. COB, however, suffer from the energy loss associated with mutual absorption of light by the neighboring chips. The basis problem of encapsulant light-emitting chips is the total internal reflection at the planar encapsulant air interface. In COB, light rays that experience total internal reflection and get reflected back into encapsulant can be partially absorbed by the chips and the substrate. Well, to use this pyramidal shape structure, we have the increase in efficiency, approximately 40%, and luminous flux, 10%. And simulation results also show that photons are trapped between flat, if the flat phosphor layer, what you see the simulation result, flat phosphor layers and substrate, and photons are in the pyramidal shaped form, photons are redirected under different angles, which causes less backscattering. And therefore, applying pyramidal shaped phosphor layer to the gallium light-emitting diodes, we change the optical geometry of photon propagation, can improve such negative effect as total internal reflection and backscattering of photons inside the LED package. Photoluminescence analysis showed increase of luminous flux and efficiency with the use of pyramidal shaped phosphor. I think that my time is end. I am here for your question. Thank you very much for your attention. Hello. Hello. Do you listen me?
Thank you very much for this nice talk. We can take questions.
Yes, please.
Okay. Don't have any question. Thank you again. And we have limited time.
Yeah.
Therefore, we can take next speaker now. Thank you, Rasim Jabbarov.
Thank you very much too.
Our next speaker and the last speaker is Dr. Özgür Selimoğlu from the Ankara University, Faculty of Engineering, Department of Engineering, Energy Engineering. Özgür, welcome. Hi, Özgür.
Merhaba, hello Ramazan hocam.
Merhaba hocam. Hoş geldiniz.
Merhabalar.
You can begin your talk now.
Thank you. Okay. This is Özgür Selimoğlu, and I'll present our latest study about silver zoom lenses. And this study is also a part of the master thesis of Barış Tanyeli, supervised by me and by Dr. Semran Sağlam. And this is my outline. I'll go over this study step by step. First of all, the importance of silver imaging and applications that I'll discuss. Then design targets and requirements. How we start to design a zoom lens by using a 4 subgroup layout. Then paraxial lens design, I'll explain. After the paraxial lens design, we will use real glasses to design a silver objective. Then the optimization step will come, and at the end, I'll show our results and also give some comments how to improve this design. First of all, I want to mention the spectrum of light. We all know the spectrum of light. And with our eyes, we only see a limited portion of the spectrum. When we go to longer wavelengths that we couldn't see with our eyes, we see the infrared light at that region. Although all the spectrum at that part is called as the infrared, in fact, there are sub-portions of this infrared light. Not all the infrared light is the same. And we can say that there are near shortwave, midwave, and longwave infrared regions. And in fact, the applications related to these different infrared lights exist. And for example, for the near infrared and shortwave infrared imaging, we mainly interested in with the reflectivity and transmission of the objects. But if we go mainly to the midwave and longwave regions, it is more called as the thermal imaging, and self-emission of the objects are important. And when we image something, we see the temperature of the object. And in this study, we mainly focus on the shortwave infrared region. The shortwave infrared region getting very important for the recent years as a result of the development in the sensor technology, such as the standards in indium gallium arsenide sensors are more available today. And as you see, the technology that we use in the visible band needs different kind of sensor technology. But if we want to image a shortwave region, probably the first selection will be the indium gallium arsenide sensors. And from the pictures here, as you see, the applications or the imaging gives different results. For example, this is visible image of an apple, but when you image it in the infrared, shortwave infrared region, you see different things. And similarly, it is also different for the quality checks. This image is much different from this one. So changing the spectrum of the imaging gives us a lot of different information. What are the applications of silver imaging? Silver imaging is used to provide a clear view in low light and hazy environments. Maybe this is one of the most important applications. Another one is to view the declining of fruits and vegetables that cannot be distinguished by human eye. And to analyze the fertility of soil and how healthy the plant is in the field of agriculture is another application in the agricultural field. Also, we see some applications in the biomedical applications between the tumor tissue and the healthy tissue in the field of medicine, especially in the area of open for surgery, can be distinguished by the silver imaging. Let's go into a little more detail. Silver applications are important for moisture detection. Water is strongly absorbing at wavelengths of 1450 nanometers and 1900 nanometers. So that field level detection through non-transparent packaging is possible, as shown in this picture. Also, detection of the dents or bumps in fruits are possible, and gauging relative water contents in the plants is possible with silver imaging. When we go to the semiconductor and solar cell production lines, silver imaging also becomes important. The light emitted by the silicon has a peak at 1150 nanometers, so we can detect the emitted light from silicon materials. And also at wavelengths above 1150 nanometers, silicon is transparent. So we can see the defects in the silicon material. Also, silver application can be used for thermal imaging if the thing that we want to measure has a very high temperature. For example, here we have a soldering iron, and it has a very high temperature. And in the S4 part, S4 imaging, we can see that it has a shiny image. And for the long-range surveillance applications, S4 imaging is important. And for this case, sorry. As you see in the left picture, we have an airplane. It is very easy to detect, but for the visible case, it is hardly detectable. And this picture is taken from our university campus. As you see in the shortwave infrared region, the mountains, the background can easily be seen in a very hazy day. And in this case, for example, it is taken at the same time nearly. The visible case, the mountains are not possible to see. So shortwave infrared imaging is getting important, and to develop applications, we need spatial lenses that is working in the shortwave infrared region. Otherwise, we are not getting the most of from the sensor that is developed. So in this study, we are trying to develop a shortwave infrared lens. And these are the design requirements of the shortwave infrared lens. First of all, the spectrum is taken from 900 to 1700 nanometers. The focal length range is from 30 to 90 millimeter. The F number is taken to be small, smaller than 2.5, so that we can get we can see in the low light conditions. The image circle diameter is selected to be 12.3 millimeters, which can be used for 15 micron sensors. We are applying mechanical compensation for the zoom technique, and mass and volume should be minimized. And as another requirement, an iris is required. And we want the first lens and the last lens to be fixed, so that it is more easy to use. So back focal length should be fixed while zooming, and fixed F number is targeted while zoom operation. So as the variable zoom is necessary from the requirements, several sub-optical groups has to be used. But if and mainly the zooming operation is related to changing the focal length. If only focal length change is required, then only 2 groups may be enough. But in this study, we have more constraints. So 4-group lens design best suits to the requirements. What are these requirements? The aperture stop should be at a fixed location. The first and last element should be fixed, and the F number of the lens should be independent from the zoom operation. So all these requirements taking us to a 4-group lens design. The optical design layout with 4 subgroups can be used to cover all these design requirements, and there are in fact 8 different varieties that we can discuss. Optically balanced lens design needs 2 movable lens groups. One is variator and the second is the balancing group. And while focusing, first moving group is changing the magnification, and the second moving group performs the focusing operation. So every design, in fact, should start with the paraxial design. And this is the paraxial approximation of the 4-group zoom lenses that we used. And we make some design choices. First of all, first element of the zoom lens is selected to be a converging lens. This choice minimizes the size of the optical components. If the first optical elements were selected to be negative, then the rays will diverge, and as a result, later elements will be much larger. The second element, selection of the first element to be positive is leading the second element, in fact, becomes a negative element to compensate the chromatic aberration. Therefore, second element is chosen to be negative. Third element, this can be positive or negative, and the main reason that we use is to compensate the change of the focus position. So this is the compensating element, and here we are give permission to the optimization. It can be negative or positive. So we are not restricting this element. And the fourth element is focusing the light and generating the image, so it is also a positive element. Therefore, the selected configuration is P and XP, positive, negative. Positive or negative can be the third element, and the last element is a positive element. And here, the paraxial representation of the zooming operation is shown. The first configuration has a large field of view and has a long effective focal length and large field of view, and the second element medium field of view, and the last one has a small field of view and long effective focal length. These are the paraxial lens groups specifications. All the focal lengths and the separations are given if somebody wants to reconstruct this design by himself or herself. And after the paraxial lens design, we should now go into a glass selection. Because the paraxial lenses are ideal lenses. In fact, there's...
You have got only 1 minute.
Oh, so, okay.
I don't want to break your nice talk.
Okay, I'll be more quicker. Glass selection is shown here. So in the S-Ver band, most of the flint glasses become chrome glasses, and we need to select glasses from them. And the paraxial to real lens layout is changed by considering several glasses. And initial material choices are performed. The first element, the second element, all selected to compensate the chromatic aberrations. And mostly we selected higher index materials. And the first initial performance of the lens is shown here. So all the ideal lenses become real lenses. And at least MTF is not totally zero in this condition. And after that, we define a merit function. To protect the design layout, several constraints are applied. And to do that, for example, the element sizes and separations all constrained individually, so that when we push the optimization button, the layout is still conserved. And after that, the third and fourth elements is separated and doublets is replaced to the locations. And finally, we get these 4 configurations as a result of the optimization. And from the aberration charts, the sidal diagrams are shown here. And when you look to the final parts of the aberrations, mainly the distortion is the main factor. And here you see the MTF charts. And as you see, we all have plus MTFs at the Nyquist frequency. So this lens design may be acceptable for many applications. And when we come to the conclusion, when we check the design, MTF seems acceptable, but there is a room for further optimization for the edge fields. And astigmatism should be reduced for further improvement. The dominant aberration seems distortion. Although the distortion is high, it can be compensated by post-processing as the image is captured by a digital sensor. And the F number of the optical system changes plus minus 10% when zooming. To overcome these issues, stop position will be studied more and further constraints will be added to the merit function. And these are my references. Thank you for listening.
Thank you very much for this nice talk. Now we will give a lunch break.
Okay.
Süleyman Hocam, do you have any message to the participants? Yaşar?
Thank
Yes,
you.
Do we have
Thank you
any
very much.
message?
Thank you very much, Professor Ramazan Koç. Süleyman Hocam buyurun.
You can continue. I want to thank Mr. Özgür Selimoğlu. Thank you very much for your contribution to the conference. Thank you everything for everyone.
Okay, after the lunch break, we will continue.
Yeah. Yes, after the lunch break, we will divide it to the two halls as the first day of the conference. Our colleagues share the links of the two halls here with password also and announced. It is clear, I think. After 32 minutes exactly, we will come back here. And thank you, Professor Ramazan Koç, for your nice chairing, and also Professor Süleyman Özçelik and Özgür. Thank you. Goodbye.
Thank you very much, hocalarım.
You're welcome. Bye.
Good afternoon. Welcome to session 3 in hall 1. We are going to start introducing our speakers. Our first speaker is Dr. Nezaket Kerimli. I don't know if our speaker is here.
Hello, Professor. I think she is not here now. But I have her video.
I believe she's here, but she's not host. I've seen
Nezaket Kerimli.
Nezaket Kerimli.
Okay, okay. I see.
Here.
So probably we can allow her to.
Hello, everyone. I'm here.
Okay, okay. Could you please share your screen so we can see your presentation?
Yes, of course.
So Nezaket Kerimli is from Bakü State University, and today she's going to talk about the action of losses at three-way mixing in metamaterials. And when you're ready,
sorry, yes, is it seen?
We have not seen your presentation. Yes, you started screen sharing, but you should probably click your presentation for us to be able to see it.
It is seen in my computer.
When you have your when you share your screen, you should probably click the presentation.
Sorry.
It says double click to enter full screen mode. Okay, now we can see it.
Okay.
Okay, you can start your presentation.
Thank you.
But it disappeared. Your we don't see your presentation right now.
Gözde bir çetek, gözde kızım. İmkan ver, bu özüm elim. İmkan ver. İmkan verin.
Bak şunu göstereceğiz. Götür başkalarına.
Okay.
Okay.
Yeah, you can have it full screen mode. Yes, exactly. It's okay now.
Okay. Okay. Hello, my name is Nezaket Kerimli. As you mentioned, I'm from Bakü State University. I would like to express my thoughts beforehand. You know, today is two great events in my life happen. One of them it's about the day of the establishment date of the first democratic republic in Azerbaijan, and as you know, 100 years pass since establishment of the first democratic republic in Muslim East, and which is corresponding to this day. And the second, it's about my presentation in the famous university, Gazi University, in our brother Turkish country. Our presented paper is about the action of losses at three-way mixing in metamaterials. Okay. As everybody knows, it has been problem. Wave loss has been a problem for materials, which is associated with negativity of electric permittivity and magnetic permeability of these mediums. And theoretically, we try to analyze and understand influence of different factors in within materials during interaction and nonlinear interaction of waves within materials. And in entrance of materials, it's taken omega-1 and omega-3 waves. It's considered to be omega-1 and omega, where the omega-3, it's about the strongest pumping wave. Omega-1, it's about the some frequency. And during the generation, we are taking into account amplification of backward wave within materials, you know, and omega-2, it's about the wave which has the negative index of refraction within these materials. And this is analysis, understanding of these processes is done by us due to method of constant intensity approximation. This is method was proposed by our greatest scientist, Professor Tagiev, in 1978. But familiar other method also is known. This is about the constant field approximation, the method of constant field approximation. And this is authors, which is presented in our slides in 2010. They tried to analyze this interaction of waves with the materials based on constant amplitude approximation. What's the difference between constant amplitude approximation and constant intensity approximation? During constant amplitude approximation, the complex amplitude of waves are considered to be constant, but in based on constant intensity approximation, only real amplitude is considered constant, but a phase changing of phase between these interacted waves also is taken into account. In order to understand the amplification and generation of this counter wave, theoretically, this understanding, we use shortened equation, where the first equation describes the omega-1, and this is, I mean, this sound wave frequency. This is A3, it's about the complex amplitude of this pumping, strongest wave, pumping wave, and A2, it's about the generation of this counter wave or backward wave. And using these boundary conditions based on method of constant intensity approximation, we could find the complex amplitude of counter wave, I mean backward wave. And this is general form. And for a specific condition, for phase match condition, it's found like this one. And from this equation, we try to understand influence of these wave loss to amplification factor of this counter wave, I mean backward wave. As you notice from this, it's about the complex amplitude of backward wave. From uppercase, one can consider that with increasing of, we could understand that with increasing of the wave loss, you know, intensity also, the intensity will be decreased. With increasing of wave loss, intensity will be decreased. But this is increasing of this wave loss will be met. It can reach to some value. When it can be met, it can be compensated by wave loss of the backward wave. After that, this is a increasing of intensity of backward wave was obtained by us. And also we try to analyze this amplification factor. And I want to say something else. This is, but this is positive contribution of this uppercase, but every time it's a negative contribution of the down case also takes place. And this amplification factor.
You have 5 more minutes.
Okay, amplification factor is found, and here for ordinary medium, I mean this volumic medium, and for volumic medium, and for metamaterials it is found, and this is graphically comparison at different pumping waves intensity at different intensities of initial waves. You know, we could analyze changing of amplification factor, and one can easily figure out the higher intensity, the higher amplification factor is, and at a given different wave losses. And here optical fiber, metamaterials, and volumic medium is compared, as you notice. 4 belongs to metamaterials, 2 also it's about at different initial intensities, and third and 1 it's about volumic medium. As we noticed, the amplification factor it's greater comparing with volumic medium. And here it's conclusion.
Thank you for your presentation. Now I would like to ask audience if they have any questions. Okay. I guess we don't have any questions. Thank you for your contribution and the talk. So I would like to.
It's an honor for me participate in your conference in Gazi University. Thank you.
Thank you. Hopefully we'll see you in the near future. We'll
Inshallah.
see you in Ankara, in Turkey. Thank you.
Thank you.
I would like to ask our next speaker, Hakan Yargin, if I don't know if Hakan Yargin has joined.
I joined. Hello, everyone.
Yeah, Hakan Yargin is from the Electrical and Electronic Engineering from TOB University from Ankara. And the title of the talk is Simulation of a Semiconductor Laser Using EWR Design Environment. And if you are ready, probably we can start.
Okay, can you see me, and can you see my presentation?
Yes, we can see you, we can hear you, and we can see your presentation.
Okay, thanks. Let me start then. Good afternoon, everyone. Before we begin, let me introduce myself briefly. I'm Hakan, and I'm a postgraduate student at TOB University of Economics and Technology, Electrical and Electronics Engineering. Same time, I'm working at one of communication and security system company. Today, I'm going to be talking about simulation of a semiconductor laser using AWR design environment. I'll begin with our motivation, then continue by semiconductor lasers after I talk about semiconductor lasers equivalent circuit and its math behind, then results and conclusion. Communication is the transfer of meaningful information between the transmitter and the receiver in the transmission medium. Today, population growth, globalization, the desire to reach any information fast from anywhere, and the needs that diversify with the developing technology have increased the importance of the technological developments of the communication system. As you see in the figure, in mobile communication, the bandwidth has been increased 10 times for every 10 years. It is started with transmission of electrical signals over copper wires, diversifies and continues as wired and wireless transmission. Due to occurrence of capacitance and inductance along the conductors, it causes the metallic cables to act like filters that limit their bandwidth. Fiber optic cables, on the other hand, work on the principle of full reflection of light. And then, because they do not transmit electricity, no capacitance and inductance effects occur on the cable. In this way, communication is provided with low loss rate and high bandwidth. In places where cable length costs more and there are multiple users and mobility, wireless communication is preferred and it's provided with radio frequency waves. Microwave photonics is an area formed by the combination of these two powerful technologies. You take the RF signals, modulate it in the photonic area, and then transmit it with high speed, and then reproduce your original signal. It is the transmission of the radio signal from the user at high speeds. Here is our radio antennas between the communication system centers over the fiber optic cable by modulating the light without subjecting it to another frequency process. In short, it is the name given to a high frequency broadband microwave communication system in which radio frequency electrical signals are converted into optical signals and then transmitted using optical technique. In order to design a realistic communication system with RF fiber, a reliable simulation environment is needed. The simulation of fiber optic based communication is well established area, and there are very precise commercial simulations environment like VPI, OptiWave, etc. However, it was shown that RF transmission over fiber systems does not work well with these environments, and that the system has both optical and RF components. In our work, we aim to simulate the components and process in a purely RF simulation environment. For example, as you see in the Balkan and Golan city, optical-based simulation environment could not able to give similar result as experiment. But AWR simulation environment give close solutions. In order to provide a reliable simulation environment for RF over fiber systems, AWR is proposed. AWR popularized microwave software environments in both academia and industry. Also 6 months free for academic usage. AWR does not have any optical tools, hence each optical component have to be modeled using electronic components. We start with modulating a semiconductor lasers on AWR and will present the approach and first results. First, let me tell you how laser it works. We have two bands, two energy levels. A photon comes to this band, active layer, and the photon makes the electron jump to the higher level from lower ground level. The photon is consumed and the electron moves to upper state. This is called absorption. When an electron is in the excited state from one state to that higher energy level with energy difference delta E, it will not stay there forever. Eventually, a photon will be spontaneously created having energy delta E with random direction, conserving energy, the electron transition to a lower energy. This process called spontaneous emission. A photon can also cause an electron to drop from the higher to the lower level, emitting a new photon having energy delta E, and the emitted photon exactly matches the original photon in wavelength, phase, and direction. This process is called stimulated emission. Laser radiation, where it comes to the name, it's initials of the light amplification by stimulated emission of radiation. It's nearly monochromatic. Monochromatic refers to single wavelength or one color of light. Laser radiation contains a narrow band of wavelengths and can be produced closer to monochromatic than the other light sources. Laser radiation is highly directional. The radiation is produced in a beam that is spatially narrow and has light divergence relative to other light sources. Laser radiation is highly coherent, which means waves light emitted have a constant relative phase. The waves of light in a laser beam are in phase with one another at every point. This is the reason we get more power according to other light sources. So now I will try to tell you rate equations and solutions. Rate equations are described as the exchange of energy between the input current and the output power by considering the rate of exchange of the three principal optical process known as spontaneous emission, stimulated emission, and absorption. Everything in this equation have physical counterpart. Eta E is the efficiency, I is the injected current, Q is the electron charge, where act is active volume of the active cavity. A, B, C are the recombination coefficients. G is the gain. S and N are our carrier and photon densities. Beta is the spontaneous emission coefficients. Gamma is the confinement factor. Tau S is the photon lifetime. Anything else? No. Okay. In order to solve the rate equation, first the steady state analysis is performed. What does it mean? When the steady state analysis enables the calculation of the average carriage and the photon densities. When steady states occur, your derivatives goes to zero, then you can extract your average photon and carrier densities. This is our equivalent circuit. One of the most important advantages of semiconductor lasers is they can be modulated directly. Here is our model. Here is our bias current. Here are our AC RF signal. This is our ideal BSD. BSD here our AC modulating RF signal, and thanks to BSD, it's isolated from DC bias supply. Same like the DC bias is prevented from the modulating signal source. In this inductor, here is the inductor. Inductance imitates wire from RF input to chip. You know, metallic wires imitates inductors at higher frequencies. This is our PET capacitance and losses. This is our laser in-streak model, which we will solve it after this. These are noise we added, and then let me try to solve the equations. It can be observed that the rate of change in carrier density depends on I and S, while rate of change in photon density only depends on N and S. When we use a small signal here, delta I, we conclude our carrier density and photon densities differences delta N and delta S. When we put this our numbers with the here density rate equations, we end up with this the delta N point and the maths you see here. Let's keep it in mind here. These two are important for our small signal analysis. What we do next? We do next is our Kirchhoff law solutions. Here is our model: resistor, inductor, resistor, capacitor. When we put as a delta V, when we input modulated signal delta V and delta E modulated signal, it gives us the Kirchhoff equations here. And then we have a boundary equation here, and we take the derivatives to the time. The boundary equations, here we end up with this. So we have this. Please. Excuse me?
You have 5 minutes left.
Okay, I'm sorry. We end up with this. If you see this and this equation, they are identical in form, and if we match the comparing constants, we can obtain the values of this in-streak model. And if after we extract the model's coefficients, we start simulations. Here, as you see in the graph, we use different bias currents, and we have frequency response reach its peak value for here. At the damped oscillation frequency, it is maximum, and the modulation frequency efficiency decreases rapidly when the modulation frequency is greater than the damped oscillation, which is here 6 gigahertz. Here we have bias current to output power. Conclusion: in this work, a circuit design of semiconductor design is implemented on AWR simulation environment. We obtained the first result, frequency response and bias current over RF power dependency. Our next step is building an RF over system in the lab and comparing the simulating results with the experimental ones. Thank you for your attention, and I can take the questions.
Thank you for your presentation. Let's ask audience if they have any question for our speaker. Okay. I guess we don't have any questions. Again, thank you very much for your time and effort.
You're welcome.
Contribution to the conference.
Thank you.
Okay. Then I believe I can call our next speaker, Fariba Lofti. I wonder if Fariba Lofti has joined. Fariba Lofti is from Tabriz University, Iran, and the title of the talk is a tunable plasmonic sensor-based metamaterial and graphene with high sensitivity. Can you hear us? Fariba Lofti, can you hear us?
Hi, I'm there.
Welcome. So if you could share your screen, we could see your presentation.
Yeah.
In the bottom section of your screen, close to the middle, there's a share screen area. Okay, good.
Okay.
Okay. You can start your presentation.
Yeah. Good afternoon, ladies and gentlemen. I'm Dr. Fariba Lutfi from University of Tabriz in Iran. I'm going to talk about a tunable plasmonic sensor-based metamaterial and graphene with high sensitivity.
Excuse me, you can do full screen? So in the bottom, there's 84%. So next, the one on the left side of 84% written. You can press to make it full screen. Okay, then we can continue this way. All right.
Yeah. This project is collaborated with Dr. Sainurpur from the University of Alberta and Dr. Kharatman from University of Tabriz. My presentation will be in 3 parts, as you see in this slide. The first part is background, is divided to 2 parts. The first part is about surface plasmon polariton, and the second part is about materials. Then in the second part, I'll introduce model and method of our sensor structure. Finally, I'll go on to talk about results and discussions. I want to describe surface plasmon polaritons. Surface plasmon polaritons are electromagnetic excitation that propagate at the interface of a conductor and the dielectric. The capabilities of surface plasmon polariton in the subwavelength confinement of electromagnetic energy at the interface facilitate their application as miniaturized plasmonic devices like sensors. As you see in the figure of this slide, to have propagating species media with positive and negative Electromagnetic susceptibilities like permittivity are required at the interfaces. The skin depth of surface plasma polarity at the dielectric media is higher than the skin depth of surface plasma polarity in the metal media. Surface plasma polarity is sensitive to the electromagnetic susceptibilities like refractive index of surrounding media. So we focus on the refractive index plasmonic sensor. In this slide, I talk about the materials we used in our sensor structure. Our sensor structure is capable to work with different lossy dispersive media with positive and negative electromagnetic susceptibilities, including metamaterials, graphene, and silicon. For the electromagnetic susceptibilities of media, we employed the generalized Lorentz model for media with oscillation strength F and damping constant gamma, and resonance frequency is omega subtitle 0. The generalized Lorentz model for permittivity and permeability is shown in this slide. The electromagnetic properties of graphene are characterized by its surface conductivity. The Cobos formula for graphene surface conductivity is divided to sentence is subtitled with sigma intraband excitation and interband excitation. And another material we used in our sensor structure is silicon. To describe the electromagnetic properties of silicon, we use Sellmeier equation. As you see, the parameter of this equation in the downside of this slide. Then we talk about a model and method. Our sensor structure is based on Mach-Zehnder interferometer. The reason of our choice of Mach-Zehnder interferometer is high sensitive, and manufacturing technology of MZI is easy and low cost. Our sensor structure is composed of 3 layers slab waveguides. The waveguides, our waveguide structure is including lossy dispersive media as cladding of waveguide and lossless non-dispersive media as core of waveguide. In our project, we restrict our choice of material to homogeneous, isotropic, and linear material, and we use the finite element method to solving the dispersion equation of surface plasmon polarity at the boundary of the lossy dispersive media and non-dispersive media. I want to introduce our sensor structure. As you see in this slide, the schematic of our sensor structure. Our sensor structure composed of asymmetric Mach-Zehnder interferometer with different distance, with different widths of up branch and down branch of MZI. The blue area is the dielectric media. We proposed air in this work, and the green area is metamaterial. We imply monolayer graphene in the boundary of dielectric and metamaterial boundary, and the sampling domain as shown by pink area. The sampling domain is near the up branch of MZI, and the sampling domain is restricted by the silicon layer and shown by a gray color. we infiltrate and drain the sample to the sampling domain via pipe. The geometrical parameter of our structure is bring in the downside of the structure. Before I talk about the result and discussion, I add the presence of graphene at the boundary of core and cladding of waveguide facilitate the dynamic tunability in the energy propagation by voltage. In this work, applying gate voltage to graphene the core cladding boundary of the sensor modifies the electromagnetic properties of graphene. The change in the graphene electromagnetic properties shift the transmission peak of the sensor to different frequency and affect the sensitivity of sensor. Our result in divided to 3 parts, A, B, and 3. A is the magnetic field profile of TMSPPs. TMSPP can propagate from 0.01 omega E to 0.06 omega E. Because in the transmission spectra of sensor we focus on this frequency range, the TMSPP can propagate. As you see in the part B, we change the refractive index of a sample from 1.34 to 1.38. And by increasing the sample refractive index, you can see the shift in the transmission spectra, redshift by increasing the refractive index, and by applying a gate voltage to the monolayer graphene in the boundary between metamaterial and dielectric, the sensitivity is higher amount compared to previous results in this area. And I added our sensor structure has applications in liquid and gas chemical sensing, biomedical sensing, aerosol sensing, and environmental sensing, and to detection the pollutant water. I'd like to thank you for taking time out to listen to my presentation.
Okay, thank you, Fariba Lofty, for your contribution to the conference, for your presentation. And I'd like to ask audience if they have any question to Fariba Lofty. Okay, I guess there's no question. Again, thank you for the speaker.
Thank you too.
Thank you for joining us. Then I can probably introduce our next speaker. We have a change of speaker at this time, and our next speaker is Ofelia Balayeva, and the title of the talk is Controllable Synthesis of Nickel Zinc Sulfide Nanoparticles on the base of nickel zinc aluminum layered double hydroxide PVA composite matrix. And I wonder if she's able to. Oh, okay. Welcome to the conference. And if you are ready, you can probably share your.
Okay, I am sharing my presentation. Just a minute. Okay, do you see my presentation?
Okay, it's a little bit small. Can we, I guess we cannot make it bigger, can we?
Wait a minute. What about now?
Yeah, it's better now. It's better now.
Okay.
It's your turn. We are listening. Thank you.
Thank you. Now I'm Balayeva Ophelia from Baku State University, Department of Chemistry, Sub-Department of High Molecular Compounds Chemistry, and I'm also working with Nano Research Center at Baku State University. Other research group at a high molecular compound chemistry laboratory, we work the synthesis of new types of thermotropic and thermochromic polymer nanocomposites, and we obtain also layered structures, layered structured polymer nanocomposites. Also, we are working with metal sulfides, semiconductor transition metal sulfides, and they're nanocomposites by the polymers. And we study all of these compounds properties. Now, I'm going to talk about first. I want to start with semiconductor metal sulfides. We know the nano-sized transition metal sulfides, and these materials are very attractive materials, and they have attracted scientific research interest for renewable energy application, because they have unique optical, physical, and chemical properties. And we can say also transition metal sulfides are also semiconducting compounds. Their sulfur is anionic sulfur associated with the metal, cationic metal, and we can get metal sulfides. And here some effects we can say: heterostructure formation, doping effects, composite formation, defect engineering, annealing temperature effect, and porosity effects that influence affect the physical and chemical properties of the metal sulfide nanoparticles. And there are also morphologies and energies they influence. And there we show them. It's of course literature. I took from the literature, and I showed it at the end of this presentation on the reference. We can show that metal sulfides are useful for the preparation of lithium-ion batteries, sodium-ion batteries, and it's also useful for the oxygen reduction reactions, hydrogen evolution reactions, capacitors, and so on. And these sodium-ion batteries are shown in here, and it's one of the most promising battery technologies. And we can say that these transition metal sulfides that emerge as promising anode materials, and they have advantageous features. They use in electrochemical processes because they're electrochemical redox reactions, and high capacity. It belongs to these compounds. And there are different methods that we describe here. Some methods, Sol-Gill methods, hydrothermal, electrospin, solvothermal, electrodeposition, microwave, and solar methods. There are different methods that are useful for the formation of metal sulfide nanoparticles. But compared to all these methods, the SILAR method, the successive ionic layered absorption and reaction method, it's a very simple and less expensive method and less time consuming method that we used this method in our research too. And we can see also recent advances have demonstrated ternary metal sulfides. They are very promising alternatives to noble metals and because for various electrocatalytic reactions and because their excellent redox reversibility and their high electronic conductivity. And we can also compare these ternary metal sulfides with binar metal sulfides and mono metal sulfides compared with this binar metallic sulfides. Ternary metal sulfides pose more attractive structural advantages as electrocatalysts, photocatalysts, and on the another hand, owing to their relatively low activation energy for electron transfer between cations. These ternary metal sulfides generally pose higher electrical conductivity than bimetallic or monometallic sulfides. In our laboratory, we synthesize nickel zinc sulfides, cadmium, cuprum cadmium sulfides, cadmium zinc, nickel cobalt sulfides. These compounds, the ternary sulfides, are we synthesize on the base of different synthetical and functional polymers. If in VR it's functionalized nitrobutadiene rubber oxidative chlorophosphorylation reaction we took here, and LDH, it's layered double hydroxides that we all know. They are layered double hydroxides. They are famous group of layered materials, and they known as anionic clay, and the formula or general formula is shown in here, and there have a high basal spacing, and there is interlayer domain that we change these anions with another anions. These layers are positively charged, and between these layers there exists anions that are not bonded with the chemically to the these layers, and they bonded low bonded, they physically bonded, and we can change these anions with optical organic compounds, with another anions that organic anions, and we can increase the basal spacing. By this way we can intercalate different compounds that we did also. We can now I'm going to talk about the synthesis of zinc aluminum layer double hydroxides by the different parameters, reaction parameters, and we will show here the reaction parameters, how the reaction parameters and compounds concentration and different agents influence the structure and morphology and next processes. In the experiment, we use zinc nitrate, nickel nitrate. For the next process, we will use nickel nitrate, and for 3 valence metals, we use aluminum cells here, and urea and ammonium citrate we used here for the intercalating process, and sodium hydroxide and sodium bicarbonate we used here for the precipitation process, and polyvinylic alcohol we used here for the stabilizing process. The reactions carried out with the formation of LDHs, zinc oxide and zinc aluminum mixed oxide. We used we use here 3 different methods: co-precipitation, co-formation, and urea hydrolysis method. And in the experiment, we got 6 different compounds. That these compounds differ each other by the reaction experiment parameters. And at the end of the experiment, we got these 6 samples, and we sorry, do you hear me?
We can hear you, but we cannot see your presentation at this moment.
Sorry for it. Sorry, there's a problem by the charting these slides. Okay, I'm crossing to this certain slide.
Finish. You could probably finish up without showing your slides.
Yes, 2 slides are couldn't download. Maybe I didn't understand. Okay. Maybe from the connection problem, I don't know. And okay, sorry for this problem. I can describe the mechanism of this process. I can say that the first reaction, we used a low concentration of base solution, and here we got the pure layer double hydroxides. And at the second process, we used a high concentration of base solution. You can see here sodium hydroxide here is 18 mole, and we can describe that, we can have seen that zinc oxide and zinc aluminum oxide, mixed oxide compounds are formed from this process, and we explain this process because using a high concentration of sodium hydroxide, aluminum hydroxide is dissolved in the reaction system because it's amphoteric. And here high crystallized zinc oxide and mixed oxides formed. And at the end of this reaction, at the third reaction, we here used ammonium citrate, and ammonium citrate helped for the intercalation of the layers. And we can show here 2 XRD patterns, XRD results, X-ray diffraction results. And here you can see the 003 plane here. Peak is at the A figure. It's for the compound that's formed by using ammonium citrate. And at the second figure B, we used urea, but a very low concentration of base solution. And here we can see that the interlamellar distance is increased here. And
Ophelia, you have 4 minutes left.
okay, thank you for telling.
No, you have 4 more minutes.
1 more minute?
4.
4 more minutes. Thank you. Okay, and we the parameters, the structure and optical parameters we calculate. And here you can also see by using urea at a low concentration of the solution, we get the higher basal space. The parameter is 9 and C parameter is 28. It's very high. And the morphology of these compounds we described here. It's flower-like or star-like compounds morphology that's obtained. It's because in the system zinc oxide and zinc aluminium mixed oxide is formed. And now I want to talk about the nickel zinc nanoparticles, that's ternary sulfide compounds. These compounds are formed from the nickel zinc aluminium layer double hydroxides. And here we chose this template to get a pure structure, high crystallized structure. And here nickel zinc aluminium layer double hydroxides give its structure and its some parameters to the ternary sulfides. And in this process, we use 2 methods, Silar and sulfuration of oxides, especially Silar methods. We get we calculate the band gap energy, and this the obtained ternary sulfides nanocompounds show low band gap energy. That's good for the degradation process. We even check this photodegradation of compounds in the laboratory. And here is shown the XRD analysis of these compounds. We can say that the ternary systems, nickel zinc S ternary systems, is formed from the reaction, and that's shown on the XRD results.
Okay.
Thank you very much.
Thank you very much for your contribution, for your work and sharing your work with us. Let me ask if there is any question for you from the audience. And I do not see any questions. Again, thank you very much for your contribution.
Thank you.
Nice talk. Okay, let's move on to our next speaker, Ali Kodayari from Department of Chemistry, Faculty of Science, University of Guilan, Iran. And the title of the talk is Silver Brom MIL 53 Aluminum Plasmonic Nanocomposite as an enhanced visible light photocatalyst for the composition of rhodium brom dye, rhodium bor dye. I believe he's not with us due to technical difficulties, but we believe we have his presentation video recorded, and I would like to ask host to upload his recorded video. Okay, we can start.
The title of this presentation is MIL-53 Aluminium Silver Bromide Plasmonic Nanocomposite as an enhanced visible light photocatalyst for the composition of rhodamine with dye, that presented by Ali Kodayari. In the past decades, we have witnessed appearance and development of various environmental contamination, such as industrial wastes, textile dyes, pesticide, weed killers, and detergents, which are a serious menace to human, animals, and plants living organisms. There are many techniques that could be used to eliminate these pollutants from air and water. However, most of them involve time-consuming and costly physical, chemical, or biological processes. Photocatalyst processes have been widely applied as an eco-friendly technology for advanced oxidation, photodegradation of dyes, and other organic pollutants. Visible light-driven heterogeneous photocatalysts were used to convert light energy to electrochemical energy. Plasmonic photocatalysts have attracted attention for their effective light absorptivity in the near-infrared and visible regions. These photocatalysts work on the principle of surface plasmon resonance, or SPR, the phenomenon in which the collective oscillation of free electrons on the surface of certain metal nanoparticles, such as gold, silver, and copper, are detected using polarized light. Metal organic frameworks, or MOFs, are described as crystalline coordination polymers consisting of metal clusters as secondary building units, linked by multifunctional organic spacers. The strong metal ligand covalent bonds in MOFs lead to formation of three-dimensional network with the same cavity shape and regular pore size. MOFs have many notable features such as high adsorption affinity, large surface area, permanent porosity, and desirable functionality. Metal organic frameworks have been successfully applied in chromatography, sensing, storage, and separation of gases, drug delivery, and photocatalysis. However, the photocatalytic activity of most metal organic frameworks is commonly restricted due to their wide bandgap and rapid recombination of photogenerated electron-hole pairs. Hence, composition of chromophores and light-driven semiconductors with MOFs are among major strategies to enhance the photocatalytic capability. Another solution is fabricating MOFs using functionalized organic linkers, which make the absorption band shift to the visible regions. In this situation, the promoted electrons can transfer to the metal oxide clusters, preventing electron-hole recombination. For hydrothermal synthesis of MiL-53 aluminum, a mixture of 25 millimole aluminum nitrate and 13 millimole benzene dicarboxylic acid and 36 tannous water after mixing and stirring was placed into a Teflon-lined stainless steel autoclave and heated at 220 degrees centigrade for 3 days under autogenous pressure. After cooling down to room temperature, the white salt products was obtained by centrifuge and then washed 3 times with tannous water. The asynthesized MiL-53 aluminum was dried at 70 degrees centigrade overnight. Finally, the unreacted and excess benzene dicarboxylic acid absorbed in the pores was removed by heat treat and 400 degrees centigrade for 1 day. To prepare 1 gram MiL-53 aluminum silver bromide containing 28% silver bromide, 0.8 gram of the MOF was sonicated in 50 milliliters deionized water for 30 minutes. Then 0.20 gram of silver nitrate was added into the MOF suspension and vigorously stirred for 30 minutes. Afterward, a solution containing 0.40 gram of sodium bromide and 20 milliliters of deionized water was added twice into the suspension. After refluxing for 2 hours, the suspension was cooled down to room temperature. The obtained precipitate was centrifuged and washed 3 times with deionized water and then dried at 80 degrees centigrade overnight. The photocatalytic ability of plasmonic nanocomposite was studied by removing rhodamine bit dye from aqueous solutions. The initial concentration of dye was 10 ppm. In each test, 50 mg of the photocatalyst was added into 100 ml of dye solution in dark condition and stirred magnetically to attain an adsorption-desorption equilibrium. Then, immediately photocatalytic experiments were carried out under LED light illumination. A 20-watt LED lamp with 466 nanometer dominant wavelength was used at the top of the reactor at the distance of 10 cm as the visible light source. The light intensity at the source of the experimental solution was 100 kilolux as measured by a luxmeter. To track the progress of the photocatalytic reaction, 5 ml of the mixture was sampled, centrifuged, and analyzed using UV visible spectrophotometer. The survey XPS spectrum shows the presence of aluminum, carbon, oxygen, silver, and boron in the plasmonic nanocomposite. In the high-resolution XPS spectra of silver 3D orbital, the peaks at 367.9 and 373.9 electron volt are ascribed to the silver cation from silver bromide, and weaker peaks at 368.6 and 374.6 electron volt belongs to the metal silver nanoparticles. The high-resolution XPS spectrums of other elements revealing the successful synthesis of nanocomposite. Scanning electron microscopy images show MiL-53 aluminum has been synthesized in the form of layered semi-cubes with irregular crystalline shape. The thickness of layers are about 50 to 60 nanometer in some area. In the SEM image of nanoparticle, the observed quasi-spherical particles can be related to formation of silver-silver bromide clusters on the surface of MAO. As shown in HRTM image, the lattice spacing of 0.236 nanometer can be ascribed to 111 plane of cubic phase for metallic silver, and the spacing of 0.288 nanometer is in good accordance with the 200 lattice plane of cubic phase for silver bromide. The results confirms the formation of heterojunction between MiL-53 aluminum and silver-silver bromide nanoparticles. The optical properties of synthesized samples were explored by UV visible DRS spectra, and results were illustrated in this slide. The energy band gap of the samples were estimated according to the Tag equation. As it can be seen in figures, the absorption age of the pristine MAF is around 340 nanometer, corresponding to energy band gap of 3.65 electron volt. The large band gap in the MiL-53 aluminum might be due to the low electronegativity of aluminum cations that requires more energy to transfer charge. In DRS spectrum of silver-silver bromide, the absorption age of silver bromide about 476 nanometer and the broad absorption peak at about 550 nanometer are observed. The peak at 550 nanometer corresponding to distinctive SPR absorption of metallic silver in the silver bromide structure. Energies of conduction band and valence band of MiL-53 aluminum were measured from Matschatzky plot. In the Matschatzky plot, the flat band potential was determined from extrapolation of 1 divided by C squared to the potential intercept, in which C is the capacitance of space charge and obtained from electrochemical impedance curves. As shown in figure, The Matschatzky plot of the MAF has a positive slope and induced to typically N-type semiconductor. Besides, the flat band potential of the MAF is about minus 0.6 electron volt versus AgCl reference electrode, corresponding to minus 0.39 electron volt versus NHE. It has been already proved that the flat band potential of N-type semiconductor is about 0.1 electron volt lower than the flat band potential. Therefore, the energies of conduction band of the MIL53 aluminum was calculated as minus 0.49 volt, and energy of valence band was measured as 3.16 electron volt. Based on Mulliken electronegativity theory, the energies of conduction band and valence band of silver bromide are minus 0.06 and 2.54 electron volt versus NHE respectively. In order to assess the silver-silver bromide effects in the photocatalytic efficiency of nanocomposite, the PL spectra of MAF and nanocomposite were provided. It is clear that the intensity of the PL emission for nanocomposite is notably lower than the bursting MAF, which is related to the lesser combination rate of electron-hole pairs in the nanocomposite. On the other hand, due to longer lifetime of the photogenerated electron hole in the nanocomposite, this photocatalyst can have an effective precipitate in the photodegradation reactions. As presented in this slide, the photocatalytic ability of the synthesized nanocomposite was compared with that of prepared MAF and silver-silver bromide for degradation of rhodamine B under visible light irradiation. Before the photocatalytic process, in order to obtain an absorption-desorption balance, the photocatalyst and rhodamine B solution were stirred in a dark place for 30 minutes. It is apparent that photocatalytic performance of nanocomposite were enhanced due to the presence of silver-silver bromide nanoparticles in photodegradation of rhodamine B under visible light. On the other hand, the nanocomposite showed the best activity and eliminated 94% of the rhodamine B within 2 hours. Kinetics of photocatalytic degradations was obtained from experimental data and was fitted upon a first-order reaction. The K subscript up stands for appeared rate constant. The K up for photodegradation of rhodamine B hour nanocomposite is which is around 2 and 8 times higher than those of our silver-silver bromide and pristine MAF respectively. Hence, the heterojunction between MAF and plasmonic silver-silver bromide nanoparticles provides some advantages, including good light absorption, facile electron hole separation, and rapid transfer of the generated species for their further precipitation in the photocatalytic reactions. Practical quenching experiments were carried out to explore the portion of reactive species in photodegradation of rhodamine B hour nanocomposite. For this purpose, photocatalytic experiments were performed by addition of benzoquinone, isopropyl alcohol, and ammonium oxalate as scavengers for trapping of superoxide anion radical, hydroxyl radical, and whole species respectively. As shown in figure, inhibition sequence is as follows: benzoquinone, ammonium oxalate, isopropyl alcohol, suggesting superoxide anion radical had the main role in the photocatalytic degradation of rhodamine B over nanocomposite. Therefore, according to the energy levels of silver-silver bromide and MIL53 aluminum, and based on radical quenching experiment, a schematically illustration of possible mechanism for photodegradation of rhodamine B over plasmonic nanocomposite is depicted in this slide. In this research, MIL53 aluminum silver-silver bromide nanocomposite was synthesized as a novel plasmonic photocatalyst and characterized. The photocatalytic efficiency of nanocomposite was investigated by photodegradation of rhodamine B dye. Results indicated about 94% of tested dye was removed by nanocomposite under LED light irradiation in 2 hours. because of heterojunction between the plasmonic silver bromide nanoparticles and MiL53 aluminum. The nanocomposite showed high photocatalytic ability. The results confirmed that due to some notable features such as high surface area, surface plasmon resonance effect, and good chemical stability, the introduced nanocomposite acts as a high-performance photocatalyst for degradation of some organic pollutants in organic solutions.
On behalf of organizing committee, I'd like to thank Ali Kodayari for sharing his work with us. Our next speaker is Alparslan Bayraktar. He's from Vocational School of Higher Education for Healthcare Services, Iğdır University, Turkey. The title of his talk is Investigation of Structural Properties of Bromine Azocalyx RNA Molecule using DFT method. I believe due to the technical difficulties, he's not with us at this moment, and we are going to share his recorded talk so we can listen his talk. If we are ready, we can share his recorded talk. Yes, we can start right now.
Hi everyone. Thank you for coming my presentation. And my name is Alparslan. I will give you a presentation on the theoretical investigation of the structural and spectroscopic properties of the bromine calixaran compound using the DFT method today. In doing so, we will compare the theoretical results with the experimental results from time to time. Let's get to know the calixarans. Molecular structure of calixarans are characterized by a wide upper rim, a narrow lower rim, and hydrophobic space in the middle, as shown in figure 1. In this work, bromine azocalixarans from calixaran family, which has a cyclic structure and is known for its ability to carry and complex organic molecules, anions, and metal cations, was investigated theoretically. The theoretical studies were carried out using by Gaussian O9W package program and Avogadro molecular modeling softwares. Our main aim in this study is to theoretically calculate the structural and spectroscopic properties of the bromine calixaran molecule and compare them with experimental results. The question we look for the answer to: can theoretical studies direct experimental studies? Next step, optimize the structure. The bromine calixaran compound was optimized with DFT B3LYP level and 6311 GDP basis set to determine the most suitable geometry of the molecule, which will form the basis of theoretical studies on the molecule. When the calculated optimized structure was examined with the molecular visualization program, it was seen that 4 hydrogen bonds were formed in the molecular structure. In figure 2, the optimized structure of the title compound calculated theoretically with the DFT method is given. In addition, with the help of molecular imaging software, 4 hydrogen bonds in the molecular structure are shown in figure 3 more closely. And then, since we don't have experimental data on the optimized structure, the calculated parameters were compared with another similar calixaran compound. In table 1, the average bond lengths of the optimized structure obtained as a result of theoretical calculation are compared with the literature. The data of hydrogen bonds calculated in table 2 are again compared with the literature. It can be seen from table 1 and table 2 that the experimental data and theoretical data are compatible with each other. The next slide will be about IR spectrum data. Yes, for the infrared spectrum data studies, in the first step, using the optimized structure parameters, the infrared spectrum is calculated by the DFT method. And then the discrepancy between the values calculated in the second step and the experimental values, which is due to the phase difference in which experimental and theoretical studies were carried out, was multiplied by the theoretical infrared values scaling factor to eliminate. Finally, about this slide, as seen in figure 3, the fact that the OH band peak at 3234, the experimental infrared spectrum is not sharp, but broad proves the formation of hydrogen bonds in the compound. This confirms the theoretical work. Now we talk about table 3. Experimentally observed and calculated wave numbers of some modes are assigned by PET analysis and given in table 3. On the next slide, we will look at the correlation between experimental data and scale theoretical values. The graphic expressing the correlation between the calculated wave numbers and experimentally observed ones is given in figure 5. As seen in the graph, the correlation values was calculated as 0.9996. Also, hydrogen NMR study has been done for the title molecule. NMR spectroscopy is one of the most effective spectroscopic methods used to explain the chemical structure of a molecule. Experimental and theoretical hydrogen NMR study has been performed to elucidate the structure of the bromine calixaran molecule. The experimental and theoretical data obtained are given in table 4. At the same time, the correlation graph between these data is drawn and shown in figure 6. As seen in the figure 6, the correlation values was calculated of 9748. Conclusions. The 6 to 311 GDP base set. Theoretical hydrogen magnetic isotropic chemical shift values with respect to TMS is reported and compared with experimental data showing a very good agreement hydrogen NMR. And it is seen from the correlation graphics. Correlation values for infrared and NMR spectra were found as 0.9996 and 0.9748 respectively. These results clearly state that the theoretical results are reliable and can guide experimental results. I apologize to you for my mistakes I made during the presentation. Thank you so much.
I'd like to thank our speaker, Alparslan Bayraktar, for sharing his work with us. Our next speaker is Cenk Ceylan from company Göktürk Bilgi Teknolojiler R&D Center. And the title of his talk is The VC Cell Solid State Laser is Photonic MEMS and their several applications in 3D time-of-flight LiDAR. Thanks for joining us. If you could share your presentation, share screen so we can see your presentation. Okay, so it's your turn. We are listening.
Good afternoon. Welcome to my session. Hi, hello, bonjour, privet, shalom, and merhaba, yasru for international participants. Dear participants and organization committee, academician, and scientific researchers, welcome to my session. My short view for RD Center startup project for working and 5G research and optical component production, but only startup company. The laser is acronym name, all researcher and academician. Light amplification simulated emission radiation. My definition, the laser is direct light from coherent photon array. Laser is the figure. First experimental setup. Left figure is xenon vacuum tube for energy pump. Right figure verilmiştik yakut crystal, meaning ruby crystal for all Turkish man corona crystal, maybe you know. First inventor laser Theodor Meinmann, American inventor, but in same time German and Soviet Union researcher for about the laser. Telephone kind, Siemens, lights, cars, for laser market. And MEMS micro electromechanical system. All VXL laser in MEMS technology. VCSL laser, vertical cavity surface emitting laser, very innovative technology because very small and very fast laser, and technology in right top quantum well strategic technology, and aluminum arsenic, gallium, aluminum nitrate, all wafer between, all academician. LiDAR is permanent production, laser imaging detection and ranging. LiDAR is all of them included. Kind of laser, mirror, or reflector, inertial measuring unit for photon counter, and camera, and time of flight calculation. Just a moment to have a short video.
We cannot see your presentation.
Okay, we can,
Not yet. Media, playback.
Okay.
Yeah, we see it, yes. We can start video. Could you increase the volume a little bit? We cannot hear the volume. Could you increase the volume?
Sorry?
We cannot hear the volume of your video.
Oh, okay. Sorry.
Could you increase the volume a little bit?
Okay, just a moment.
A little bit better, but if you could increase more, it would be better.
Difficult to install or unreliable.
Okay, so
Solid-state LiDAR with MEMS and 1550 nanometer laser technology has the advantage of better resolution, longer distance, more reliable, and more cost-effective. MEMS is one of the mainstream directions of solid-state LiDAR. New Vision is one of the earliest pioneers and developers in MEMS and 1550 nanometer LiDAR technology to power better vision for smarter future. With many years of development and some pretty serious engineering, New Vision offers high-end LiDAR sensors and many software solutions for innovative application scenarios around the globe. New Vision LiDAR is very well accepted and welcomed by customers. The industry-leading high-resolution 480 to 700 lines, advanced machine vision, long effective detection range up to 600 meters. For autonomous driving, safety first. It needs to see more, further, and to recognize what it is seeing. New Vision LiDAR's higher resolution and longer range allow identifying danger further away. It gives the system a long time to respond and provides better safety. V2X transfers part of the perception ability from the vehicles to the roadside system. New Vision LiDAR Solutions has roadside systems provide environmental information for the vehicles through 5G and other communication methods with minimal latency. Any tiny foreign object on a train track is a serious danger. 600-meter detection range and 700 lines high resolution of New Vision LiDAR allow better railway transportation safety by detecting small objects from as far away as possible. Welcome to New Vision.
Okay, other MEMS and LiDAR sample. Okay. You can see my presentation?
Yes, we can see it.
Okay. LiDAR production very important because industrial robotic arm driving, artificial intelligence, FMG sector, counting by object. LiDAR choice mechanical LiDAR. This MEMS LiDAR after, for example, Intel LiDAR flash lidar technology is very different. Beamforming for interference, object, photon reflection, and beam, and near mechanical lidar, mainly hybrid lidar. And important angle for lidar, mass lidar angle, field of leading angle. This lidar subject, you know, all academician. Who is lidar millionaire man? This important man, the 25-year-old millionaire building Stanford student, Luminar company, for startup company, but loans and grant funding, very big company now. Other lidar several application, very important project, Subaru telescope, guided light interferometric imaging technology, because observation, galactic observation for science. Other application, free space optic, very old historical technology. Before first photo phone, you know, maybe Bell and assistant training, and second production, German production, Blink Gerät for flash lamp Gerät for cryptography in the communication for bar. Other last production, optical inter-satellite link communication terminal, very important production because long range communication, 10 gigabit per second free space optic, same production, GPON, gigabit passive optic network production. Other several application, early net for climatization observation, and lidar calibration station, right figure, and observation map, ISO map implementation. And lidar, MEMS lidar very developing, but observation range, low range, and maybe lidar defense sector. Conclusion, it is my dream, single dark photon from memories. It captures with covered crime evidence, with MEMS galactic solid state telescope beaming, maybe for the sky and space, quantum engagement in hydrogen wind, the future. Okay.
Okay. Thank for your presentation. I would like to ask if there is any question for our speaker. Okay, I have a question. Actually, are you still in the process of research and development, or how far you are in the research and development? Are you close to have a production?
Only concept production, because laboratory building very expensive, 5 million euro funding.
Okay, all right. Thank you for your presentation. It was very nice
Okay.
to hear what you are dealing with. Thank you very much.
Thanks.
Okay. Then we can move on to our next speaker, Ataur Rahman Shervani from Department of Physics, Istanbul University, Turkey. And the title of his talk is Optical Sense of Anti-Cancer Drug
Doxorubin.
Sorry for my pronunciation, on 10 nanostructures. Okay, so if you could share your presentation, and microphone is yours. We are listening.
Thank you. I'm trying. Share screen. Can anyone see? Can everybody see?
Yes, we can see it. If you could make it full screen, that would be
Yes, of
better.
course. Is it good now? Okay. So my name is Ataur Rahman, and today I'm going to be giving a talk about the optical sense of anti-cancer drug doxorubin on PANI nanostructures. So we know that the drug dox is a drug normally used to treat cancer patients. So basically, in this study, we try to develop a material which can be used as a biosensor for detecting very low concentration of dox, or it can be used as a drug delivery agent. So for this purpose, we utilized a hydrophilic, a very low toxic, chemically stable biocompatible material, that is PANI polymer. This is actually an initial study to see whether the PANI polymer is a suitable candidate for drug loading of dox. This is going to be a very short presentation. So I will first discuss a little about the background on how these flexible biomaterials are produced. Then I will talk a little about the experiment, how it was done, how we did it, and lastly about results and analysis. So this here, you can see a schematic which shows that how the basis of how we can make an molecular imprinted polymer films. Basically, these MIPs, or molecular imprinted polymer films, are the biocompatible materials which can be used as biosensors or as a drug delivery agents. So basically, first of all, a solvent is used, which is called a progenic solvent, which constitute all these materials inside in a dissolved form, such as the functional monomers, the molecular cavity, cross-linkers if necessary, and the template molecules of which the molecular imprinted polymer is being made. And all these constitute then forms of polymer matrix over a electrode, over a suitable electrode surface. This can be done through various techniques such as bulk imprinting or surface imprinting, etc. The one that we used is the electrochemical polymerization. So what happens is that all this solution is mixed in a beaker where the electricity is conducted, and the film is then electrode deposited over the electrode. And we can actually control the thickness of the films by the charge transfer of the system. Also, we can change the surface morphology by our surface morphology or the porosity of the produced polymer matrix by controlling the solution or the supporting electrolyte concentration or the suitable solvent concentration. After the formation of this polymer matrix, we can remove these template molecules, and we can use this as a drug sensing compound or material, such as a biosensor. And this can be done with the big help of these many different techniques, such as potentiometry, chronoamperometry, etc. So basically what we did here is we use the same principle to create a polymer matrix of PANI over a transparent conductive electrode that is PET coated Ito for DOX molecules. Before I go for any further, I would like to talk a little about our PANI. So we can see here the basic structure of a polyaniline molecule polymer. So it has, you can see there is an NM. This corresponds to the reduction phase of the aniline monomer. Actually, this is the aniline monomer, and it is the reduced form. And this is here the oxidized form. And based on the number of the oxidized and reduced monomers in the polyaniline structure, it can be, it is present in actually in 3 states. leucoemeraldine base form, the emeraldine base form, and the pernigraninal base form. So if it is completely reduced, the polymer structure, polymer structure is completely reduced, it is called the leucoemeraldine base form. And if it's completely oxidized, then it's called the pernigraninal base form. And when it's 50-50, that it is 50% oxidized, then it's the emeraldine base form, and it is the most conductive form of polyaniline. And we can also increase the conductivity of this polymer by doping it with electropolymerizing the polymer in a acidic medium, and that induces protonation in the compound, and thus these are called the salt forms of the same compound, the emeraldine salt form. So in our this we can see here a setup of our system. It's fairly easy setup. A 3-electrode system is used to make this polymer matrix of molecular imprinted polymers. The 3 electrodes that can we see here is, one is the working electrode, over which the monomers are oxidized to form polymer. Then there is the counter electrode to complete the circuit, and a reference electrode is used against which the potential is measured. In our experiment, the PET coated etho was used as a base for the PANI polymerization and was used as a working electrode. The electrolyte of this solution contained an ionic solution of potassium chloride, and aniline was used as monomer, and a mixture of activated carbon was used as cross linkers for DOX molecules. Platinum mesh was used as a counter electrode, and a silver chloride electrode was used as a reference electrode. So the electropolymerization was done through cyclic voltammetry. As we can see here, the electrochemical synthesis of this aniline monomer was done by sweeping a potential between -0.2 volt to 1.2 volt against the reference electrode, which is the silver chloride. The scan rate was optimized accordingly. In the end, a greenish thin film of the PANI polymer was deposited over the electrode, which is the emeraldine state of the polymer, which is the most conductive form. So we see here, firstly, that there's actually 2 regions of redox potentials, one from 0 to 0.6 volt, and there's another region between 0.8 to 1.2 volt or 1.5 volt, 1.15, something like that. So this region here is the region in which the most reduced form of PANI polymer, that is the leucoemeraldine form, is oxidized to a radical ions, where here it goes to form emeraldine, and then further it goes to take the form of this third form, which is the pernigraninal form. Actually, there are 2 peaks here, but because the potential is quite near to each other, it's showing as a single peak here, redox potential here. And we can see that as the intensity, as the peak cycles are increased, the current density is also increasing here in this cyclovoltammetric analysis. The aniline monomer actually exhibits electrochromatic behavior. So within the low potential region, it is yellow in color, then it goes to green, and then goes to blue at higher potentials. So what we did was, the main aim was to first to synthesize the most conductive form of PANI polymer, and with using the same condition, we used the activated carbon molecule with DOX molecules in the same system to make a molecular imprinted polymer, and then we took the analysis further. Now, to check whether the polymer that we fabricated was in
We cannot hear your voice. Something happened. Can you hear us?
Can anyone hear me? I think.
Yeah, now I can hear.
Okay. I think something happened now. So to confirm the MLT state of Pani, X-ray diffractometry was used. The peaks around the 19 degree and a 25.5 actually exactly. That can be attributed to the Pani emerald state. PET, because of its low crystallinity, some degree of crystallinity, it has also some peaks here around 25 and around 35 here. You can see here, and around 45. These are related to PET, and the rest of the peaks are related to the Ito compound. We see a shift of peaks around the 25 for the samples which were coated with Pani, which showed that the Pani was fabricated successfully. Also, we did the Raman spectroscopy to further support the claim and of the emerald state of Pani polymer, and we see that there were strong bands around 414, 812 something, and 112 1.5, this band here, and 15359 here, and 1464, 1632. These are the bands for the emerald state of Pani polymer. Other bands are can be attributed to PET polymer. So this was here to support that the polymer that we fabricated was of emeraldine state. In the next, we wanted to know whether we were able to successfully able to fabricate the DOX molecule in the polymer matrix. So we did the UV visible spectroscopy, and first we just did the spectroscopy, took the results of the DOX layer over PET Ito substrate, and we found that there is an absorbance. There is a peak at 490 nanometer. This is because DOX molecules causes a fluorescent effect in the visible region around 400 to 570 nanometers, and this peak was according to the literature as supported by the claims in literature. So we also did the absorbance spectra for Pani polymer also, and it has some strong peaks around 335, around 390 to 410 nanometers, and above 850 nanometers. And then at the last, what we did was compare the results of Pani with DOX and activate carbon on PET Ito substrate, and we see that the Pani was there. And also there was a peak at 547 nanometer, which was attributed to DOX molecule. There is a big shift of this DOX molecule from 490 to 547, and this can be attributed because of some proteinated amino molecules of DOX molecule in its structure that cause this giant shift. So in the end, actually, this was actually an ongoing study, and we are still currently in the process of knowing the drug release of capabilities of this structure. So in conclusion, what I say is that we were able to show that we can use Pani with active carbon molecules to load DOX molecules instead of using two-dimensional carbon structures such as graphene or carbon nanotubes for drug delivery systems. And that's it. Thank you for listening.
Thank you for sharing us your recent work with. Thank you for sharing your recent work with us. Let me see if there is a question. Okay, there's a question from Gökhan Gözlekçi. He says, I wonder the answer of this question. Shifting on XRD spectra can affect you on the grain size. Can you hear us?
Yes, I can. Actually, we didn't check the size of the grain particles for that spectra, but for that we need to confirm it through visually also. We didn't, how can I say, calculated the grain size for this structure right now. So as I said, this is an ongoing study. It's still not finished. So maybe we will see in the future whether it's affecting the grain size of the polymer or not.
Okay, thank you. I believe that's it. We don't have any other question. By the way, Gökhan Gözdekçi, I apologize. You had another question for the previous speaker. I missed your question at that time. Sorry about that. Okay, let's move on to our next speaker, Sima Aliloy from Tabriz University, Iran. And the title of the talk is FDTD simulation of propagation of Hermite-Koch Gaussian high-intensity laser beam in inhomogeneous plasma and modeling of ponderomotive force and magnetic field. And hi, Shima, welcome. And
thank you.
Could you please share your screen with us?
Evet, share screen. It is good?
Not yet. Yeah, it is good. So you can make it full screen?
Yes.
Okay, microphone is yours. We are listening.
Hi, I am Sima Alilu from Tabriz University, and I'd like to talk to you about FDTD simulation and propagation of Hermite-Koch hyperbolic Gaussian high-intensity laser beam in inhomogeneous plasma and modeling of ponderomotive force and magnetic field, which is the result of my work and that of Dr. Shahrasai. The purpose of the presentation is the field of nonlinear optics is one of the most prominent developments. My talk is divided into 4 parts. I start with instruction, then I will look at simulations and calculations, and finally analytical and simulations results. As you are all aware, laser plasma coupling is an immense research topic amongst various research groups worldwide because of its significance in various applications including inertial confinement fusion, ICF, supercontinuum generation, X-ray lasers, and acceleration of charged particles. On the other hand, a variety of mechanisms capable of produce large and small scale magnetic fields in plasmas have been proposed by including temperature gradient in plasma, the ponderomotive force of the laser pulse, inverse Faraday effect noncollinear density, Biermann battery effect, and etc. FDTD is the gold standard for modeling in nanophotonic devices, processes, and materials. For this reason, in this paper, both theory and simulation based on FDTD are used, which are complementary to each other. To sum up, the following describes the propagation of the Hermite-Koch hyperbolic Gaussian beam electric field in inhomogeneous plasma and discusses the magnetic field, the nonlinear ponderomotive force. Simulations and calculations. The defined source of the Hermite-Koch hyperbolic Gaussian electric field propagates vertically in the plasma, which is defined as equation 1. In the relation, Hn or Hm are Hermite polynomials and omega step defined in the form B divided by the laser frequency when B equal 1. That is in relation 2. By placing M equal 1 and N equal 1, the electric field becomes the relation 3. Using Faraday induction law, that is equation 4, we can calculate the magnetic field from the electric field mentioned. Finally, the magnetic field is obtained by deriving from the electric field in the form of relation 5. Panematic force. When an electromagnetic wave, such as a high-power laser, propagates in plasma, it acts on it via a nonlinear force known as panematic force. Panematic force is obtained by relation 1. When E is an electric charge and M is the mass of electron or ion, and E is the electric field. By placing Hermite cosinus hyperbolic Gaussian electric field, whose Hermite polynomials is M and N equal 1, in relation to the panematic force, equation 2 is obtained. In which case the refractive index of non-collision plasma is defined by relation 3. In this relation, omega is the laser frequency, n is the electron density, n0 initial electron density, and omega p is the plasma frequency. In relation to placement, we have that epsilon equal 1 minus n0 divided by n. If the plasma density profile is inversely linear, that means 1 divided by x, and place it in the relationship refractive index of non-collision plasma, equation 5 is obtained. Let's now turn to analytical and simulation results. In the simulation of the paper, the numerical program is used to simulate an FDTD, which is 2 dimensions, plasma with dimensions of 3 times 3 micrometers. We can see the intensity of the electric field, which is in the form of a Hermite cosinus hyperbolic Gaussian beam in 2 dimensions. The resulting electric field intensity actually has 4 peaks. In the following, we see intensity of electric field penetration inside inhomogeneous plasma in axial direction xz. With the 2 dimensions inverse line density profile in figure, when the maximum value of the electric field at the point z approximately equal plus or minus 0.75 is 0.735 volt divided by micron. We see in another figure intensity of magnetic field penetration inside inhomogeneous plasma and axial direction xz. When the maximum value of the magnetic field at the point z approximately equal 0 is 9.08 times 10 to the power minus 3 Gauss. If you look at this figure, you can see that the given magnetic field is perpendicular to the electric field. We observe the pi2 phase difference between the magnetic and electric field. The phase difference between the normalized electric and magnetic field is 1 dimension. I think the graph perfectly shows how where the intensity of the electric field is maximum, the intensity of the magnetic field is the minimum. Another significant point is that the considered plasma has a density index of the form 1x. So with the penetration of the Hermite cosinus hyperbolic Gaussian beam into the inhomogeneous plasma, we will have phenomena such as reflection, transmission, absorption, and so on. Let me use a graphic to explain this. We see the behavior of the panematic force in this figure, which change periodically. The effect of the panematic force is very small due to the weight of the ions, but high for the electrons, which have a lower mass. Conclusion. In conclusion, let me sum up my main points. We investigate the interaction of Hermite cosinus and hyperbolic Gaussian beam with inhomogeneous plasma with variable density profile. We observed and compared the behavior of magnetic field, electric field, and pneumatic force. Simulations for this topic have been performed by using a FTTD method. In conclusion, for high-intensity Gaussian laser plasma interaction, we have observed that the results from the simulations are in good agreement with an analytic calculation implying thanks you all for listening. It was a pleasure being here today. That brings me to the end of my presentation. Thanks for your attention.
Thank you, Shima, for your presentation. And I would like to ask audience if they have any question for Shima. Okay. I don't see any question at this moment. And I'd like to close the session. Session 3 ends here. And we have a coffee break until 4:30 p.m. And after the coffee break, we'll with you. Okay? Have a good afternoon.
So, how was Turkey? So Turkey was... Wow. Yes. So, how was Turkey? So Turkey was... Wow. Yes. So, how was Turkey? So Turkey was... Wow. Yes.
Good afternoon, everybody, and good morning in the United States of America. Professor Dr. Evren Mutlugul, are you here?
Yes, I'm here.
Yes. Thank you. Nice to meet you. I would like to give the stage to Professor Dr. Mutlugul from the Department of Electrical and Electronic Engineering from Abdullah Gül University, Kayseri, Turkey. Please.
Yes, thank you so much. So I'll be hosting this chair on behalf of the committee. So once again, welcome everyone. So I hope this is a great start of the day for our meeting. And for the ones who are attending from Turkey, I mean, good evening to everyone. So we have 4 nice talks followed by on each other, and we'll be starting with the first plenary speaker of today, Professor Kevin Eliseri. So I'd like to have a very short intro to him. So he's an internationally known expert in the advanced light microscopy in the Laboratory of Optical and Computational Instrumentation, LOCI, in the Graduate School of College of Engineering at the University of Wisconsin-Madison. And he's also a principal investigator in the Morchett Institute for Research. And the mission of the institute is to develop advanced optical and communication techniques for imaging and experimentally manipulating the living specimens. So without further ado, Professor Kevin.
Well, thank you so much for the kind introduction and the invite. Can everybody hear me okay?
Yep.
Great. Well, I wish I could be there in person, but I'm delighted that I could join remotely. Hope you all are staying safe, and please ask any questions you have as I talk right at the end. So my talk will be about computational optics for studying the cellular microenvironment. I'm an engineer who builds microscopes and software, but my biological rationale is trying to understand the role the microenvironment plays in disease. The same way the microenvironment affects all of us, you know, the temperature of the room lights, friends visiting, good food, sleep. These are all microenvironment variables. The same thing is true of cancer. And during most of cancer imaging and other diseases as well, we've largely ignored the microenvironment. And only in the last 5 to 10 years have we appreciated it and tried to develop approaches to look at it. And one of the rationales for this is shown here on this image here, where you can see a cancer cell crawling along collagen fibers to escape a tumor and invade the lung. So in this case, going from breast to lung. And that's the power of imaging, is that you can see a single cancer cell tightroping along a metastatic highway. And so I'll be talking today about these techniques. My email is there. Please email me. I'm very responsive to emails, and I love to chat. And then also my webpage if you have questions. So disclosure, I am involved, co-founder of a company called Onloom, which is a company that is making a fluorescence guided device that it would be its own optics talk. It's kind of interesting, a simple idea, powerful, that we blink the room lights so fast that your eye can't see it and you think the room lights are always on, but the detectors can actually image in the transient period. So it allows us to do low light fluorescence in the clinical room. I won't talk about that today, but some of the technologies I'm talking about are relevant to that. And this is now FDA approved and is commercialized. So I want to talk a little bit about my lab, what we do, and I'm going to highlight what we're going to talk about. I won't have time to talk about everything we do, so there'll be some things in here that are just overview and not in detail. But I developed microscopes, and increasingly we call them optical instruments because we're moving past the form factor of a microscope. Increasingly, we're looking at microscopes that are very small and compact, in many cases, instruments that have no eyepieces. So that's why we call it optical instrumentation, and also looking at endoscopes like many in fiber-based systems. And my fascination is beyond cancer. I'm interested in wound healing, which is a very universal disease that could be everything from diabetes to a cut to a burn to cancer. And I'm fascinated how the microenvironment is hijacked or can fight wound healing. So in some cases, a wound healing like cancer, we have evidence the microenvironment can be conspired to be part of it, or in other cases, we've seen that it actually can be an active fighter against it. So one of the technologies we have is intervital imaging, where we do live imaging. I'll show you examples at the end where we actually can look live in the animal. We also are increasingly doing big montaging, particularly for interest in being relevant to medical imaging, where we go from cell contrast to tumor to organ, even a whole animal, we want big fields of view. So if you were to go and want to look at like a beautiful mountain range with your favorite camera, you could probably stitch like a Google or iPhone and see big fields of view. We want to do the same thing. We're also developing microscopes that actually can combine the wonders of optical sectioning with physical sectioning. So essentially a meat slicer combined with an optical microscope. And we're also looking at techniques that can go beyond classic optics and are actually optics that are driven by computation, such as polarimetry, where you can actually change the front by changing liquid crystal devices. But underline are the things I'm going to talk about today. I will talk about fluorescence lifetime and this technique of looking at metabolism and how we can use metabolic imaging with optics, looking at cell contrast. I'll talk about second harmonic, which is a multiphoton-based method for looking at proteins that are non-centrosymmetric, such as collagen, and then a bit about spectral imaging. Don't have time today to talk about our fiber imaging, but we're developing fiber-based techniques that allow us to do spectral separation. And then, of course, the disclosure about surgical imaging. We're trying to develop microscopes to be practical in the surgical suite. And then I will be talking about some of our work in multimodal imaging of collagen metabolism. A big interest of mine is trying to look across scales. I'll talk briefly about that. What I won't have time to talk about today, so I just have 2 slides on this, is our software work. So half my lab develops software, and you may be familiar with our major effort, which is Fiji and ImageJ. We've been home of that development now for almost 12 years. So if you have questions about the end, you can ask me. That kind of permeates everything we do. And some of the things I'm doing today are all using ImageJ. So if you have questions about ImageJ, certainly ask. And we're developing tools like Slim Curve for looking at lifetime. I'll talk today about our work in collagen analysis with Curveline. And then we also develop light sheet microscopes using this, machine learning based methods, and also instrument control, or with tools called Micromanager, open source acquisition as well. And then we also do work in notebooks where we can actually do pipelines and analysis workflows. So it's all part of an ecosystem we're developing, including bioinformatics and OME, where you can import and export your data. So due to time, I won't have time to talk much about this except the things underlined. But again, in the Q&A session, if you want to know more, we can chat about that, or offline if you email me. But today's talk is going to be all about the ECM, the extracellular matrix, and the role it plays in the tumor microenvironment. And I've been fascinated by this for many years, as many people are. And we always knew it was important, but the importance is becoming increasingly relevant, that people have discovered that there is a process that the ECM, besides being essential for normal development, you need all the components of ECM, including the basement membrane, for normal development. There's evidence that cancer can uniquely hijack it. And this cartoon is not only our cartoon of the microenvironment, it's specifically a cartoon of the microenvironment. And this cartoon is setting up the whole stage of today's talk. What you're seeing here, if you can see my mouse, is the cancer cells. And this is the cartoon I was talking about. You can see my hands here. The collagen kind of engulfs the tumor. And when I first saw this data, which I'll show in a few minutes, I thought that basically the collagen was entrapping the tumor, because it's known, as all of you know, that collagen is a big part of the immune response. And as you probably know, it's the most abundant protein in your body, and it's very relevant to fighting disease, including macrophages can use it. But it turns out that what this cartoon shows, the collagen is signaled by pathways related to cancer. It becomes long and tangential to the tumor, perpendicular to the tumor, and then the cancer cells escape, like in that first image I showed you in the title slide. So we want to understand this system. We want to understand the components of the ECM there in green, the role the collagen plays, the role macrophages play, and that's what today's talk is about. So this takes a team. So I've had very good luck of working with a number of wonderful folks, everything from medical imaging folks like Wally Block, cancer experts like Suzanne Ponik, clinical experts like Lana Sikowski, and then other imaging folks that represent different modalities, such as Paul Campanola, who can 3D print collagen, Jerry Rogers, an expert in OCT, and Tim Hall is expert in ultrasound. And this particular work was done by Michael Pinkert, my grad student just finished up. And the reason we wanted to go after collagen initially, it was before we knew about that pathway that I just talked about with this metastatic highway. We didn't know that. So why did we start looking at collagen in the first place? We were the first group to show that collagen was a metastatic highway, but how did we know to look at that? It was completely by accident. We were actually going after the work in mammographic density. it was known that for many, many years, that if you're a woman with breast cancer, a more dense breast is a reportable factor to you. So it's a risk factor. And so we knew that one of the reasons women have dense breasts is related to collagen. And we knew that collagen was upexpressed here in more dense breasts. And we knew that when you see these dense images, that collagen was part of it. So we were curious that if dense tissue was a higher risk factor for getting cancer, perhaps collagen played a role. That's what first started us off in the collagen imaging, because we knew that second harmonic was uniquely sensitive to collagen. And so why do we care about collagen in general? Well, there's the quantitative hope that it correlates with breast cancer prognosis. And I'll talk more about that. But essentially, we have shown that this is the real data here, that this cartoon again, where you see the cancer cells invading here, we showed with our imaging techniques that you can actually see the fibers start becoming long and taut. And it's important if we could quantitate that. And so the neat thing about this related to other pathological measures, a lot of pathology is based on visual cues that are qualitative, not quantitative. And yet this is neat because this can be quantitative. And we're able to show us prognostic. So when we started looking at these highways, I'll talk more about the imaging methods in a second, but when we started imaging these things and seeing these fibers, these angles, we show that actually the more aligned collagen is negatively prognostic. So this is really what launched our lab more in the collagen highway investigations, because the fact is that in thousands of patients, we and others have shown that more aligned collagen is a risk factor for death, and it's because we see more aligned collagens, we see more metastasis, because the more aligned collagen is a way for the tumor cells to escape the tight focal tumors. If tumors stay tight and focal, you can surgically remove them, but when you have metastasis, you know, that's unfortunately can lead to death. And so we really wanted to understand the links between collagen topology, which is a fancy word for this organization, and the important risk factor of breast density, which is a known clinical marker. So to do this, we needed multi-scale models. And so multi-scale, as you know, maybe you know, is the idea that you can look from nanometers with techniques like electron microscopy, confocal multiphoton, and then millimeters with MRI-CT. But multi-scale is also the model here. And you can see the power of the model if you look here, that this shows the original data that we first got with electron microscopy. And from this is why I had that wrong hypothesis. I thought from looking at this is a cancer cell, this is the collagen, this is done with electron microscopy. It looked to me like the collagen was trapping the tumor, but that's because I didn't have a time lapse. EM can't do time lapse in the classic way. With optical microscopy, we can see that change over time, where we actually can see collagen fibers and fluorescent cellular tumors. So that's why you need to have not only scale of imaging techniques, but also scale of models. And so an important point we always like to bring up is that multi-scale is not just the multi-scale of the imaging method, but also multi-scale of your studies. And so for the work today, I'll be talking about slides that are human biopsies, so replicating histopathology. There's in vitro models like collagen gels and 3D printed tissues that I won't have time to talk much about, but engineered models are very important. And then I will talk, of course, about animal models and patients, either live in the animal or patient tissues as well that are not fixed. So you really want scale of models as well. It's important. And so the breast density paradigm was this idea that we know that women with dense breasts have a strong risk factor for developing breast cancer. And this is well known and been studied for many, many years, over 15 years. But there's no definitive quantitative understanding of what component of breast density causes increased risk. And we have really tried to correlate processes to these, but the tools to verify and quantitably define it are still really needed. And so for this, we wanted a multi-scale study where we can look at the gold standard imaging method for collagen, which is second harmonic, to MRI and PET in particular, and ultrasound. And if you see this funny gap here that I drew, that's because there's actually a gap of about 10 to 100 microns that no one sees well. And that's, for another talk, is something that we want to develop, but it's currently unknown. And so we really need ways to actually link across this and try to link collagen alignment at the microscale to macro scale. So to do this, we decided to build a multimodal system that would allow us to do 3 methods relevant to collagen: second harmonic, high frequency ultrasound, and OCT, that represent the 3 scales in the previous slide. And we built, this is the drawing of it where we could actually have the ultrasound mounted here and then the optics here, and then your sample underneath. So there's the SHG and OCT representing the optics, and then you can have forwards harmonic, which is basically a method of looking at the light that propagates through the sample, and then you can have your ultrasound, and it's an arm pivots back and forth. So we now have built this, and you can see here that we built an open source frame. There is no eyepieces, and this shows the lens that can go over the sample here. So this could be a tumor biopsy. In the ultrasound, you can go back and forth and correlate things. And this system we call Link is now operational, and we're starting to use it for biological studies. What's unique about it is the amount of different tissue scales. So we just finished commissioning it, now we're using it. But you can see that with the classic harmonic that we've done, you can see collagen fibers, and you can see the resolution here. And you can even look at H&E, classic histopathology, but you can also see what OCT and ultrasound do in terms of the resolution. We're also exploring other methods that are newer, like EBS, which is a method for looking at backscattering, Pulscope and Mueller, which are polarimetry-based methods. And so the idea is to have a system where no one method's better than the other. They're just all complementary. So there's always a trade-off in imaging, as you know, between contrast, depth, and resolution. And we want to combine those. This shows some early efforts where we've been able to combine ultrasound and harmonic. And you can see here where you can actually have the real ultrasound data, the images of the harmonic, and then being able to lend more insight where we overlay, and you can see better structure here from the collagen. And the idea is that we might develop a rubric where we can extract more out of ultrasound, which is much more clinically relevant than optics because the ability to penetrate so deep. But of course, optics is more high resolution. And so the ability to combine both worlds is a big goal of ours. And so we call this multi-scale imaging with harmonic ultrasound of breast cancer. So as far as imaging methods for today, I'm mostly, as you've already seen, going to be focusing on multi-photon-based methods. We'll be focusing on the use of second harmonic, FLIM, and then, of course, spectral imaging with that. And the goal is to be non-destructive and exploit endogenous signals. And I think at this point, for most audiences, I don't have to explain multiphoton, so I don't have slides on that. But essentially, if you don't know what multiphoton is, it's been around now for quite a while. It is very similar to confocal microscopy, where you have galvos that scan a raster. But what's unique about it is you're using a very high femtosecond laser that has such a high rep rate that actually the chances of having two photons for a single station event are so high that you actually have two photons and one photon. So it's actually a 2 photon or more event. And this allows you to image deeper because these longer, the wavelengths that are used for this 2 photon event penetrate deeper. And so we're actually using very long wavelengths. So instead of the classic 400 nanometers used confocal or 450, we're more like 900, 890 in that range. So multiphoton is also very benign because it's past a lot of known UV checkpoints. And then we're using a technique of second harmonic, which is basically exploiting non-symmetric structures. If you have the multiphoton laser hitting a non-symmetric structure, you get this instantaneous reflection that we can exploit this scattering phenomenon. We also can use FLIM, which is a measure of how long fluorescence lasts, and spectral readouts as well. I'll talk a little bit about that a little bit later. We do some algorithm development in our lab, and I'll talk a little bit more about some of the math. I won't have time to talk about our machine learning work today, but of course, we're moving rapidly towards doing this more towards machine learning. But a lot of our work in collagen analysis was based on algorithms that were based on curvelets, which is originally used for looking at topology of ocean floors. And our collagen story is kind of similar to that same kind of undulation that you see at an ocean floor. So trying to exploit that. And you can see our efforts here where this shows the tumor, and these are the collagen. And you can see it here as well. And we can automatically now track all the fibers and measure them. And this software package called Curvaline 55 are now available. They have a fairly wide user base. And I only mention this because it shows you how many labs are interested in this technique. There's over 150 labs that are using this right now, which is quite a lot if given that it's focused on only collagen. We're also working on our software in ImageJ to do big stitching. And this shows our efforts to do big extended point of view, where you can have very, very big fields of view, where you could take your classic image, it's 100 by 100 microns, and go really big fields of view. And just as the scale bars here, you can see how big we can do. This is 11.6 millimeters. So you can do really big pieces of tissue and then correlate to H&E. So you can have your classic pathology view and then our view that is collagen specific. And this shows invasive ductal carcinoma. It also gives you a chance to see how different the topologies start getting. The fibers become longer and tout into cancer. And IDC is one of the more important cancer phenotypes. We've also been starting to look at other cancers as well. We've been really looking at ovary as well, and you can see the big difference between ovary, high risk, and cancer. We've also been looking in the brain. You may be surprised if you know things about the brain. You'd be like, why is he looking at the brain? As you can see here, there's very little collagen in the normal brain. You only see collagen in the core plexus here in green. But otherwise, maybe a little bit in blood vessels, and that's it. Collagen is not thought to be a major role in the brain, mostly because there's not fibroblasts in the brain, unlike the epithelial tissues. You can see a better example here. But what happens when you have a wound? And this is where we put an electrode in the brain that's often used by neuroengineers. And you can see striking in the electrode all this collagen that just is in the shaft of the electrode. And we believe that when there's wounds, that collagen comes in. And we believe the difference is that in epithelial tissue, the collagen is already sitting there, so it could be hijacked by cancer. But in the case of a wound, it's being made by macrophages. So this is a protective mechanism and not a bad thing. And so we're very interested in this idea of that collagen for macrophages. I say here about harvesting material, we have some new unpublished data that we haven't shown yet, where if we make this electrode soft, very interesting enough, you don't see any collagen. And it kind of makes sense because you think in your brain, if you had a very hard, rigid object, it could be more prone to wounding as you move your head in response. But if you have something that moves with your tissue better, you have less of a wounding response that's soft. We're also looking at this in glioblastoma as well. So we've seen very similar changes of collagen in glioblastoma. Very relevant to my current work, we're looking at pancreatic cancer. So the focus of my lab at the moment is more pancreatic than breast, just because of how deadly disease this is and how relevant fibrosis is. The fibrosis is the change of collagen. And you can see here that if you look at the changes that happen over progression, there's a big change in the appearance of the normal tumor, where you can see the fibers like this versus the long taut of cancer. And so this is something we're quite interested in doing, very stark differences. We've shown similar to breast cancer, this is also prognostic. So if we go in and look at collagen alignment, we can actually see big changes between normal, chronic pancreatitis, which is a very different disease, but often confused with pancreatic cancer, and the 3 grades. And we have published now that you not only can use collagen to tell apart the 3 grades and from cancer, but even more interesting to pathologists, you can tell apart from chronic pancreatitis, which is often confused. And so it's neat that we have shown that collagen alignment is prognostic. Similar to breast cancer, we've shown that more collagen is a higher chance of dying from it. More collagen alignment, it's actually dying from it. So to the second stage of my talk, it's always all pathology, looking at fixed tissues, but we also want to look at things in vivo. So in breast cancer, we can actually put a window in the animal, a glass window. We could use multiphoton image to do that. So I want to talk about live data, and this gives a little teaser. This is live data showing all intrinsic labels, showing NADH cancer cells, FAD cancer cells in red, NADH in blue, and then collagen in green here. And so the ability to get this kind of exquisite palette of the picture all via autofluorescence is quite powerful. And one of the reasons I forgot to mention we're excited by autofluorescence is that you can use it on clinical tissues. So it makes it more clinically relevant. You don't need FDA approval because you're not adding anything. You're just taking advantage of nature's natural contrast. So as I already mentioned, we have a link to breast cancer. We know that high density promotes tumor invasion. In fact, in the animal, we can even prove that. We can actually create mice that have increased collagen density. This is COL1A mice where the collagen is purposely overexpressed to mimic what's seen in the human and breast cancer. And we see we can actually make cancer cells more aggressive just by having a denser collagen matrix. And this is showing the same data I showed earlier, but this time is showing some live data where you can actually see not only the cartoon and the fixed pathology, but now you actually can see, similar to the first slide I showed you earlier on, you can see the green cancer cells lining up with the fibers and starting to escape. And so that's very powerful, but we wanted to know if we could go beyond the collagen part of the microenvironment and look at the other hallmark of cancer, which is it being a metabolic disease. And you may have all heard of the Warburg effect, which is that you see more glycolysis cancer cells. Cancer cells are able to shift to glycolysis, an alternative metabolic pathway, unlike normal cells. So one of the 2 main metabolites in your body are NADH and FAD. And it's quite nice that nature has made these glow. They naturally fluoresce under the microscope. You can see NADH at under 780 or 740 with the multiphoton, and FAD about 890. And so using a a window microscope, sorry, a windowing method that we now make out of plastic, so it's compatible with multiphoton and MRI. We can actually create windows that even have ports in them and holes. We can implant this as a toy mouse, but we can plant it in the mouse and image it. And so this shows the kind of contrast you get in a live animal. This is NADH, and this shows FAD. And this shows how we can combine it with collagen. So you can get, again, this beautiful contrast between all these methods together. And we want to use FLIM, which is not a new method. FLIM has been around since the 90s, but mostly it was a chemistry method. But FLIM is exquisitely sensitive to NADH because FLIM is a measure of how long fluorescence stays in excited state, and whether a protein is bound or free can be detected by that. And that's really exciting because this is the only way of doing it with any kind of temporal contrast. Otherwise, you have to use biochemical methods or more blender-like, don't give you any spatial temporal context. What's unique about multiphoton-based NADH FLIM is it gives you temporal and spatial with metabolic contrast. And so we can actually do this. We can actually now do metabolic mapping where we can look at free and bound NADH. And we wanted to know if we could go one step further. So rather than just seeing cancer cells and metabolism and Warburg, which we and others have published quite a bit, we wanted to know if we could use it for cell identity. And one of the harder problems when you look at a case like this, when you look at autofluorescence, you assume that all these cells are all cancer cells, but the reality is they're not. They can include normal cells. And historically, even more interesting is they include macrophages that often get confused. And so actually, when you look at this image here, we snuck in something here that actually the red is NADH, but the green here is actually a macrophage marker. So this is one of the first images I've shown you where we're using an extrinsic marker. So this in the animal, we can actually use a macrophage marker. And we want to know if we could co-localize the extrinsic known marker for macrophages with the intrinsic marker of NADH and FAD. And the reason we want to do that is that we want to be able to prove the identity of macrophages using intrinsic fluorescence. So essentially a fingerprint. So we were able to do this. We actually looked at FAD high cells. So this means cells high in FAD. And they had a very different lifetime than those in NADH high. And we were able to show that with lifetime. And then we can correlate that back to the known macrophage marker. And so we actually can look at wherever we see the green macrophage marker, and we can co-localize that in image J with the red and be able to prove the phenotype. And essentially what we found was that macrophages and the cells that are FAD high are the same. So wherever we saw the high FAD was a measure of a macrophage. And so we were able to prove what was a macrophage just basically by label free. And so then we were able to combine these methods where we start looking at it near fibers. And what's quite powerful is that if you look at the map of lifetime, wherever we see the cooler blue is more glycolysis, which makes sense because we're seeing it near fibers. And so it makes sense to us that cancer cells would be more blue, more glycolysis because they're metastatic due to Warburg theory. And so this shows in better detail that signatures of tumor cells near collagen fibers are more glycolysis. So now we have the ability not only to tell you what's a cancer cell or macrophage, but we also can tell you what's more glycolysis as well. And we can correlate it to the collagen fibers. So conclusions of this part are that these collagen signatures that we call tumor-associated collagen signatures, this perpendicular marker that I mentioned, are prognostic markers for breast cancer and pancreatic cancer and many others. That NADH, FAD, and harmonic provide endogenous stromal and tumor cell contrast. And the NADH FLIM provides in situ metabolic signatures in the breast tumor microenvironment. And that FAD cells in stroma have a higher NADH lifetime than NADH high in stroma, which just means that we can map what is the identity of metabolism. So I wanted to kind of sum up the optics because I went through all this quickly, particularly focusing on the biology. But if you think about multiphoton microscopy, which at this point is very well established, including being a commercial method, you don't need home-built systems like ours. You can use commercial systems as well. We can look at dynamics, such as cells invading a matrix. You can look at structures, such as 3D views of the collagen. You can see the black are the tumors and the collagen fibers. And then you can look at the fluorescence lifetime, which is a measure of the chemistry of the fluorophore, and look at NADH metabolism, or you can look at the physics of the environment, such as harmonic generation, which is physical-based, to look at collagen orientation. And then there's supporting technologies. There's the intervital mammary window, there are engineered fluorophores, there's advanced detection methods. I didn't have a chance to talk about Nanovid, but this is a method where we work with a collaborator where they actually can insert a device, microfluidic device, to create local areas of chemical contrast, such as drugs that are maybe drug therapy or the kind of changes. If I had more time, I would talk more about the software and machine learning, but I think I just will end here. You could leave time for questions. That this slide kind of represents our efforts in image analysis. So we're very involved in image analysis, and we're creating an ecosystem. We're developing tools in OME along with many others. Jason Swedlow leads this effort, but this is an effort to create a whole system, and our role has been more in the past than bioformats, but we use this tool quite a bit. And then ImageJ, Fiji, and NIME, so Profiler are tools that we work with to do quantitative analysis, and then we're also involved in open acquisition. So I do want to stress that since a lot of you do microscopy and image analysis, I hope you use our forum. This is a place to ask image analysis questions. We have over 60 partners of software groups on here, and this is a great place to get free help and very responsive help online. So I encourage you to take advantage of that. So this is my group. They're the ones who do all the work, and I'm very grateful to all of them. It's a terrific colleagues and students, and my collaborators, and also I think my funding from NIH, NSF, DSRC, and DoD, and of course my two homes in Wisconsin and a mortgage. And with that, I will end there. Leave time for questions. Any questions?
I have a question.
Please go ahead. Yes.
Yeah, so you may have said it and I probably missed it. Do you see these tools moving from lab environment to maybe application by being used, more into industrial environment? And would they even be possible because of the time that it takes, to do the measurements?
Yeah, absolutely. There are, I think, three aspects that are relevant to your question. There is what you do in research, there's what you do clinically, and then what you do in the industry marketplace. As far as research, early labs like ours did multiphoton. We did a lot of this before there were commercial instruments, but now there are at least 15 companies that make multiphoton instruments. So commercially, multiphoton and fluorescence lifetime are very viable techniques for the research market. That's because these techniques of multiphoton, cycloharmonic, and lifetime are becoming pretty widespread, where these methods are being used, and people don't want to necessarily home build. And home building makes sense for labs like ours that are trying to add new things. But if you just want to actually use one of these biomarkers by itself, or just to use it more in a turnkey mode, a commercial microscope works quite well. So absolutely, companies are using this as a research tool and selling it. But in addition, there are companies that are trying to explore the clinical relevance. So multiphoton, like a lot of the optical methods, cannot be used on a live human. Unfortunately, we don't penetrate deep enough to see these tumors in situ. In animal models, we have to use a window to get deep enough. So, but what we can do is we can look at biopsies. And so pathology has become a major market. And so there are several companies trying to make versions of this for pathology use. And so that's become a big area. So any other questions?
Thank you.
No problem.
Professor Evren Mutlugün, are you here? Can you hear me?
I can hear you.
Professor Mutlugün, can you hear me? No. Okay, thank you very much, Kevin, for
my pleasure. Thank you very much for listening.
For accepting our invitation and also for your excellent talk. We have times for question. If participants and audiences have some question, you can write on the chat box here, and also you can ask us to open your voice to ask the question. We have time. So, okay. So I have a question, Kevin. If in the case of super resolution, we have diffraction limits, and people in some cases say that we can in the case of diffraction limit, we can see the particle sizes or the structures below the diffraction limit. But it is in conflict with physics and optics. How we can describe this generally?
Well, superposition is still very much a work in progress. I tend not to use as much for my current work because a lot of it has not yet gotten to the resolution that we need, and also the practicality of the contrast, because it's not compatible with some of the imaging methods that I've done. But it is getting better and better. And what's powerful about super resolution is that you might be able to get closer to electron microscopy, which we use right now. So right now, if we want to do ultrastructure studies, we use EM to understand what happens for example, in the collagen story. Not only is there topology, but there's the makeup of the fibrils, and superposition could be used to potentially look at that as those methods become more compatible with multiphoton or harmonic imaging, for example. And the promise is that maybe you can look at structures that are below the 300 nanometer that we currently look at with multiphoton. However, there is a need to better characterize these methods and to know what they can do. And so I think the superposition has certainly shown its ability to look at cell structures and other kinds of things. But in terms of better quantity comparing to EM, I think if you're asking me how you could best understand the limitations in physics of super res, I think there's a need for more correlative methods and gold standards and being able to compare to what you can do with EM. But it's certainly intriguing, the idea of using super res. It's just not something we currently do because of the lack of contrast for the microenvironment. So.
Okay, thank you for your answer. And I'm waiting for the chair just now, and also
Yes,
Professor. Yeah.
I'm hearing it, but Professor, an issue with the microphone. So somehow I write in the chat, but nobody have seen it. Maybe. Anyways, so thanks, Kevin, once again. So is there any other question to our speaker? If not, I do have one, a quick one, Kevin.
Sure.
So you have talked about the film measurement. So I was wondering about instrumentation, about the wavelength of the emitted light that you looked into. Could you please elaborate the film measurement system that you already mentioned?
Yeah, so we're using more than one film system, but typically, if you're using endogenous signatures, you're looking mostly at NH and FAD, which would be 890 and 780 in a multiphoton, and you can either use a time domain system, such as Becker-Hickel's system we use, or a frequency domain, such as the home built we have, or the PicoQuant. And we're typically looking at changes that are with those wavelengths, and we're using endogenous. We can also use extrinsic too, but typically it's multiphoton tuned to 890 or 780 using a time domain system is our most common system. And we're looking at changes in lifetime that range from about 300 picoseconds to about 1.2 nanoseconds. So that's our typical range of the system. And we typically collect for about 30 to 60 seconds in order to get enough photons to be confident of our fits, although we're trying to improve that.
Yep, thank you. Thank you.
No, my pleasure.
That was what I was wondering. Yes, is there any other question to Kevin?
It's not other question, I think, Professor Mutlugun, but it's very interesting. There are very much more similarity between Professor Evren and also Kevin, yeah? But accidentally. Yeah.
Wonderful. Well, thanks so much for the invite. I enjoyed talking to you guys.
Yeah.
Thank you. So, well, there is time for the next talk. I would like to ask here whether we should continue, Mr. Yashar. So shall we continue here or just wait for 5:30?
Yes, just now we have approximately 20 minutes, but you are chair. You can continue with Professor Bülent Çakmak. Okay.
Okay, so the thing is, there may be some participants who are just having an eye on the program. So I would suggest to wait at least about 10 minutes so that we can just wait for the next session. So because I mean, when you just look at the program, the next talk would be starting at 5:30. If you don't mind, I would just suggest to start about at least around 20 past 5, so that.
Okay, this is a very good time for taking a group photo if you are agree. Yeah, Kevin, Evren.
Sure, why not?
I want to ask everybody to open their camera, and I would like to take some photos from everybody. Everybody open your camera. Alka, thank you. Hakkı, Gökhan, Berenice, thank you for your nice talk. And also Meltem, Dilshat, Burak, thank you. So we are ready. Smile. Okay. Meltem? Yes, thank you. Thank you. So, Evren, we have the closing ceremony at the end of the talks. For example, for approximately 20 minutes, I would like to inform all participants and people here to participate at the closing ceremony and also prize ceremony. Yeah.
Yeah, sorry, I just lost the connection, so I couldn't hear the few verses.
Okay. So, yeah.
Are there any problem, Mr. Emre?
Tamam.
So, how was Turkey? Turkey was... Wow. Yes.
Hello.
Hello, Professor Chakmak. Yeah.
Yes, I am here.
All right.
Dear Professor Çakmak, welcome.
Thank you hocam. How are you?
Fine. Nasılsın hocam, iyi misin?
İyi hocam, hamdolsun. Sağ olun. Teşekkür ederim.
Have a good
Daha iyi oldu.
presentation. Have a good presentation. Thank you, Evren Mutlugün.
Thank you, Süleyman Hocam. So I thought it could be a good idea to wait a bit longer because some of our participants may wanted to join the Bülent Hoca session. So they may just look at their time and then just be on here on time. So I thought it could be a good idea to just wait a bit more because I mean in the program it was scheduled to be at 5:30. We'll be starting in a few minutes, Bülent Hocam, if you're also okay. So
Yeah.
I'll be starting the session about 5:25.
All right, okay.
All right, so welcome back, everyone. So we'll be starting our next talk with Professor Bülent Çakmak from Erzurum Technical University, Turkey. Professor Çakmak has his BS from Karadeniz Technical University in Turkey, and he holds PhD in electrical engineering, electrical and electronics engineering from Karadeniz Technical University, and also from University of Bristol in United Kingdom. During his PhD, he studied the fabrication and characterization of Q-switch long wavelength semiconductor lasers
Currently, he's also holding a rector position at Erzurum Technical University, and it's a great honor to host him at our talk. His research interests include fabrication of diode lasers, fuse switching, chirped semiconductor lasers for production of ultra-short pulses, and modeling of the tapered waveguide structures. So, Professor Çakmak, please.
Thank you so much, Chair. I will share my screen. I think it's okay.
Yep. You can make a full screen, yes.
Okay. Thank you again. First of all, I would like to also thank the chair of the conference, Professor Dr. Süleyman Özçelik Hocam, for inviting me for this prominent conference. My name is Bülent Çakmak. I am at Erzurum Technical University in electrical engineering. My talk is about chalcogenide-based two-dimensional structures, new quantum materials. This work is carried out in the 2D materials group. The leader of group is Güven Turgut. So we carry out this project in our High Technology Research and Application Center, and this project was supported by the Scientific and Technological Research Council of Turkey, TÜBİTAK project, and also Erzurum Technical University scientific research projects. In the first part of my talk, I will give some information about characteristic properties of TMDCs, transition metal chalcogenides, synthesis methods of TMDCs, and applications of TMDC materials. In the second part, the results section, I will give some information about the growth of TMDC materials in our labs and characterization results. I will conclude my talk on ongoing studies in our labs and future plan. Okay, our motivation is that 2D materials refers to crystalline solids consisting of a single layer of atoms. Single layer materials are derived from single elements or compounds of two or more elements. As you know, the first known 2D material is graphene, as you can see here, the atomic structure of the graphene, which was experimentally obtained in 2004. Graphene has an excellent thermal, electrical and mechanical properties, but lack of intrinsic band gap led to the discovery of other 2D materials, such as HEX-BN and MO-S2 materials. And here, 2D nanostructures in this slide are given because after graphene discovery, there are a growing interest on 2D materials. I will summarize some of them. Black phosphor, as you can see here, HBN, hexagonal boron nitride, COF materials, covalent organic frameworks. Here, graphene, as known, LDH layered double hydroxides, oxides, MOF metal organic frameworks, metals, and two-dimensional inorganic compounds here. TMDS, transition metal chalcogenides, which we focus on these kind of materials. In 2D chalcogenides materials, we focus on especially TMDC materials. As known, there are some other type of 2D materials, such as monochalcogenides, which are called AX, chalcogenides B2X3. Why we choose TMDC materials? Because they are superior to many properties, many outstanding properties, electrical, optical, and structural. Atomic planes of TMDCs exist as self-contained units. Individual layers can be isolated from the bulk. And one of the most important properties of the TMDCs is they have layer-dependent properties. Therefore, they are suitable for power generation, conversion applications, and bring important opportunities in future technology. I will give some information about the structure of TMDC materials, as you can see here. In figure A, you can see the cross-section of MX2 structure. M is a transition metal, such as molybdenum and tungsten. X is the chalcogen material, such as sulfur or selenium. In figure B, you can see the 2D structure. And in figure C, you can see the top view of a hexagonal TMDC material. One layer of M atoms is sandwiched between two layers of X atoms. They are part of a large family of so-called two-dimensional materials named so to emphasize their extraordinary thinness. Because, for example, a MOS2 monolayer is only 6.5 angstrom thick. They are very thin materials. Here, the characteristics in this table, I give some details about the two-dimensional materials. For example, MOS2, MOSE2, WS2, and WSE2. The thing here is that from bulk to one monolayer, also the bandgap structure changes. The bandgap structure changes from indirect to direct. All these materials, two-dimensional materials, 2D materials, are semiconductor. One of the most important properties here, from when the structure is changed from bulk to one monolayer, also the bandgap structure changes from indirect to direct. As you can see here, in the bulk case, the bandgap is 1.2 electron volts, which is indirect for MOS2. It becomes direct bandgap, and the bandgap is 1.8 electron volt. This is very important because you can use these kind of materials in many applications. Also, some of two-dimensional materials also metallic. For example, TAS2, TASE2, etc. Okay, in this presentation, I give the band structure of MOS2, which is commonly used two-dimensional materials. As you can see here, in the bulk case, it is indirect. Also, for four monolayers, two monolayers, it is still indirect. But when you make one monolayer from MOS2 material, as you can see here, it becomes direct bandgap, which is very important because when you make indirect bandgap to direct bandgap, this is there are different kind of application fields in which you can use these kind of materials. In figure B, you can see the PL spectra, PL intensity of this material. For one layer, you can see this red figure. Okay, this PL spectra is for one layer MOS2 material, and the peak, PL peak is at about 1.9 electron volts. And also, if you look at the inset figure here, for one monolayer structure, quantum yield, quantum efficiency is much higher than for 4 or 5 or 6 monolayers. This is why researchers are focusing on one monolayer two-dimensional structures such as materials such as MOS2. Two-dimensional structures also have interesting magnetic properties. For example, VS2 two-dimensional material exhibits ferromagnetic behavior from bulk to single layer. That means when it changes from bulk to single layer, it shows some kind of ferromagnetic behavior. Also, at room temperature, VSE2 exhibits a kind of ferromagnetic behavior in case of monolayers, of course. If you look at this diagram, for trigonal prismatic structure, ferromagnetic ferromagnetic material, the total energy is very low for ferromagnetic material at trigonal prismatic structure. At octahedral structure, ferromagnetic materials have higher energy than that of trigonal prismatic materials. This is another important feature for the two-dimensional materials, I can say. Okay, now we can now continue with giving some information about the synthesis of two-dimensional materials. Okay, if you look at here, we have two. There are two nanomaterial synthesis approaches here. One of is top-down, another one is bottom-up. In top-down approaches, bulk materials are divided to produce mono or a few layered materials. Top-down methods include macromechanical exfoliation and liquid phase exfoliation. Macromechanical exfoliation is a good method, is a very good method to produce high-quality atomic thin materials with minimum defects. You could see here in figure A, bulk HFS2, two-dimensional material. TMDC layers, as you can see in figure C, are separated as individual layers from the main crystal by mechanical division using adhesive tapes. This is why it is called mechanical method or micro-mechanical method. In the case of liquid phase exfoliation, we use kind of chemical solvents, liquids or polymers. As you can see here, kind of in ultrasonication device, a sonication device is used for exfoliation due to it's very effective in the separation of the layers by emitting vibrations in the van der Waals bonds between the layers. In bottom-up approaches, okay, as component size decreases in nanofabrication, bottom-up approaches become a good alternative when we want to use a better method. One of the methods, bottom-up methods, is chemical vapor deposition, CVD. As known, CVD is an excellent method for producing high quality nanomaterials and well known for the production of two-dimensional nanomaterials. As you can see this figure, first reactant gases, blue circles, are transported into the reactor, step A, as you can see here. Then there are two possible routes. One route is here, which follows D, and another route is here, which follows BC, directly diffusing through the boundary layer, which is B, and absorbing onto the substrate, absorption process in C, or forming intermediate reactants, as you can see here, intermediate reactants, green circles, and by-products, pink circles, or red circles, via the gas phase reaction here, in the case of B, and being deposited onto the substrate by diffusion, step B here, and adsorption again, like here, C, surface diffusion and heterogeneous reactions, step E, as you can see here, step E, green circles here, take place on the surface of the substrate before the formation of thin films or coatings. Finally, byproducts and unreacted species are desorbed from the surface and forced out of the reactor as exhausts, in the case of F. This figure shows the growth steps of the chemical vapor deposition. There are other methods, other techniques in bottom-up approaches, such as physical vapor deposition, PVD, and atomic layer deposition, ALD. PVD is very well-known method to deposit materials on our samples, which is done in high vacuum, or you can use sputtering or other techniques. Also, pulsed layer deposition, PLD, is another technique, another PVD technique, in which a high power pulsed laser beam is focused inside a vacuum chamber to strike a target of the material to be deposited. Another method is ALD, atomic layer deposition. This is a more sensitive process, more accurate process than PVD. Much more thinner films are deposited using ALD technique, in which all ALD reactions use two chemicals called precursors or reactants. Here in this slide, you can see the applications of TMDC materials. There are many application fields: photodetectors, battery electrodes, topological insulators, electronics, solar cells, FETs, gas sensors, lasers, and LEDs. You can see in this figure timeline of the development of the applications of 2D layered, two-dimensional layer semiconductors in photodetectors. For example, in 2008, graphene-based hybrid phototransistors were produced. There are other type of photodetectors using different kind of two-dimensional materials. For example, MOS2, graphene mixture of graphene and MOS2 hybrid phototransistors. WS2 phototransistors, MOS2, WSE2 vertical photodiodes, etc. This is one of the examples. Of course, there are other application fields of two-dimensional materials. Now I will give some results which we carried out in our labs in our center. You can see the CVD synthesis of MOSE2 and WSE2 monolayers. Here you can see the schematic of the CVD process, and also this is the CVD system in our lab, which is a homemade CVD system in our lab. Okay, to produce, to grow MOSE2 and WSE2 monolayers, of course, you can see the CVD schematic here. The substrate, which is silicon dioxide or sapphire substrates, were placed here face down on precursor sources in curricle. You can see here WO3, MOO3, and selenium source materials used here in the CVD tube. The temperature and growth times are, of course, very important parameters. 780 degree temperatures is used for MOSE2 monolayers. 930 degree deposition temperatures are for WSE2 monolayers, for the growth of WSE2 monolayers. Growth times are different, of course. 14 minutes is for MOSE2 and 20 minutes is for WSE2. We use the mixture of argon and hydrogen gases in the tube, as you can see here, and CVD process is done under ambient pressure, as you can see here. After this process, we produce MOSE2 or WSE2 two-dimensional materials. Some characterization results, you can see Raman results on the left-hand side of this slide. As you can see here, MOSE2 is given with red figure here, as you can see, and WSE2 is black one. The Raman peak is around 254 WSE2, which shifts to lower Raman shift is for MOSE2, as you can see here. The PL peaks for the PL intensity figures, as you can see here. For MOSE2 is about 1.551 electron volts and 1.61 electron volts for WSE2 two-dimensional structures. Here, atomic force microscopy results for MOSE2 on the left-hand side and for WSE2 on the right-hand side here. The thickness of the monolayer MOSE2 is around 0.74 nanometer, and which is about 0.82 nanometer for WSE2 monolayers, which are quite thin flakes for these monolayer materials. Okay, our ongoing studies for TMDCs, as you can see here, we give XRD spectra. XRD spectra shows that all powders have MOO3, which are some of them undoped and some of them doped 1%, from 1% to 5%. These results show that V-doping, vanadium doping, doesn't change crystalline structure. Any peak related with V wasn't observed. This is important progress to obtain undoped and doped MO-related TMDC materials. After this step, V-doped MOS2 monolayers will be deposited with CVD. We do this because we want to see if we dope different kind of materials. If we dope the TMDC materials with different kind of materials, what will change? And if we can improve the structure of the two-dimensional structures. Okay, the thing is, in our future works, we want to control the doping of TMDC because in the literature, generally the doping is not controlled in the research. We want to control. We want to dope with control. We want to make the controlled doping of TMDCs because we want to control and manipulate the physical properties of the two-dimensional materials, such as TMDC materials. And also, we proposed in our project, in TÜBİTAK project, the synthesis of genus TMDC materials because they are also a hot topic in research. Because in these structures, researchers use different kind of atoms or elements in this case. For example, in MOSSE, you use different kind of element between molybdenum and selenium, sulfur here, sulfide. In this case, more electrons around S bring about a net electric field pointing from Se to S atom. So we want to see if we can see any improvement in this case. Okay, in the final part of my talk, I want to give very brief information about our center, which is called UTAM, High Technology Research Center, which in this center, which we carry out our projects and also we grow the TMDC materials in this research center. We have 1,000 clean rooms in our center. Also, we have in one of the clean rooms we have a maskless aligner, RAICP system, spin coating, RF DC sputter, thermal evaporator, PECVD, and etc. And also this photo is from our 2D materials group. As you can see here in the CVD system, our researchers, our group members are working in this lab to produce two-dimensional structures. Okay, I finalize my talk, my presentation. Thank you so much for listening.
Thank you very much, Professor Bülent Çakmak, for warm presentation. Thank you.
Okay, I close the presentation.
The line is open for us. You can do questions. All right. So I just lost the connection once again. So I was asking whether there's any questions, and I'm not sure, Bülent Hocam, you were able to respond to the question asked in the chat window.
Chat window, okay, I will check.
It says, what size silicon substrate did you use to grow the films?
Okay, the silicon substrate, we use the conventional silicon substrates, which is around 250 microns, something like that.
Mm-hmm. Any other questions from the audience? Right, if not, we would like to thank the speaker once again.
Sorry, another question is, have you made any devices and do you have any electrical measurements on these films? Not yet, we work on it. So we want to make two-dimensional devices from MOS2 and other type of two-dimensional devices. This is why we proposed this project to BITAC and get financial support. So we are working on it.
All right, thank you. So no more questions, I think. Thank you so much, Professor Bülent Çakmak.
Thank you.
All right, so our next talk is from Professor Dr. Viktor Kisel. Well, Dr. Kisel received his PhD from Belarusian National Technical University in optics in 2006. And currently he's the head of Center for Optical Materials and Technologies at Minsk, Belarus. He has given more than 100 talks in international conferences, and he had received more than 2,000 citations, and he's holding a H-index of 25. He will not be able to make it live, so he has shared his video with us. So our organizers, could you please start the video?
Good afternoon, ladies and gentlemen. I would like to present our recent results, deal with spectroscopic properties and laser performance of novel laser media based on ytterbium-doped aluminum and lutetium perovskite crystals. My report will be a small overview of spectroscopic properties of trivalent ytterbium ions in this host media, as well as the features of their use for ultrafast laser systems. This work was performed in the Center for Optical Materials and Technologies, Minsk, Belarus, in collaboration with our colleagues from Armenia. Okay, my talk will consist of a brief introduction, our view of crystal growth and thermo-optical properties, and this will be followed by experimental results in continuous wave mode locking mode and chirped pulse regenerative amplification. My talk will be finalized by conclusion and outlook. Nowadays, a large number of different types of ultrafast lasers have been developed and commercially available, which are powerful tools in industry, medicine, and fundamental research. In my report, I would like to talk about lutetium aluminate crystal doped with trivalent ytterbium ions as an active medium for solid-state mod-locked lasers and chirped pulse regenerative amplifiers. So let's look on the main criteria for choosing an active medium for ultrafast lasers. Wide and smooth gain bands allow to obtain wide spectra of generated and amplified pulses that further can be provide short pulse duration of bandwidth limited pulses. High stimulated emission cross sections will reduce the critical pulse energy in mod locking mode or provide small number of gain medium round trips for efficient amplification in the amplifiers. Good thermo-optical properties of the active medium will be very useful for high average power lasers. Efficient pumping capability will lead to high overall efficiency of the system. Small stock shift or quantum defect will reduce heat load on the active medium and allow to use simple cooling systems. And the system simple and reliable methods for growing and processing of active media will result in high economic efficiency and safety. Okay, the crystal that was used in this work was grown by vertical Bridgman method in iridium crucible with argon atmosphere. It has orthorhombic lattice, and other crystal growth and lattice parameters are shown in the slide. A few words about thermo-optical properties. Initially, Loab crystal was used as an scintillator, and they first used them as a laser active medium described in our works. This fact can explain the absence of wide investigations of its thermo-optical properties in the literature, and we found only data on the calculated and measured values of thermal conductivity. According to these parameters, the crystal is very promising. The structural YAP crystal is a well-known matrix for various active ions, and if we turn to its thermo-optical properties, we can see, for example, that thermal expansion coefficient for the direction along the crystallographic axis A, shown here, differs from practically identical to other values. Sorry. Here. Yes. That must be taken into account when choosing the orientation of the active medium. Okay, it should be mentioned a thermal conductivity variation upon ytterbium doping of crystals that contain lutetium ions. Typical situation is the fast degradation of thermal conductivity. The exception is the case of crystals where ytterbium replaces lutetium. For example, lutetium oxide, shown here, showing a slight change in thermal conductivity with increasing ytterbium concentration. And we estimate similar tendency for lutetium aluminate crystals. Okay, let's switch to the spectroscopic properties of the crystal. A radiative lifetime of ytterbium ions in Loab crystal was estimated with the help of luminescence decay measurements of powder immersed in glycerin. Estimated lifetime for 2% crystal is about 475 microseconds, that close to radiative lifetime measured for the structural YAP crystal. Luminescence quenching was observed for highly doped crystals with 5 and 10% that can be attributed to the migration accelerated energy transfer process. Absorption and stimulated emission cross-section spectra estimated by integral reciprocity method as shown on this slide. The crystal characterized by wide and structured stimulated emission cross-section bands. And the most interesting polarization state for mode-locking operation are E parallel C here and E parallel B polarization state due to high stimulated emission cross-sections. Thus, in accordance with the previously formulated criteria, the ytterbium Loab crystal has relatively wide and smooth gain bands, comparatively high stimulated emission cross-sections, good thermo-optical properties, allowed efficient pumping with indium gallium arsenide diet that is usual for ytterbium materials, and that has small Stokes shift and quantum defects and can be grown by reliable vertical Bridgman method. Further will be presented experimental results, and the first of them is the CW laser performance. Based on spectroscopic and thermo-optical properties, we choose the active element orientation that enables operation with E parallel B and E parallel C polarization states in the crystal. It was 1.5 millimeters thick slab. The working surfaces have anti-reflection coating, and cooling was performed through the side surfaces. During the experiments, the crystal temperature was kept at about 15 Celsius degrees by means of thermoelectrical cooling with water-cooled heatsink. For mirror X-shaped cavity, shown here, was used. Quasi-off-axis pump layout provides spectral and polarization independent of pump beam and the cavity mode. During the CW laser experiment, the tunability of ytterbium blow-up crystal was measured by means of intracavity prism. Okay, the results of CW laser performance: maximum output power more than 9 watts and slope efficiency as high as 73.5%, and optical-to-optical efficiency as high as 39%, confirm capability of high average power operation and high crystal quality. The described above pump arrangement allowed to obtain a more than 70 nanometers wide tunability range with output coupler transmittance of 1.5% for both polarization states. Mod-locked laser performance was investigated in a 4-mirror laser cavity designed for operation in the middle of second stability zone, which provided the possibility of controlling mod size on the ZSM, shown here, without additional focusing elements, and mod-locked regime was provided mostly by the CSM. Group velocity dispersion balance necessary for soliton mod-locking regime was provided by GTI mirrors, shown here. Stable mod-locked regime was obtained for different output coupler transmittances in the central wavelength range from about 999 nanometers to 1041 nanometers. The shortest pulse duration was 90 femtosecond with 2.9 watts average output power at about 1019 nanometers central wavelength. 7 watts of output power with 130 femtosecond pulse duration at 1013 nanometers central wavelength were obtained with more than 28% optical efficiency, and this corresponds to pulse energy of 100 nanojoule and peak power as high as 0.75 megawatts. Both these results were obtained for E/B polarization. Autocorrelation trace and spectrum of the shortest pulses with 90 femtosecond pulse duration are shown on this slide. Pulses were close to transform limited with time bandwidth product of about 0.32. Output beam profile at the highest output power is shown also on this slide. It was near Gaussian beam profile with up to the highest output powers. For picosecond laser operation, we first made a CW experiment with some power scaling by means of more powerful pump diode. As a result, more than 13 watts of output power and 39% optical efficiency obtained with 20% output coupler transmittance. 2 picosecond pulses with 12 watts of average output power at 999 nanometers central wavelengths were obtained for E/C polarization with 38% optical efficiency and 20% output coupled transmittance. Spectrum and autocorrelation trace at the highest output power are shown on this slide. It should be noted that it was non-soliton mod-locking mode with time bandwidth product of about 0.51 and Gaussian temporal pulse profile. Spatial beam profile is also shown on this slide. Schematic of the chirped pulse regenerative amplifier is shown in this slide. As I see, a terbium KIF laser here with about 100 femtosecond pulse duration, 25 nanojoule pulse energy, and about 1038 nanometers central wavelength was used. BBO-based pulse picker unit provides a pulse train with pulse repetition frequencies in the range from 1 till 200 kilohertz. Martinez scheme stretcher based on reflection grating was used for pulse stretching to about 150 picosecond pulse duration. A standard Z-shaped cavity was used for regenerative amplifier. Double biofocal cell was used to injection the pulse into the cavity, shown here. The final stage of the system is a compressor unit based on pair of reflection grating, the same as in stretcher. Pump unit and crystal geometry were nearly the same as in previous experiments. Okay, the most interesting situation was observed for E-C polarization. In this case, the amplified pulse spectrum, shown here, had spectral widths up to 50 nanometers, full width at half maximum, with the seed pulse spectral width of about only 12 nanometers. The features of the active medium gain profile for E-C polarization, you can see here, acts as a spectral filter for seed pulses during the amplification process that provides amplified pulses with wide spectra, even wider than seed ones. For a wide range of cavity round trips, pulse repetition frequencies, and the output powers without utilization of additional spectral broadening methods. Measured pulse duration was as short as 165 femtosecond, assuming Gaussian pulse shape, with the average output power of 4.5 watts and optical efficiency about 25%. Should be noted that calculated transform limited pulse duration was about 100 femtosecond. Other parameters are listed in the table. Okay, and the strong negative influence of gain narrowing effect, which is typical for ytterbium materials, was observed for E-B polarization. To explain the spectral behavior, a numerical simulation of the amplification process was carried out. The simulation was based on the split-step Fourier method, and the gain curve was calculated by means of the absorption and the stimulated emission cross-section spectra under a certain population of the upper laser manifold of ytterbium ions, which correspond to our experimental conditions. With successive passes of the pulses through the active medium, the population monotonously decreases, resulting in a change in the shape of the gain band. This leads to the light pulse spectrum evolution under its round trips through the amplifier, and such evolution are shown on this slide. The amplifier performance simulation is well agreed with the results obtained in the experiment. Calculated amplified pulse spectra have similar shape and spectral widths as measured experimentally. Such a different spectral behavior for amplified pulses for E-C and E-B polarizations can be attributed to the features of the relevant gain spectra with respect to the seed pulse spectrum. In the case of E-B polarized light, output of the seed central wavelengths well fits to the intense gain peak with the maximum at around 1040 nanometers, shown here, resulting in strong gain narrowing effect. In contrast, for E-C polarized light, the central wavelengths of the seed pulses coincide with the local minimum in a quite flat gain spectrum, providing efficient broadband amplification of the seed pulses. Okay, during the next experiment, we study a broadband seeded chirped pulse regenerative amplifier, and for this purpose, the following experimental setup was used. The main difference is in the stretcher unit. It was based on single mode fiber, shown here. This provided spectral broadening of seed pulses in the fiber, and the spectral profile is dependent on the incident pulse peak powers that illustrated on this slide. Okay, compressor unit in the schematic had separated retroreflector for relative temporal matching of the sub-spectral bands, shown here. Okay, spectral narrowing of amplified pulses observed for E-parallel polarization, which together with the use of seed pulses with wide spectrum leads to amplification of individual spectral regions. Here and here. This became possible due to the presence of two peaks in the spectrum of the stimulated emission cross-sections. Here and here. Autocorrelation trace of core spectrum is shown in the slide. Measured pulse duration of about 700 femtoseconds with average output power of more than 5 watts and optical efficiency of 22.5% were observed. Okay, and the presented spectroscopic properties and lasing characteristics of the terbium low-up crystal together with the good thermoptical properties makes this material an excellent candidate for active media of picosecond and femtosecond mod-locked lasers and chirped pulse regenerative amplifiers. And when planning further research, attention should be paid to a more detailed study of thermo-optical properties of the crystal. Mod-locking experiment at 999 nanometers also requires further development with the purpose of obtaining bandwidth-limited pulses. The task of effective compression of the wide spectrum pulses obtained in the regenerative amplifier is of undoubted interest. Okay, thank you for your attention.
All right. So this is the end of the talk, I believe. So, all right. So if you have any questions, please, you can directly send an email to him. So our next talk, I think we can just move on to our next talk, which will be given by Dr. Alka Svensson. Well, she has over 25 years of experience in optoelectronic industry, working various roles in many different companies. So most recently, she was appointed as a director. She was a director at Princeton Lightwave Company, which was acquired by Argo. And she recently joined to Kelvin Nanotechnology in November 2018. And Dr. Svensson, please.
Okay. Thank you. So thank you for the introduction, and thank you for giving me the opportunity to talk about Kelvin Nanotechnology. So I'll just give a brief introduction of Kelvin Nanotechnology, and we are a nanofabrication service provider. We are based in Glasgow, Scotland. And we are actually a wholly owned subsidiary of Glasgow University, and we are the commercial arms of James Watt Center fabrication facility in Glasgow, which is mostly used for research, but Kelvin Nanotechnology was set up to provide services to the industry. And we do three different things. We provide electron beam lithography. We provide prototyping capability. So electron beam lithography is mostly used in a lot of places, but it started out being used for DFB laser gratings. And for prototyping capabilities, we provide services to researchers and to companies who quickly want to make a prototype to see whether something is feasible or not before going on to much more manufacturable process. And we also do processing for quantum components for industry and researchers. So Glasgow University was actually just a little tidbit, was set up in 1451, and I believe it's the fourth oldest university, English-speaking university in the world. So my talk, what we do at Kelvin Nanotechnology, and when Kelvin Nanotechnology was set up, it was set up with a mind to provide services worldwide and to everybody. So on purpose, it was designed that we will not do any design work on the devices, because if we did the design work, there was a chance of us contaminating people's IP. So we do mostly processing for people. And so I can show you some of the processes we've done. Obviously, I can't share a lot of things we have done because of the non-disclosure agreements. But what I want to show you mostly is, you know, any university fab which has access to these equipment can probably do the processing. I know a lot of you have talked about in your talks where you have used or are using some of the fabrication facilities. So I just want to show you some examples of what's possible. But one of and it's possible to do a lot of good things with the nanofabrication facility, even the university type. You know, we have served over 170 companies in 23 countries worldwide. And we actually are manufacturing, we are part of the manufacturing chain for DFB lasers, which go in the datacom and telecom. And also we are partnering in the United Kingdom with companies and other universities to bring out the quantum technology, to provide quantum technology components. UK has put a lot of effort in the past few years, a lot of resources for quantum technology products. So what kind of fabrications facility we have, or what kind can be used? So the fabrication facility is at University of Glasgow, and it's called James Watt Nanofabrication Center. And it's actually in quite an old building, and the building is very old. And I'm not used to having fabs in an old building, but that's what it is. And there's clean rooms of 10, class 10,000 and 10,000 area. One of the things that's different about this facility versus other university facilities is that most of the equipment is run by the technicians and the research staff. And so the users don't really have the opportunity to change anything they want. And so it keeps the tools working well, and the tools are reproducible. So it comes in handy when you're doing manufacturing. It also comes in handy when one wants to know what's possible in real world. So it's actually sort of run like a real world facility. We have 2 electron beam lithography writers available, and over the years we've done over 50,000 jobs. They run 24/7. We also have photolithography, and we have some nano imprint technology. We have an EVG nano imprinter. We have lots of different tools for plasma tools for etching, for depositing metals, and so on. And we have a wealth of knowledge on fabrication know-how. The electron beam lithography is sort of like our flagship around which we build our other processes. And electron beam lithography can be, we have performed it in 3-5 material, 2-6 materials on glasses, exotic glasses, polymer, from 8-inch wafers to down to a small size. So it's pretty versatile, the tool, and I'm sure any university that has it, the tool is pretty versatile. So let me just show you some examples and point out some of the things that can be done in nanofabrication facilities. So Kelvin Nanotechnology supplies thermal AFM probes. So companies like Brooker and so on buy thermal probes from us. And these are the probes shown on a wafer. And on the right-hand side, I'm zeroing in on a probe. So the main thing about this is main thing about this probe is that this is a 3-dimensional electron beam lithography writing, and the scale, so this part is 20 micron. So it's a 3-dimensional e-beam lithography multi-level process. So this was done at 4-level process. and the electron beam lithography was actually written on a prism. So if I go here, there was a prism here, and this thing was patterned on a prism, and the rest of the silicon was taken away. What you see here is the silicon nitride. So that's one example of technology that can be, achieved. Some of the other examples are transistors. This is a T-gate transistor, which was an indium gallium antimonide material. And the trick here was how to make this T-gate. The trick was that we use multiple layers of resist. So really high resolution resist sandwiched in between what I call normal resist. And then we use different dosage of electron beam to define the structure and then finally lift it off the metal. The other what I'm showing here is nano gap. Those of you who are used to doing lithography know that it's harder to make gaps than to actually make structure. And what was done here was it was a statistical E-beam writing process. So the E-beam dosage was varied from high to low, low to high statistically, and then processed, and this happens to be the gap that was created. So this was just showing that very small gaps can be created with electron beam control. This is an example of a prototyping we did for a startup a while ago, actually a few years back, for solar cells. This is in gallium arsenide. And the idea behind startup was that they were willing to sacrifice some of the area, some of the transparent area, to get more electrodes, because they wanted to get as much current out as possible without heating up, thin electrodes out of the cell. And this was actually the problem here was a low-tech problem. Sometimes low-tech problems get you, not a high-tech. So what we did here was we actually we electroplated several microns of gold onto these electrodes. And the problem was that gallium arsenide, because of the galvanic effect, in the solution, we had lots of problems with that. So it was more of a what I call low-tech problem, but eventually we were successful in creating this prototype for the company. Some of the other example is this is a small pump. This is a microfluid pump, and I believe the surface is polyimide surface, and we patent electrodes for this one company. And as you apply electric field here, as you apply voltage, the membrane fluxes and then acts like a pump. One of the other companies that came to us to do some prototyping was a medical company. They were doing a photomultiplier tube for medical imaging. This is the back side of the wafer that you see, and these are structures just to support the wafer. On the front side, what we had to do was to etch at a 60-degree silicon, etch silicon at a 60-degree angle, which is not easy to do. It's not a simple matter of tilting the silicon. And we are using RIE etchers, so we actually had to play tricks with electric field to get the 60-degree etch. Obviously, if you have an ion etcher, you could do that without any problem. But for prototyping, you don't always have all the tools, and you have to make do with what you have. So this is an example of the prototyping that we did. This is a terahertz filter that was done for researchers. I don't believe this is actually the picture here is not really terahertz. I think this was at 350 gigahertz, and this had what it is. It's a silicon filter, and it has a structure which looks like log piled up in one direction and the logs piled up in other direction, and each filter has a hole so that you can put a lot of them together. You can mount a lot of them together. And what was unusual about it is that we used dry etch to etch silicon. So we first etched the top, Then we etched the bottom of, so total etch was 200 micron. And you may ask, well, why did you use a dry etch? Why not a wet etch? And the reason was that the researchers wanted very nice round holes, which is hard to get with the wet etch. And also they wanted very good side wall profile. And so we had to use a dry etch to etch all that silicon out. So these are just some of the examples of our past work. And we've also done we've also done Fresnel lenses. Here, actually the lines are quite large. They're over a micron, which is large for us. This is an 8-level electron beam lithography. The alignments had to be within 25 to 30 nanometer, and that was and it's 8 alignments, keeping 8 levels, keeping alignment to 25 to 30 nanometer. This is an example of moth eye pattern. These pillars, I believe, are 200 to 300 nanometer. This is an example of plasmonics, which is actually, there's a lot of interest in plasmonics, and I can't show you any of the photos for the work we are doing for customers, but essentially these are nanostructures. So when the light couples, different colors light up. And if you, this is an SEM photo. If you look at it under an optical microscope, you'll see like different colors, red and white and blue and green, depending on what the nanostructures are there. And there's a lot of interest right now for AR, for augmented reality application, to do these nanostructures, or meta lenses as they call them, for various applications. The other thing that we have done is, as I said, the UK government has an interest in quantum components and quantum systems, and so we worked with various researchers and universities to bring out quantum components. This is, I will talk more about this atom trap and ion trap in my next few slides, so I'll leave that for there. This is a 730 nanometer laser grating. These are sidewall grating, and I just want to show you what's possible to do with the grating. The scale here is 1 micron, and as you can see, the sidewalls are very clean. and so that's the kind of work that we actually do quite regularly, writing DFB grating on various lasers. Okay, so quantum technologies. So most of the work going on in quantum technology is for navigation, for timing, and mostly, and sensing. And we use timing just about everywhere in our lives today. We use them in the data centers. Even the tractors use the navigation GPS system to make sure they stay within the rows. And transport system use timing to move trains and and ships. So timing is used everywhere. And the idea is to develop quantum components and quantum systems to miniaturize. Most of the application is for miniaturizing the system, and also to make it more manufacturable. And in addition, to be able to do some of the navigation and for short periods of time when GPS may not be available, if you're going through a tunnel or if you're in a city where there's a lot of noise. And also for quantum computing. These are ion traps. They're on silicon, and qubits are essentially trapped. These are used to trap qubits, and the idea is you can string them all together to get many qubits to process, which is not the case today. And this was done in conjunction with the National Physics Laboratory and OptoCap. And one of the issues that we ran here, just wanted to point out some of the low-tech things that you have to keep in mind. One of the issues that we ran in here is that when we did these traps, on silicon wafers. We had good yield, except we couldn't pick them out of the silicon wafers. We couldn't release them very easily without breaking it. So one of the very low-tech idea was that you put a notch there so you can lift it out, and that helped a lot. So you just have to be careful that we don't get carried away with high tech, that we forget about how to make the devices. So today, the ion traps are really machined individually. They're machined mechanically, and so it's really hard to get repeatability and reproducibility at the right cost. And so the idea behind the research grant was to prove that they could be done at a wafer level, so that you could have more repeatability, reproducibility, in addition to small form factor, and in the future could reduce the cost, of making these microfabrication traps for quantum computing. And so what I want to show you is how we made it. So we began with a regular silicon wafer, and we grow thin oxide film, about 15 micron. And then we define the gold surface on both sides of the wafer, and they have to be well aligned, obviously, the top and the bottom. Then we etch the oxide, and on both sides again. And then we put the ohmic contacts on the silicon. And then we have to take all that silicon away in order to make a cavity, which is what we did. And then you have to coat inner surfaces with gold, and you have to be very careful because these are electrodes which are very close to each other, but I think about less than 50 micron. You have to make sure that you're within that, you're not over coating it and shorting the electrodes. And then we thicken it with electroplate, the gold. So that's how these were done. And the design was done by, again, National Physics Laboratory. And then in the end, the devices look something like this. You put these on a substrate and then wire bond, and that was the packaging work was done by OptoCap. And so this is the final device. The next quantum component that I want to show you is for atom cooling. It's a grating. It's essentially it's a grating which has 3 different linear gratings. And the idea is that when the light is shined, the reflected beams are all balanced so that you can trap atoms in the center. And it's a very small grating. It's about 1 inch by 1 inch. The way the atom trapping is done today, those of you who may not know, is there's a 6 beam that are used, which are very well aligned, and their polarization is controlled. And there's several different optics is used on, like an optical bench, where you have lenses and filters and splitters and wave plates, and then to trap the atoms in the middle. And then there's magnetic fields to condense the vapor further. What we wanted, what the idea behind this grant was to take it, and this system is done like in an optical table or an optical bench. The idea behind this was to make this optical bench into a smaller cell. So all that to be replaced by a cell about this big, which includes lasers and small magnets and everything. So the grating helps a lot, because you can just have a grating instead of having all the optics. You can have a grating which balances the beam, and you can focus it on a very small spot. For this particular grating, the spot size is about 6 millimeter. The vapor is formed about 6 millimeter away from the grating. And on this grating, the temperatures of a few microkelvins were observed repeatedly, and about 10 to the 7 10 to the 10 million atoms were captured. Now the next phase of this grant is, which we are working on with other partners, is to miniaturize the whole system and the cell, which is about this big. And the major challenges is not the grating. The major challenges now is to make the laser small enough and with high enough power and fidelity. And then the other challenge is how to keep the vacuum in that cell without having actually an active vacuum pump. And those are the things that are being worked on. Anyway, that's all for my talk. I hope I gave you a flavor of what's possible to do in university type fabs that have this kind of equipment, and what we have done at KNT. So I think I'll just stop there. Thank you very much.
Thank you, Dr. Svensson. So the session is open for questions if you have any.
Dear Alka, thank you very much.
You're welcome. Thank you. So.
Yes, any questions from the audience, please? All right, if not, we would like to thank Dr. Svensson and all the presenters in this session. Thank you so much, everybody. I think the next session, right, Professor Özçelik, will start at 7:15, right?
Yes. Yes, okay.
All right, thank you.
Thank you.
Thank you, Alka.
Thank you.
I hope we will see face to face in the future.
Yeah, if you're.
I will visit your company soon.
Yeah, please let me know. Yeah. Okay. Thank you. Thank you.
Okay. Have a nice
Bye.
night. Bye. Hi, Professor Mustafa.
Hi. Welcome everyone to the evening session of our conference. This is the last session. We will have 15 minutes talks in this session. And I remind you something. If you have any questions, please type it in the chat box. So in this session, our first speaker is Dr. Atilla Eren Mamuk from Muğla Sıtkı Koçman University. His title of talk is Determination of Presence and Molecular Orientation of the Liquid Crystal in the Core Sheath Structure of Electrospoon Fiber by Optical Method. Okay.
Okay.
I'm sorry. Thank you, Professor, again. My name is Atilla Eren Mamuk from Muğla Koçman University. I'm talking about a study which was performed by me and my colleagues from my university. The title of the study is Determination of the Presence of the Molecular Orientation of the Liquid Crystal in the Core Sheath Structure of the Electrospoon Fiber by Optical Method. And this is outline of my presentation, and one can find the main parts of the presentation in this page. Beginning of the presentation, I would like to talk about our motivation in this study. The electrospinning technique is a widely used technique in order to generate nano and micro scale fibers, and the electrospoon liquid crystal polymer fibers have been reported by various research groups in the literature, and they have a wide application area, potential application area, such as guide for drugs, gas sensors, or optical actuators, etc. Because they have a large potential application area, the characterization and generating of the electrospoon fibers are quite important. In our study, electrospoon fibers were generated by using single needle electrospinning technique. And polyacrylonitrile was a polymer, was used as a sheath material of the fiber. 5Cb, 6Cb, 8Cb, and their mixtures, which are the member of cyanobiphenyl liquid crystals, were used as a core material of the fiber. In the literature, there are several studies have been reported by different groups. For instance, Bertocchi and the co-workers reported a study for specifying the existence of liquid crystal and the orientation of the liquid crystal within a fiber by using polarized 2D Raman mapping technique. And in our study, we have used different techniques in order to specify the existence of liquid crystals. For instance, infrared spectroscopy and colorimetric techniques, as you see in this picture. And also we have performed some optical techniques. As you know that the liquid crystals exhibit high birefringence, but polyacrylonitrile shows very low birefringence. Considering the differences between these considering the differences between the birefringence of the polyacrylonitrile and the liquid crystals, we have carried out an optical carried out a measurement by using polarized optical microscopy, by using an optical retarder and without using an optical retarder. And as you see on the upper row, the electrospoon fibers can be obviously observed, but we couldn't distinguish the existence of the liquid crystal in the fiber. But the images without using any optical retarder, the existence of the liquid crystals can be determined because of high birefringence. As you see in the picture on the lower row, the liquid crystal inside the fiber are very visible. And it is known that the liquid crystals exhibit anisotropic properties at distinct temperature interval, namely in a mesophase region. But above this temperature interval, the liquid crystals behave isotropic liquids. I mean that the liquid crystals lose their anisotropic properties. By taking advantage of these properties of the liquid crystals, we also carried out the temperature-dependent birefringent analysis. So we took, according to these, we took some images at 42 Celsius and 28 Celsius. In the images taken at 42 Celsius, which is a temperature about the mesophase region of the 5 CB we used in this structure. At this temperature, as you see that the electrospoon liquid crystal polymer fibers cannot be observed. But in the images taken at 28 Celsius, the liquid crystal inside the fiber can be observed, and they are very visible because of high birefringence. These results may reveal these. How can I say? By considering these results, one can say that the existence of liquid crystal can be determined by using these birefringence techniques. At the last part of the study, we have done the angle-dependent birefringent analysis. The intensity of the transmitting light passing from the planar-oriented liquid crystal can be described by this equation. And in this equation, the first sinus term is associated with the intensity of the transmitted light by depending on the angle phi. And this phi is an angle between the liquid crystal molecules and the analyzer. For instance, a bulk liquid crystal which is confined in a planar-oriented sandwich cell, maximum transmitted light can be obtained at 45 degrees. And by decrease in the magnitude of the angle, the intensity of the transmitted light decreases too. By benefiting from this relation, a circumscribed electrospoon liquid crystal polymer fiber was oriented 45 degrees with respect to analyzer. And as you see that the electrospoon fiber is quite visible and shiny. By counterclockwise rotating the plate of the polarized optical microscopy, the brightness of the fiber decreases. And finally, the electrospoon liquid crystal polymer fiber can be observed completely dark when the fiber is oriented parallel to analyzer. And as a result of this study, it was expected that the liquid crystals should be self-settled inside the electrospoon nanofibers as a core, and the polyacrylonitrile should surround the liquid crystal as a polymer shed. This expectation was proved by benefiting of the anisotropic properties of the liquid crystal by using polarized optical microscopy, and also taking advantage of the ability of the liquid crystals that change the polarization direction of the incident light. We indicated that the liquid crystal was planarly self-ordered within the core of the PAN polyacrylonitrile shed. And you may also find the references I used in this study. And at last, I would like to thank the Center of the Research Laboratories of Muğla Koçman University for technical support. And also, I would like to thank Dr. Çağdaş Koçak and Dr. Elif Çiğdem Demirci Dönmez for their kind contribution to this study. Thank you for your kind attention.
Okay, we thank our speaker for this nice talk. So we still have 5 minutes. If you have any questions, so we can take the questions. Let me ask you a question. Is there any critical temperature? And you mentioned about some temperatures, but is there any critical temperature?
Yes. In this study, I used a 5 CB liquid crystal, and the 5 CB liquid crystal exhibit mesophase anisotropic properties at between the 22 Celsius to between 22 Celsius and about 38 Celsius. It depends on the type of liquid crystal you use in your study. So for this study, about 38 Celsius, you can see the isotropic liquids. You will obtain the isotropic liquids. But if you use a different liquid crystal, you can play with the temperature interval.
Okay, thank you.
You're welcome.
So if no other questions, we can invite our next speaker. So our next speaker is Lala Gahramanli from Nano Research Center, Bakü State University from Azerbaijan. And the title of talk is Controllable Synthesis of Ni-X Zn1-X as nanoparticles on the base of Ni-Z and Al layered double hydroxide PVA composite matrix.
Hi everyone, I greet the conference participants. My name is Lala Gahramanli from Bakü State University. I will talk about influence of various technological factors on the optical properties of cadmium zinc sulfide nanoparticles. My talk will be in 4 parts. In the first part, I'll be informed some information about cadmium zinc sulfide nanomaterials. In the second part, cyanochemical and Siler synthesis method. The next several experiments which we have carried out. Finally, I'll go talk about effects of various technological factors. Now, let's turn to the first part of my talk, which is about the binary and ternary semiconductor nanomaterials. Cadmium sulfide and zinc sulfide belong to second and sixth group materials, binary chalcogenide compound materials. The characteristic absorption of light for cadmium sulfide is in the visible range with a bulk band gap of 2.4 electron volt at room temperature, and band gap value of zinc sulfide is 3.8 electron volt. This structure have hexagonal and cubic structure as shown in the picture. Among these semiconductor compound, the ternary semiconductor compound cadmium zinc sulfide has received much attention. Much of the interest in these solids is due to their band gap being between 2.4 and 3.8 electron volt. Depending on the composition of the ternary compound, the obtained sample are formed in color between yellow and white. Then let's speak about application field of these materials. Cadmium sulfide is an important semiconductor material and has many application fields, such as pigments, solar cells, photovoltaics, LEDs, and etc. In the current development, the wide bandgap semiconductor of zinc sulfide are useful for the optoelectronic device, infrared glasses, screen panels, sensors, lasers, and so on. The replacement of cadmium sulfide with a higher bandgap ternary cadmium zinc sulfide films can lead to a decrease in Windows absorption loss and use UV diodes, electroluminescent device, Windows layers, and etc. Then I would like to speak about the two different synthesis methods. One of them is Siller synthesis method. This means successive ionic layer absorption and reaction, which call it Siller synthesis method in short, for the position of the thin film. The Siller growth is divided at least in 4 different steps presented in this mechanism. There are the absorption, rinsing, first rinsing, reaction, and second rinsing. In the first step of the Siller circle, cationic source is absorbing of the surface, forming an electrical double layer. This layer is composed of 2 layers. From the inner, it means that positively charged, and outer negatively charged layers. The positive layers consist of the cations and the negative from the counter ions of the cations. The excess and absorbed ions is rinsed away from the diffusion layer. This results in a saturated electrical double layer. Then in here, various solutions can be used as a solvent. However, in our experiment, ethylene glycol was used because PVA was used as a polymer matrix. Here, it is it is an effective synthesis for nanomaterials. Here, it is possible to easily control the number of cycle, absorption, rinsing time, and etc. parameters. It is possible to control the thickness of material obtained by such a change of parameters. Then the next slide is about the sonar chemical synthesis method. In liquid irradiated with a high intensity ultrasound acoustical cavitation, the formation, growth, and collapse of bubble provide the primary mechanism for sonochemical effects. During cavitation, bubble collapse produces intense local heating and high pressure. In our experiment, I would like to speak our several experiments. We have carried out both Siller synthesis method and sonochemical synthesis method. These materials, binary cadmium zinc and zinc sulfide, and ternary cadmium zinc sulfide ternary nanomaterials, both of powder and thin films. In here, we can change technological condition, synthesis temperature, concentration, circle number in Siller synthesis method, different initial reagents, such as couple of cation source, and etc. Then I would like to speak first of all sonochemical synthesis method. Let's first look at the absorption spectra of samples obtained by sonochemical methods. For study, the optical properties of synthesized nanoparticle are investigated using ultraviolet visible absorption spectra in E part, and in B part, the absorption spectrum of synthesized cadmium zinc sulfide with different capping agents, as shown in the picture, E part and B part. In here, the bandgap value of all synthesis sample shown as a table. The bandgap value of cadmium zinc sulfide nanoparticles approximately change in 2.45 to 3.80 electron volt. It is known that bandgap value of these materials is 3.66 to 2.97 electron volt. It is clear from our research the bandgap value of synthesis samples with MPa, it means that different capping agent, MPa, PVA, styrene, in the value of X equal 0 to 0.4 are lower than that for the crystals in the literature. As shown from the result, the width of the bandgap zone varies depending on the type of used capping agent. It be related to the two factors. One of them, the size of particle may vary depending on type of capping agent materials, which show in the table. So this can be also due to changing of particle size depending on capping agent materials. The second one, the optical properties of nanoparticles may also be related to the effective mass of the electrons in the phase of their limitation and the difference in the effective potential in the space that they moved. The difference in the effective mass of nanoparticles from bulk crystal are connected with a change in electronic potential of charge carrier in small particles. Then in similar method, two coupled cation sources have been used. The samples were measured at 200 to 900 nanometer wavelength range at room temperature. There are transmittance spectra of cadmium zinc sulfide nanocomposite synthesis from the first cation source at 5 circles. The X equal this value. And the next one, the bandgap value of cadmium zinc sulfide synthesis from the second cation source when X equal 1.1 and 1.2. Then the bandgap value of cadmium zinc sulfide nanocomposites synthesized different circle number, 1 circle and 2 circles. Then the bandgap value are shown in the table. The bandgap value of nanocomposites is degrees with the increase of cadmium zinc ratio is solution. It should be noted that there was a significant difference between the crystallization environment and the ratio of ions with the nanoparticles using different salt as cation source. As we know, the bandgap value of nanoparticle decrease as increasing the concentration of cadmium ions in cadmium zinc sulfide nanostructures. The decrease in bandgap value depends on growth of the particle size. Using polymer matrix as a substrate, in contrast to other synthesis method and other substrate, the sorption centers are located inside the polymer, and there is a certain distance between these centers. Besides, it is interesting what happens after annealing of these materials. And we have done these materials thermal annealing, which have been obtained at room temperature, and this material obtained room temperature at the same time different growth temperature, 14 Celsius and 65 Celsius. You can see the systematically in the next slide as a table. From the table, we can note that with increasing of fraction of cadmium ions in the solution, the bandgap of forming compound decreasing and shift toward the bandgap of cadmium sulfide, which equal 2.42 electron volt. The result of calculating the particle size according to the Debye-Scherrer equation from XRD results show that with increasing temperature to 40 Celsius, the particle size increasing and equal 4.3 nanometers. This apparently is associated with an increasing in the density of absorption centers and the activation of coalescence process in the volume of the polymer matrix. A further increases in the temperature, which means the gross temperature, leads to decrease in the particle size, which apparently associated with a melting of the polymer matrix. Then the band gap value of samples at different growth temperature are increases slightly from 3.5 electron volt to 3.14 electron volt during the formation of 40 Celsius. And increasing is the temperature of formation to 40 Celsius leads to decrease in the band gap value, which equal to 0.37 electron volt. It should be noted that the defect structure of nanoparticles interaction with the environment and particle can affect the band gap value. The sample which obtained at room temperature will have been thermal annealing at 60 Celsius and 120 Celsius. Nucleation of particle occurs when the experiment is carried out under temperature, but the subsequent aggregation is weakened by the effect of temperature. This may be due to the effect of reaction speed on the formation process. This is because as the temperature increases, the chaotic motion of the particles accelerated, and a stable environment is not created for this aggregation. So, as we know, as increases the concentration of cadmium ions in the solution and temperature of cadmium zinc sulfide, band gap of nanoparticle is decreases. The decreases of band gap value is depending of growth of the particle size. Then, as a conclusion, we can say that it has been shown that the particle size and band gap value depend on the type of different capping agents. When we sample our thermal annealing, which we obtained at room temperature, with an increasing the density of sorption centers and the activation of coalescence process in the volume of the polymer matrix, further increasing in the temperature leads to decrease in the particle size, which is apparently associated with the melting of the polymer matrix. The band gap of nanoparticle increases slightly from 2.05 electron volt to 3.40 electron volt during the formation of 40 Celsius, and increasing in the temperature of formation to 40 Celsius leads to decrease in the band gap, which equal 2.37 electron volt. It should be noted that the defect structure of nanoparticles, interaction with the environment, and the particle size can affect the value of the band gap. Thanks for your attention.
Okay, we thank our speaker for this beautiful work and presentation. So we still have more time. If you have any questions, you can ask. Okay. If no more questions, we can move on to next speaker. So we thank our speaker again. So we invite our next speaker. Our next speaker is Sevinç Mamatyarova from Bakü State University. And her title of talk is the effect of magnetic field on structural and optical properties of neo nanochains.
Hi, everyone. Hi, everyone. Do you see my presentation?
Yes, we can see it.
I am PhD student at Nano Research Center at Baku State University. I would like to thank the conference organizers. The title of my talk is The Effect of Magnetic Field on Structural and Optical Properties of Nickel Oxide Nanochains. Nickel oxide nanochains were successfully synthesized by effective and environmentally friendly chemical reduction methods under different magnetic fields, followed by thermal oxidation at high temperatures. For the synthesis of nickel nanoparticles, hydrazine hydrate and sodium borohydrate were used as reducing agents. Ammonium citrate 3 basic was used as a nucleating agent. In order to determine the size, structure, optical properties, and morphology, the obtained products were characterized by X-ray diffraction, ultraviolet visible spectroscopy, transmission electron microscopy, and scanning electron microscopy. Additionally, the effect of reaction time, different magnetic field intensity, and oxidation temperature on the size and morphology of synthesized nanoparticles was investigated in detail. The X-ray diffraction patterns of nickel nanoparticles synthesized under different magnetic fields are shown in Figure 1A. In the XRD pattern of nickel nanochains synthesized at 25 millitesla, 3 diffraction peaks were observed corresponding to face-centered cubic structure of a nickel nanocrystal. In the XRD pattern of nickel nanochains synthesized at 42 millitesla, only 1 diffraction peak was observed. The broad peaks in the patterns are attributed to the small size of nanoparticles. No peaks corresponding to nickel oxide or nickel hydroxide were observed in the XRD pattern of samples before thermal annealing. The average crystalline size of nickel nanochains synthesized under 25 millitesla, 42 millitesla, and 81 millitesla external magnetic fields are 5.82 nanometer, 1.98 nanometer, and 2.19 nanometer respectively. After thermal annealing at 400 Celsius in the excited pattern of samples synthesized at 25 millitesla, 3 additional small intensity peaks were found, which are attributed to the face-centered cubic structure of nickel oxide. It indicates that the surface of nickel nanochain is coated with small-sized nickel oxide. In this decaptogram, nickel-related peak intensity has increased and the width of the peak is reduced. It is attributed to the increase of particle size at high temperature. When the temperature was raised to 600 Celsius, the intensity of the nickel oxide peaks increased. Similar behavior was observed for samples synthesized at other external magnetic fields. The calculated average crystalline sizes of samples synthesized under external magnetic fields are shown in table. The crystalline size was estimated separately for nickel and nickel oxide based on the most intense peaks in the diffractogram. As can be seen from the results, the average size of as prepared nickel nanoparticles in nanochain have decreased with increasing magnetic force. After the oxidation of samples at 600 Celsius, the size of nickel oxide formed on the surface of nickel nanochains increases with increasing magnetic force. This is related to the faster oxidation of small particles due to their high surface energy. The second reason for such a sharp increase may be a combination of particles amongst themselves. As can be seen from the table, the size of nickel nanoparticles increase with increasing annealing temperature. Apparently, during the heating, nickel nanocrystals were combined with each other before the oxidation of nickel to nickel oxide. The bandgap values of samples are also shown in table. One can see that in nickel-nickel oxide nanochains synthesized at 25 millitesla magnetic field, the size of nickel oxide decreases when the temperature rises from 400 Celsius to 500 Celsius, and the bandgap increases from 3.81 electron volts to 3.1999 electron volts due to quantum size confinement. However, there are some exceptions. For example, when the temperature rises from 500 Celsius to 600 Celsius in nickel-nickel oxide nanochains synthesized at 25 millitesla and 81 millitesla, the size of nickel oxide decreases and the bandgap decreases too. We can't explain it with quantum theory because, according to quantum theory, the bandgap must increase with decreasing size. The reason of this can be explained by the fact that all metals, including nickel, have a very low bandgap. When the size of nickel oxide increases, the absorption of ultraviolet rays increases too. Therefore, nickel cannot prevent the lowering of the bandgap of the oxide. At relatively high temperature, the size of nickel oxide decreases and nickel hinders the increase of the bandgap of oxide. The optical properties are highly dependent on nanoparticle size. As can be seen from the results, it is possible to control the particle size by changing the reaction parameters. Optical bandgap is an important issue for semiconductors, which makes possible their application in optoelectronics and photocatalysis. SEM and TEM were used to determine size and morphology of obtained samples. Figures 4A and 4B show the same image of nickel nanoparticles and nanochains synthesized under 25 millitesla magnetic field at 10 minutes and 30 minutes reaction time respectively. When the reaction time was 10 minutes, only well-dispersed spherical nanoparticles with an average diameter in the range of 38-64 nanometers were observed even if a magnetic field was applied. When the reaction proceeds for 30 minutes, linear nanochains assembled by particles with the average diameter in the range of 56-88 nanometers were formed, and length of chain was about 6 micrometers. The reaction time affected the size and morphology of the nanoparticle. At 10 minutes reaction time, the magnetic moment of each particle is randomly oriented because magnetic interaction between nanoparticles is too weak. As can be seen from the results, the nanoparticle size has increased during the longer reaction time. When nanoparticle size reached a critical value, the magnetic moment of each particle is aligned in the direction of the external field, and consequently, necklace-like chains were formed. After oxidation of nickel nanochains at 400 Celsius, the diameter of nanochains increased to about 68 103 nanometers due to the formation of nickel oxide on the surface of nickel. Figure 5 shows the same image and selected area electron diffraction pattern of nickel-nickel oxide nanochain synthesized at 25 millitesla external magnetic field after oxidized at 600 Celsius. It can be seen that spherical particles are assembled in the form of a chain-like according to same results. The average diameter of nickel-nickel oxide nanochain is in the range of 97 133 nanometers. The selected area electron diffraction pattern, which is shown instead of figure 5, consists of several diffraction rings, and it indicates that synthesized nickel-nickel oxide nanochains have a polycrystalline structure. As a conclusion, we can say that nickel-nickel oxide nanochains are attractive structures due to their unique properties. In this work, nickel-nickel oxide nanochains were synthesized by oxidation reduction method. Chain-like morphology was confirmed by SEM and SEM analysis. Optical properties were investigated. Optical properties of these nanochains were investigated for the first time. Optical properties depend strongly on the size of particles. It is possible to control the size by changing the parameters such as magnetic field intensity, reaction time, and oxidation temperature. Thanks for your attention.
We thank our speaker for this nice work and talk. So we still have more time. And if you have any questions, you can ask. So no questions? Okay, then let's thank our speaker again. And we invite our next speaker, Mudathir Yahya from Bursa Uludağ University. And the title of talk is Influence of Electron Incidence Angle on Position Resolution. Okay, you can go ahead.
First of all, I would like to thank the organizer of the second international conference on light-based technology for giving us this opportunity to present our work, which is titled Influence of Electron Incidence on Resolution in Crystal Calorimeters. This work was done by me, Mudathir Yahya, student at the Department of Physics, Bursa Uludağ University, with collaboration with my supervisor, Dr. Fatima Kocha. In our time, I'll give brief introduction to isocrystal and then move on to position resolution. And I will talk the method we use to get this result and conclude this work. The isocrystal, inorganic crystal in general are used in high energy physics to detect particles such as electron, positron, or photon. The energy measurement in this crystal and the energy released of the incident in the crystal material. And light Central light generated in the show development be detected by photo detectors such as a branch photodiode and photodiode placed at the end of the crystal. In this view, you can see that the major crystals that are used in such as activated sodium iodide, activated sodium iodide crystal, deep tungsten crystal, and lyso crystal. And if we compare our crystal with the other crystal, you can see lyso crystal has stepping power due to 4 cubic centimeters. Also, this lyso crystal has small radiation links and radius about 1.4 centimeters and 2 centimeters. Lyso crystal has about 25 photon per, and also the emitted photon this crystal is a bit 402 very about seconds. In this figure, we can see that the transmission spectrum of the lyso crystal in wavelengths ranging between 60 nanometer to 600 nanometer. Also, it transmits photon from the wavelengths 180 to 600 nanometer, and the emitted photon reach a peak of 102. Position resolution. When the electron, high energy electron, hit the circulation crystal, its energy is deposited in the central crystal and near crystal. Position of the can be described by the center of the gravity matrix, which can be calculated from this gravity summation deposited in the ice crystal times the position of the ice crystal, sum of the energy deposited in the crystal. Here, between the X gravity and Y gravity, they are about 500 MeV and 2 GeV, and can be shown here for 2 GeV. Station was narrower than at 500 MeV. This crystal also proposed for use in many experiments in high energy physics. One of them is the experiment, and we use the result in comet experiment in order to validate our accuracy, the accuracy of our in this work for simulation. Magnetic calorimeter, as can be shown here, for to be used in comet experiment at Japan Proton Research Complex, is consisting of 7 times 7 crystals, which has a length of 120 millimeter and cross section of 20 times 20 millimeter. And of result, as can be shown here, the one on you can see the jump result are well matched with the experimental data obtained from comet experiment with a slight difference at low energies. Validate our accuracy of we used to simulate electron passing through calorimeter consisting of 9 crystals of 200 millimeter and cross section of 25 millimeter square. This work was first to be used at Turkish Accelerator Center, and we, in order to find the distribution of the center of the gravity of the positive energy in the crystal, we injected the electron 14 different places. Also, we use to study the position resolution. Here we can see the relation between position calculated from the center of gravity techniques and position, and we found this relation result shape like as a normal incidence, as can be here shown here for this MeV, and shape for the non-normal incidence at degree. The center of gravity results in S shape, as I said earlier, of linear variation for the determination of true position. To move this non-linearity between the true position and center of gravity position, the correction curve were fitted by using this equation, x gravity equals c and d, x2 minus e. And we used, after we calculated this parameter c, d, and e, as can be shown here in this table, we inverse this equation, the correct position of injected electron. As can be seen here, x corrected divided by d inverse x gravity divided by c plus e. The result, as can be shown here, it results in a shift. For that reason, we use function fit this results. And the sigmas here demonstrate position resolution. And as can be shown here, for 500 MeV, the position resolution is about 4 millimeters, and for 1 GeV about 3.1 or 3.2 millimeters, and for 2 it's about 2.4 millimeters. Results, we found a relation between the injected electron energy and the position resolution. And as can be seen here, as the energy increases, the position resolution decreases, which indicates that the position resolution gets better, increasing energy. For the position resolution in energy can be found from this equation. For example, in an x coordinate, sigma x equal 2.77, 0.07 divided by square root of energy times of 6 plus 0.9. And also same result are obtained for the coordinate. We studied the difference of the incident electron and position resolution. And we found that, as can be shown here, relation between the obtained position resolution sigma x and the root of energy. For normal incidence at 0 degree, the position resolution obtained, as can be shown here, and as the energy increase, position resolution is getting better. And for 5 as can be here, degrees incidence and 15 degrees incidence. To study the dependence of the position resolution, hanging normalizing the position resolution at 0 degrees. Sigma theta divided by sigma at 0 degrees. And as can be shown here, as a decrease, the position resolution is getting bigger, which indicates that the position resolution is getting worse. So as increase, the resolution can get more worse here. Also, we studied spatial resolution in the whole surface of the crystal, and we found that the position resolution is not constant in the whole surface of the crystal, depending on the impact position. As you can see here, position resolution is best at the edge of the crystal. For example, for 2 GeV, found to be less than 1 millimeters, and at the center is found to be more than 2 millimeters in X and Y. We studied the spatial resolution, non-normal incidence, and we found that this effect is more important because the position resolution is better right hand side of the, as can be shown here. One in this is for normal incidence at 0 degree, and one is 15 degrees. And so that we can see that the right hand is getting better for 1 GeV and 2 GeV. In conclusion, the Monte Carlo simulation has been performed for LICE crystal for meter intended for the Turkish accelerator center, considering the incident electron energies 100 MeV to 2 GeV. Position resolution for a matrix consisting of 3 times 3 isocrystal has been solved by using the center of gravity techniques. For 1 GeV electron, position resolution is 3.9 millimeter in the center of the and 0.96 millimeter at the edge of the crystal. As we said earlier, the stochastic for the position resolution is also found about 2.77 millimeters. For non-normal incidence, position resolution at 15 degrees, this was done at 0 degree by a factor of 1.2 at 1 GeV and 1.5 at 2 GeV after deletion. This 1.2 for 1 GeV and roughly 1.4 GeV. For non-normal incidence position resolution getting better hand side of the crystal as we showed earlier. Thank you for your attention.
We thank our speaker for presenting his nice work. So if you have any questions, so we can have them. We have plenty of times. No problem. No question. Okay. Then we thank our speaker again, and we invite the next speaker. Our next speaker is Huriye Gencal from Bursa Technical University, and her title of talk is a new approach to enhance the bandwidth value of UTC PD. Okay, yes.
Can you see my presentation?
Yeah, you can start.
Okay. Hi, everyone. Thank you for coming. My name is Huriye. My purpose today is to explain a new approach to enhance the bandwidth value of UTC PD. I have divided my presentation into 6 main points. First, I will give you a brief information about UTC PD, and I will explain using inter-hertz frequency range. Then I will talk about the design of UTC PD and modified UTC PD by adding embedded structure. After that, I will represent result and discussion. And finally, I will explain conclusion and I will finish the presentation. First, I would like to start with introducing UTC PDs. UTC PD meaning is Unit Traveling Carrier Photodiode. The band diagram of UTC PD shown in figure 1. Active region of UTC PD consists of 2 layers. One is P-type indium gallium arsenide absorption layer. The other is N-type indium phosphate collector layer. As seen in figure, the red one absorption layer, the blue one collector layer. First, the light injected from bottom end contact and pass through the collector. Sorry. And then absorbed in the absorption layer. The electron and hole pairs are generated in absorption layer, and carrier electrons are diffused and directed to the collector layer. In this structure, only electrons are employed as traveling carriers. Since the electron velocity is higher than the hole's velocity, so high speed and high output can be achieved by a new structure. With the development of potential application in terahertz range, such as radar, remote sensing, imaging, spectroscopy, and wireless communication, the importance of terahertz waves has become more remarkable recently. So photodiodes are important components of the system, and it's necessary to develop photodiodes. Figure 2 shows that representation of terahertz waves in the electromagnetic spectrum. These waves are in the electromagnetic spectrum between 0.1 to 10 terahertz, as seen in figure 2. Design of UTC PD. The UTCPD was designed by using numerical with two modules. One is FTDT, the other is device. FTDT means finite difference time domain. This module is required to obtain the optical generation ratio. The other module is device module. This module is used to perform electrical analysis of the device. Firstly, reference UTCPD is designed. The epitaxial layer structure of UTCPD given in table 1. Which material were we used, what are the layer thicknesses, what type of doping was used for each layer. Table 1 shows that this information. A structure is created by using this information. Modified UTCPD by adding embedded structure. The 3D structure of reference UTCPD designed by using device module of numerical are shown as seen in figure 3A. This is a reference UTCPD. The purpose here is to show the change in bandwidth value by placing the circle material horizontally or vertically between the absorber and collector. The 3D structure of modified UTCPD are shown as seen figure. In figure B, circle material placing vertically. In figure C, circle material placing horizontally. Result and discussion. The gold, silver, copper, and silicium material were selected, and two illumination types were used: X direction illumination and Z direction illumination. For two illumination types and for different embedded materials, and radius value is increasing. The results are summarized table 2. According to the result, gold materials should be selected, and light should be applied Z direction, because here is the highest value. The bandwidth is 239 GHz approximately. The bandwidth value has been obtained as 20 GHz for reference UTCPD as shown in figure 4. When an embedded structure, gold structure is inserted between absorber and collector, the bandwidth value is increased as shown in figure 5. As shown figure, for reference UTCPD, bandwidth value is 20 GHz. For modified UTCPD, bandwidth value 239.30 GHz approximately. As can be seen from the graphics, bandwidth value is increasing. In summary, when we use an embedded structure in UTCPD, the bandwidth can be increased. Thus, the modified UTCPD can be used at terahertz frequency range. The reference UTCPD was not changed, just we added a new structure in it. Thus, 3D shape doesn't change. Here our aim is to accelerate electron, that means to enhance carrier transit time. According to the result, gold material should be selected and light should be applied from Z direction. The modified UTCPD was operated under zero bias, thus the energy consumption and self-heating problems due to bias circuit can be removed. Thank you for your attention.
So we thank our speaker for this nice talk. So if you have any questions, you can ask. We have plenty of time. So our listeners are so silent. So you all understood everything? Okay. Okay, then let's thank our speaker again. So we invite our next speaker. Next speaker is Şamil Şirin from İzmir Yüksek Teknoloji Enstitüsü, and his title of talk is Distributed Current Sensing via Optical Reflectometry.
Thank you, Mr. Sarısaman. I am Şamil Şirin from İzmir Institute of Technology, Electronics and Telecommunication Department, and I'm a master's student under the supervision of Kıvılcım Yüksel Aldoğan. And my presentation will be on distributed current sensing, electrical current sensing. The main motivation behind this purpose is the fact that the worldwide electricity consumption is increased year by year. So demand for monitoring higher electrical current in power plants grows. And there is a need of safe, compact, and cost-effective current sensors. And optical ones are good candidates for this purpose. And so I'm studying on that. Let me continue with my outline. I will start my presentation by reviewing the conventional electrical current sensors. Then I will move on fiber optic current sensors based on Faraday effect principle. And then after that, I will briefly introduce OTDR methods. They are optical time domain reflectometry methods. And then I will narrow my scope to polarization sensitive optical time domain reflectometry. And I will sum up my presentation with sharing some simulation results of polarization sensitive optical time domain reflectometry. Let me start by some physical principles of current sensing. One of the most popular current sensing method is Ohm's law. However, it cannot be used in high current measurement due to excessive power loss. And another one is Hall effect sensors, and they are operating in a narrow range, so they also cannot be good candidate for high current measurements. And you see their range is too low for this purpose. And also there are principles based on measuring the magnetic field induced variation of shape or resistance of a magnetostrictive or magnetoresistive material. And they are also restricted to a narrow range. So what are being used now is the sensors based on Faraday's law of induction. However, they are restricted only to measure AC currents, since the Faraday's law of induction states that the current that is inducing a magnetic field, if it is varying over time, the magnetic field would be varying over time, so it would induce an electromotive force. So we can use this principle. So the first condition is that the current of interest must be varying over time. And they have two main sensors. Current transformers are employing a ferromagnetic toroid so that their sensitivity can be enhanced. But due to this ferromagnetic material, they are open to hysteresis or saturation, etc. And their size must be larger to handle higher currents. On the other hand, Rogowski coil does not employ that kind of ferromagnetic material, so they do not have these advantages. However, their sensitivity is less, and their common drawback is, as I said, they can be used only for AC measurements. Let's move on to Faraday effect. The Faraday effect can be described as follows. If a magneto-optic material is under magnetic field, it exhibits circular birefringence proportional to the magnitude of magnetic field parallel to the light direction. And because of Biot-Savart law, current induces a magnetic field around it. So we are actually trying to measure the magnetic field first. And the circular birefringence causes linear polarization axis of the propagating light to be rotated at an angle theta sub f that also can be called Faraday rotation angle. And this Faraday rotation angle is related to the strength of magnetic field, as you see here. If the length of magneto-optic material is assumed to be very short, then the magnetic field can be assumed to be constant during this L. So it can be expressed like this. And here there's an important parameter that is Verde constant. It describes the strength of Faraday effect for a particular material, that is magneto-optic material. And if it is high, our sensitivity to magnetic field is high. And also this Verde constant is temperature and wavelength dependent. So we want to use magneto-optic materials with high Verde constants. However, interrogating these kind of magneto-optic materials require using bulk optics generally. So it makes the setup a bit more complex. Instead of that, we would like to employ optical fibers as magneto-optic materials, so as sensors. However, their Verde constant is low, but it can be compensated by winding the fiber around the current carrying conductor. And let's move on to fiber optic current sensors. As you see, the total Faraday rotation for fiber coil with radius r and n number of turns is n can be expressed as v times n times I. So increasing n can compensate the low value of Verde constant. And there are numerous configurations for fiber optic current sensors, but I'm sharing only three of them, three general version of them. One of them is an interferometric type. It interrogates the sensing fiber that is winded around the conductor by sending circularly polarized light from both ends due to these quarter wave retarders. And they counter-propagate, and they get Faraday-induced phase difference. And when they are interfered, this phase difference can be obtained. So the Faraday rotation angle can be obtained, and it can be related to the current of interest. And its relation to the detected intensity is given like that. Other types are also existing in the literature. One of them is using reflector instead of using two-sided interrogation technique, using one-sided but with a reflector. And this quarter wave retarder is differently connected here with a 45-degree aligned axis, so that the propagating light in the sensing fiber has both right circularly polarized and left circularly polarized components. So their phase difference is measured in this type. And in the second type, the Faraday mirror is used to compensate the linear birefringence, which is coming inherently in optical fibers, and it can deteriorate the circular birefringence that we wish to obtain. So a Faraday mirror can compensate the linear birefringence. Now I'm moving to backscattering based fiber optic sensors, and I will come back to current sensing technologies. As light propagates down the fiber, it is scattered by the interactions between light and the crystalline structure and vibration frequency of fiber itself. And the backguiding portion of the scattered signal, called backscatter, is classified according to a wavelength of them. And these two, you're seeing these two, beryllium and Raman backscatters, they are inelastic backscatters. So their frequency, their wavelength are different from the incident light. On the other hand, Rayleigh backscatter is an elastic phenomenon. So there are different sensing interrogation methods based on measuring these backscatters. One of them is polarization sensitive optical time domain reflectometry. And now I will focus on polarization sensitive optical time domain reflectometry to use them in current sensing. Its general schematic is like that. Interrogating pulse is sent, and the backscatters during the pulse is traveling in the sensing fiber are collected in detector using a circulator, and the detected power in the sensing fiber is given like this, and you see it is a function, it is the function of distance z. Since we can understand when the backscatters arrive to detector. So we can relate the power and the distance so that it allows us to take distributed sensing. And when we get this equation, so it is a sinusoidal expression, as you see, and we are trying to extract the theta sub f here, and it is embedded in capital delta, and it is directly related to special frequency of this expression. And once we extract capital delta, we can calculate theta sub f. Here, the little delta is linear birefringence and can be obtained from the spec sheet of sensing fiber, and then we can find current. Here is a POTDR simulation result, and we adjusted the sensing fiber between 20 and 35.7 meters. And the radius of coil, of course, affected this location. Also, the number of turns of the coil affected this location. And our beat length is 480 meters, which means our sensing fiber is a very low birefringent fiber. So we can get the circular birefringence without any distortion. And our resolution cell is determined by the length of our interrogating pulse. And it is fairly short so that we can get a nice resolution on the graph. And the lead fiber has no change in the power, but in the sensing fiber, we are observing a sinusoidal form as expected from the previous expression. And when we focus on this sensing fiber, we can extract capital delta by using a Fourier transform, for example, or we can employ curve fitting to obtain capital delta. As a conclusion, distributed current sensing techniques bring a new dimension to optical fiber sensors. And from optical time domain reflectometry-based sensing techniques, POTDR technique is simulated, as I have shared with you. And simulation results show that current can be obtained from power trace of POTDR, and conventional and also optical current sensors have been examined in this presentation. And investigation of different OTDR techniques is in progress. For example, there is phase OTDR, which is another very popular interrogation technique, and we are also studying on this topic. Thank you for your attention.
So we thank our speaker for this beautiful presentation. So if you have any questions, you can ask. So no questions. Okay, we thank our speaker again. And we invite our next speaker. Our next speaker is Ertunga Burak Koçal from İzmir Yüksek Teknoloji Enstitüsü. And his title of talk is Simulation Tool Development for FPGA-aided FOTDR Vibration Sensors.
Can you hear me?
Yeah, we can hear you.
Okay, thank you. Hello everyone, this is Ertunga Burak Koçal from İzmir Institute of Technology, Department of Electrical and Electronics Engineering. In this presentation, I will give brief information on simulation tool development for fiber Bragg creating aided phase-sensitive optical time domain reflectometer vibration sensors. And I will start my presentation by explaining our motivation to develop a simulation tool. Reflectometry-based techniques have been around for more than 30 years in distributed optical fiber sensing field, and for long-range vibration sensing applications, Rayleigh scatter-based techniques have been used most commonly, and their popularity has increased in the last 10 years due to their advantages over conventional sensors. And some of their advantages are their lightweight, small size, durability in harsh environments, and immunity to electromagnetic interference. With increasing popularity, we have seen numerous system configuration and signal processing techniques proposed for phase OTDR systems. However, development process of a phase OTDR system is costly and time consuming, and for this reason, we have developed a detailed and practical simulation tool. Now, I will give some information on OTDR systems, and I will explain what's the difference between conventional OTDR and phase OTDR systems, sorry. Then I will share some simulation results with you. The operation principle of OTDR is based on measurement of Rayleigh backscattered signal, and Rayleigh scattering is an elastic process caused by molecular inhomogeneities and dopant density fluctuations in optical fiber. The light traveling along the fiber experiences scattering, and some portion of the scattered light is recaptured and guided towards the input end, and it's measured there. The measurement procedure can be summarized in 3 steps. Consecutive pulses are generated and launched into the fiber under test, and then the backscattered light is guided towards the detector, and at each measurement, the time delay between the launch time of the probe pulse and the arrival time of the backscattered signal is recorded. As the velocity of light is known, distance for each measurement can be determined. As for phase OTDR systems, their main difference from conventional OTDR systems is the line width of the employed light source. In phase OTDR systems, narrow line width lasers are used, and they provide longer coherence length than the probe pulse width. As a result, the backscatter signal response of the fiber is formed by the coherent interferences between scattered signals. And this obtained signal profile maintains its form as long as the fiber under test is held unperturbed. In this figure, timescale transformations used in phase OTDR systems are shown. phase OTDR systems obtain signals along two axes. The first one is phase time axis. It corresponds to the delay between the proposed launch time and the backscatter signal arrival time, and the slow time axis. Along the slow time axis, measurements taken with successive pulses are arranged, and they are separated with a time which is equal to pulse repetition period. In order to develop a simulation tool, we have used one-dimensional backscatter impulse response model, which has been used to analyze the characteristic of Rayleigh scattering in optical fiber for a long time. In this model, a hypothetical fiber is approximated using a linear filter in which SI and TI denote the amplitude and the relative delay of ith scatterer. In order to obtain Rayleigh backscattered signal, we have used an ideal rectangular pulse as an excitation signal, which is expressed with equation 2, where tau p denotes the pulse duration, omega s is the angular frequency of the quasi-monochromatic optical carrier, and phi is stochastic phase modulation. By using the first and second equation, we derive the Rayleigh backscattered signal, which is expressed as a convolution of h of t and e of t. And by using equation 3, we can derive the signal intensity, which is expressed with equation 4. Based on this formulation, we have developed our simulation tool, and in this figure, I presented a phase OTDR traces of a perturbed fiber generated under perturbation. For demonstration purposes, we have used a short fiber. A 10-meter long fiber was interrogated with a pulse of duration 10 nanoseconds. And in this simulation, 1 meter long fiber section between 5th and 6th meter were subject to perturbation. This perturbation modifies the refractive index of the fiber and shift the positions of scatterers in the fiber. By subtracting each trace from the first one, by using the first one as a reference, we can obtain the absolute values of signal power variations, which can be used to detect presence of external perturbation. As you can see, there is no variation on any point if there isn't any perturbation on there. One other trend in distributed vibration sensing application is the implementation of fiber Bragg gratings into these systems. Fiber Bragg gratings can be used to detect change in temperature, strain, pressure, and vibration, and they can be cascaded and interrogated simultaneously using different multiplexing schemes like wavelength division multiplexing or time division multiplexing. In this case, we can say this is a time division multiplexing scheme. In this figure, uniform fiber Bragg grating structure is shown, where L sub FPG denotes the grating length and lambda is the periodicity of the refractive index modulation. Okay. In this figure, reflection and transmission spectrum of FPG is shown. As you can see, response of FPG is wavelength dependent, and in the presence of perturbation causes refractive index modulation and change in refractive index cause variation in FPG response. And the change in the response cause variation in obtained signal power, and we can detect that variation. In phasor TDR system, different configurations used with FPGs, comprising different number of FPGs also. And in one type of the configuration, FPGs written in the optical fiber are arranged as pairs and interrogated by a pulse that covers FPGs, two successive FPGs, and by analyzing signal variations at interference zone, we can detect the presence of external perturbation applied between FPGs in a pair. The reflected electric fields from FPGs in a pair can be expressed with equation 5 and 6, where delta phi of t denotes the experienced phase difference by the probe pulse between FPGs in a pair, and capital T of t carries information of transmission coefficient of all preceding FPGs in configuration. The most common shim used in vibration sensing applications consists of large number of equal spaced FPGs, as shown in the figure, and by using a pulse that covers at most 2 FPGs at any time instance, phasor TDR signature shown in the figure can be obtained. As you can see, we have interference zones which contain signals from 2 FPGs, and by tracking variation in this zone, we can detect presence of external perturbation. As an example, we have simulated a basic configuration and presented simulation result in this picture. In this configuration, 6 identical FPGs are written in a fiber, and 3 vibration events were applied at different locations. The first vibration event was applied on the first FPG, second vibration event was applied on third FPG, and the last vibration event was applied on the last sixth FPG. The applied variation can be detected by analyzing signal power value variations on interference zone, as I explained before. The first applied vibration event can be detected by analyzing the variation in sensor 1, because the first interference zone, which is named as a sensor 1 in here, contains signal from the first and the second FPGs. And slow time analysis results are presented on the right for 3 events. That's all I want to say. Thank you for attention. Thank you for your attention. I can answer any questions.
Okay, we thank our speaker. So do you have any questions?
No.
So we have plenty of time. You can ask any question. Okay, we thank our speaker again for his nice talk. And we invite our next speaker. So Our next speaker is Yusuf Mert Gümüşay from Gazi University. And his title of talk is Development of IR Optical Chopper Disk by Thermally Evaporated ZNS Thin Films.
Hello, can you hear me?
Yeah, we can hear you.
Okay. Hello everyone, I'm Yusuf Mert Gümüşay from Gazi University, and I'm going to present development of infrared optical chopper disk by thermal evaporated zinc sulfide thin films. Before I start, I would like to give a chance to present our work in this wonderful conference. And thanks a lot to my supervisor, Süleyman Özçelik, and other researchers from Gazi Photonic Research Center for their contributions. Firstly, I will give a brief information about how pyroelectric detectors work and how it's used in thermal cameras. And after that, I will explain what is the importance of optical